Alright, hello everyone. Let me set the context. This video is going to be divided into two parts, the beginner stuff in Rust and then the slightly advanced stuff in Rust. We have already done the beginner stuff once in a longer 4-hour video. So this should have ideally been part 2, but I'm still going to recap everything we have covered in part 1. If you want a more toned down version of part 1, then you can go to the 4-hour video. It's on YouTube. If you want to recap it very quickly, if you want to, if you understand usual constructs of a language, for example, things like conditionals, loops, functions, then you can just go through this part 1, which covers all of this in 1 hour. This video covers all of this in 4 hours. Pick and choose which one is more relevant for you based on, your current level. This is going to be part 1, probably an hour to 2 hours. Then we'll go through part 2, where we will be covering some new concepts in Rust we haven't touched until now. Specifically things like vectors, iterators, HashMaps. These are collections that are very commonly used in various languages, not just in Rust. How do you create them in Rust? What are the challenges that come here? Then we'll understand the difference between strings and string slices. It's a very subtle but important difference. Then we'll go through generics. We covered them a little bit in part 1. We'll recover them in part 2 on the current part. Traits, multi-threading, macros, futures, async await, and Tokyo. We'll try to cover all of this. Most probably, my current guess is that asynchronous Rust we're probably going to do in another video. It probably deserves a video of its own. So 0.8 and 0.9 that I've mentioned over here may or may not be covered in today's video. Everything else that you see over here, including lifetimes, is what we will cover. The things that you see in green are slightly easy. The things that you see in orange are not too difficult to understand. And the things that are written in red are slightly harder to digest. So, based on what section you're on, feel free to go slow, do a bunch of practice, so on and so forth. Without any further ado, let's start with part 1. Let's recap our 4-hour video. Let's go through all of these concepts one by one, kicking things off with installing Rust in our machine and doing a very basic IDE setup. What does IDE mean? Visual Studio Code, WebStorm, whatever is your, integrated development environment. How do you set it up for Rust? To kick things off, you have to first understand how to install Rust on your machine. The easiest thing you can do over here is go to the official page and it will give you a script that you can run on your machine. Once you run the script, Rust should be working. Let me quickly show you what that looks like on my laptop. I already have it installed. But if you look over here, this is the official Rust page. This is the command that I ran on my machine. If I open my terminal and try to run the same command again, it will probably tell me Rust already exists. It asks me to reinstall. Let me just reinstall to show everything again. I would probably go with step 1 over here. Proceed with standard installation. There we go. Rust is installed for me. How can I confirm that Rust is installed? If you run cargo over here in your terminal, if it gives you an output that looks something like this, it means you're good to go. If running the cargo command tells you Rust package manager and gives you a bunch of commands that you can run using it, then you are good to go. If you run cargo and you get an output that looks something like this, command not found, cargo, not cargo 1, cargo. If you run the cargo command, it gives you an output like this. It means you've not been able to install it correctly. So first, make sure you debug through all of these problems. Have it installed locally. How do you know you have it installed? If you run cargo, you should see something like this. Step 2 is setting up Visual Studio Code. That's the IDE that we are going to use. Feel free to, follow the same steps. Probably not the same step. If you are using WebStorm, NeoVim, Sublime Text, then the steps will be fairly different. I would assume most people here use Visual Studio Code. So over there, the steps are fairly simple. There are 3 extensions that are good for you to install, but one extension that you should definitely install, the Rust Analyzer. So in your Visual Studio Code, you might have seen this plugins section over here. Let me just show you to it. On my machine, if I open Visual Studio Code, there is this section over here called extensions. Over here, you can search for 3 extensions. The Rust Analyzer, I already have it. If I go over this, it asks me to reload, probably because I just reinstalled Rust on my machine. But you should see a button over there that says install. Make sure you install this and two more extensions which might be good for you to install. Code LLDB, this will help you to run Rust code directly from your IDE, and 𝗏𝗁 because this is a common format for a bunch of Rust files. 𝗟𝗶𝗸𝗀, what does format mean? Don't worry about, but basically you might have heard of JSON or YAML as two, formats for configuration files. 𝗏𝗁 is fairly similar. Rust uses 𝗏𝗁 very frequently, which is why it's a good idea for you to install this so you can, see color highlighting in your 𝗏𝗁 files. That's pretty much it. That's all you have to do in the first section. That should complete installing Rust and doing the IDE setup. If you want a more detailed video, the 4-hour video is there, covers this in a little more detail. With that, let's move on to initializing a project locally. All right. Initializing a Rust project locally is fairly simple if you have Rust installed locally. There are two types of projects in Rust. One are called binaries and one are called libraries. Binaries are mostly what we will be dealing with today, and which, as the name suggests, a binary is a final binary that you run. It is like a end user application. 𝗟𝗶𝗫𝗀, what is a end user application? The backend of a website, a command line interface, an operating system, a dictionary assignment code that you might have written. Anything that you write is an end user application. And what is a non-end user application? If this is my end user application, it can use various libraries. These are called libraries. Rust lets you create libraries as well. The goal of a library is that you write reusable code that other people can use. And what is an end user application? The final thing that actually executes in production. Think of this as your Node.js project, and think of the library as something like Express. So whoever has written Express has written a library in Node.js, and whoever writes their own Node.js project uses this library in their end user application. So there are two types of projects that you can create in Rust: an end user application for which the command to run is cargo init, or you can create a library for which the command to run is cargo init --lib. Today, most of the code that we'll be writing ideally should be a library because we're just testing code. But to avoid any complexity here, because here you have to write some tests to actually run the code. Since this isn't an end user application, you can't just run it. You write tests to run it and test your code. To avoid that complexity, today we will just be creating a binary package. How do you do it? Cargo init. Let's quickly try that out. If I go to my terminal over here, let me create a fresh folder called Rust part 2-1. Let me go to this folder and let me open this folder in Visual Studio Code. In this folder, now let me run the In this folder, now let me run the cargo init command. The cargo init command would initialize an empty cargo.toml file, and it will create a source/main.rs file. These are the two files that you should see after you initialize a binary project. If you initialize a library, then you wouldn't see main.rs, you would see lib.rs. We'll come to what that is and when you might want to do this. Today, we will create a binary package for which you run this command, it initializes a package for you. You have a main.rs file. This is where we'll be writing all of our code. Now, if this feels overwhelming to a few, if you cannot install Rust locally, the best thing you can do is just go to 𝗏𝗶𝗹𝗀𝗀it, which is a platform that lets you create, a similar Rust environment on the cloud, so you don't have to run it locally. Go to 𝗏𝗶𝗪𝗀𝗀it.com, click on create REPL after you sign up, select Rust as the language over here, and click on create REPL. You will get a very similar environment over here. If you look at this Rust environment, on the left, it has cargo.toml, it has source/main.rs. What do I have over here? Cargo.toml, source/main.rs. Ignore the target folder for now, ignore what cargo.lock is. Here is where we'll be writing all of our Rust code. Eventually, we will come to what is cargo.toml, why do you need it? It is similar to a Maven file in Java or a package.json in JavaScript. It has, the name of your package, the current version of your package, and all of your dependencies. Eventually we'll be getting other people's code in, using other people's modules. So we will be filling this dependencies section. Right now it's completely empty. This is where we'll be writing all of our code. If you find problems trying to write this code, go to Replit and you can write the same code over here. This is how you run it in Replit. As you can see, hello world gets printed over here. This is how you run it locally. Run the command cargo run in the VS Code terminal, and you should see hello world printed on the screen. Cool. If you saw a while back, there was a warning over here. It was just telling me, okay, this is a toml file. You should install the toml extension. Can you see the warning over here? That is why I suggested that you install the toml extension. If you do, you will see some nice colors over here. Even if you don't, that is fine. That is all that we had for this section, which is how can you initialize a project locally or on the cloud based on your, familiarity right now. If you want to do it on the cloud, that is fine as well. Let's move on to writing some Rust code next. We'll understand variables, conditionals, and functions. Fairly simple stuff. All right, let's go through variables, conditionals, loops, and functions through a bunch of examples. I think the best way to learn the syntax is by going through a few assignments and quickly solving them. The first assignment that we will be solving today is going to be write a function called isEven that will take a number as an input and returns either true or false based on if it is an even number. So this will teach you how to create a function. This will teach you how to define a number variable. This will teach you how to call a function. All three of these things, how do you do them in Rust? Let's see it first pictorically, and then we'll code it ourselves as well. This is the final code. There is a main function in Rust, which is the entry point of your application. This is the first thing that runs anytime you execute a Rust program. In here, I am saying, please print. What does this print ln macro do? This is not a function. This is a macro. We'll come to what macros are, but since there is an exclamation here, this means this is a macro. Think of it very similar to a function. It says, please print a dynamic variable. That is what these curly braces over here mean. Print a dynamic variable, the value of which is this function call. Is_even is a function that is defined here. Find the return value of that function and print it on the screen. That is what this specific assignment over here does. I have defined a function. I've printed this function call on the screen. I've defined another function over here. The function is called is_even. It takes one argument as an input, and the argument is of type i32. What does i32 mean? It means it's a signed integer with 32 bits. 𝗏𝗏𝗃, what does signed integer mean? What does 32 bits over here mean? Signed integer means it can be positive and negative. 32 bits means it follows certain constraints. It can only be as big as some number 2 raised to the power 31, and it can be greater than minus 2 raised to the power 31 minus 1, something like this. It follows some constraints like this. It cannot be an infinitely long number. It is a 32-bit number. Can there be bigger numbers? Yes, you could have a 64-bit number as well. You could write i64 here as well, but we are just dealing with smaller numbers right now, hence i32. In a different language like C++, you might see this as int. In a language like TypeScript, you might define this as number. But in Rust, you describe numbers as i32, u32, i64, u64, so on and so forth. This is unsigned, this is unsigned, this is signed, this is signed, this is unsigned. Whenever you have u, it means it's an unsigned number, which means it can only be positive. Whenever you have I, it means it can be both positive and negative. This is the argument to the function. And what does the function return? It returns a Boolean. It returns whether or not this number is even. And then we have the final function body, which checks if num modulo 2 equal to 0. Now notice we don't have parentheses over here. You don't need them in Rust. You do need them in other languages. But in case of Rust, you can add parentheses, but you don't need to. If the condition is true, if num modulo 2 equal to 0, what does modulo 2 mean? It means the remainder. Whenever num is divided by 2, the remainder that is left, if it is 0, then it is an even number and hence we return true, else we return false over here. That is the implementation of this function. We'll be coding it very soon. Quickly to recap, I am defining the main function over here. I am calling the isEven function over here. I have defined the custom isEven function, my own function over here. This is the name of the function, is_even. These are the arguments to the function. We have a single argument called num, the type of which is i32. It returns back a boolean, and this is the function body that actually calculates the final answer. That's how you write a function in Rust. This is our final implementation. Let's try to code it really quickly in our browser, in our VS Code as well. We define a function called is_even. The common practice in Rust is to not write camel case. You might be very used to writing something like this in JavaScript, but in case of Rust, you don't write camel case. You write whatever this case is called, snake case. I think I could be wrong. You basically separate the words by an underscore. You don't have a capital letter over here. It's just standard practice. You can still write isEven, but general practice in Rust is to write variables like this. What is the name of our argument? Number. What is the type of our argument? Could be u32, could be i32, depends on what kind of number it is. What does it return? It returns a boolean. What is the function body? Okay, if num mod 2 equal to 0, then we return true, else we return false. As simple as that. And over here, if I want, I can create a fresh variable. Let answer equal to is_even of, let's say 10, and then print the answer over here, something like this. That works as well. Or I can directly put this is_even function call over here, just like I did in the slides. So feel free to do either. This is slightly more digestible code. So this is the final code that I have written. Let's try to run it really quickly. Let me open the terminal here at the bottom. And how do you run code in Rust? Cargo run. What output does it give us? It outputs, wait for it, true on the screen, because is 10 an even number? Indeed it is. Is 11 an even number? No, it isn't, which is why it returns false. What did I say? I is unsigned. If I make this, I is a signed number. I repeat, i32 is signed, which means it can be negative and positive. If I give it a negative value over here, it will still execute for me. If I run cargo run, it still gives me false over here. But if I make this u32 unsigned, what is an unsigned number? कि भाई इसका कोई sign नहीं होगा. You can't pass negative numbers over here because I made it an unsigned number. Ҳर्कीरत, why would you want to make a number unsigned? You can store more data. I mean, for people who've done unsigned and signed numbers, you probably already know why this is done. The reason this is done is so that if you know a number can only be positive. If it's a u32 number, I can store a much bigger number over here compared to if it was a i32 number. If it was an i32 number, then one of the bits, if these are the 32 bits, the first bit is stored for the sign, which is why you can not store as many numbers in a i32 number. You can store some negative numbers, some positive numbers, but if you have an unsigned number, then you can store many positive numbers. That is why you might want to use unsigned integers. Cool. Hopefully that's fairly simple. Let me again show you the final code. It looks something like this. And as you can see, if I give it a very big number, Rust starts to complain again. It says literal is out of range for i32. It says i32 numbers can only follow this range. So what can I do? Let's say, I was passing this maximum number plus 5, or 9, something like this. It starts to complain. It says, yeah, this is a very big number. So what can I do? I can change the argument to i64. Here I have a 64-bit number. This is a much bigger number compared to a i32 number. It's almost, many times bigger, which is why, this bigger number is also now accepted as an argument. But of course, there is a limit here as well. If I make this very big, then, it will start to complain. Okay, the integer value is too long. Cool. All right. First function is done. This is what the function looks like. Let me commit and push this onto GitHub, so you have a reference of all of these codes in a final repository. All right, I've deployed a repository. You'll find all the code for today over here, so feel free to go code by code over here, and if you're not able to code it yourself, you can just copy the code from here. This is the first code for the day, the isEven function. Let's move on. The next function that we're defining today is a function fib that finds the Fibonacci of a number it takes as an input. I'm sure the people who are into competitive programming are suddenly very happy, and the people who hate competitive programming are going to dread this problem, because it requires a very basic, Fibonacci algorithm for you to know. I keep forgetting the algorithm from time to time, but the algorithm looks something like this. Okay, Fibonacci is a series. Just how this can be a series 1, 2. Wow, it's like really thin. 1, 2, 4, 8, 16, 32. This is a series where every number is doubling up. Similarly, Fibonacci is a series that starts like this. 0 is the first number, 1 is the second number. The third number is sum of these two. 0 plus 1, what is that? That is 1. The fourth number is sum of these two. What is 1 plus 1? That is 2. The fifth number is the sum of these two, which is, what is 1 plus 2? 3. The sixth number is the sum of this and this, which is 2 plus 3 equal to 5. The next number is 3 plus 5, that is 8. The next number is 5 plus 8, that is 13, so on and so forth. It's just a series that, has some significance in the real world, but don't worry about what that is. This is how you calculate the Fibonacci series. So can you now try to code it? Can you try to code a bunch of these, variables or this very long pattern such that you have to eventually write a function that finds the Fibonacci of a number it takes as input. For example, if the input is 3, then you have to find the 0th, 1st, 2nd, 3rd number in the Fibonacci series, that is 2. If the input is 5, then you have to find the 0th, 1st, 2nd, 3rd, 4th, 5th element in the Fibonacci series, so on and so forth. It takes an index as an input, could be any number between, let's say, 1 to 200, and you have to find, that specific Fibonacci number in that pattern. Cool. The code looks something like this. I've already written it for you. Ignore the main function, it does nothing over here. But if you notice the function below, it is a function called fib. I've defined a function, the name of which is fib. It takes a number as an input over here. It first defines two variables, first and second. Both of these are mutable variables. This is something new I'm introducing a little early. Mutable variables are variables whose value you can change. Think of them as non-constants. I repeat, these are non-constants. Any variable that you define in Rust by default is a constant. Just like in JavaScript, you write const a equal to 1, and then you cannot change the value of a at all. Similarly, in Rust, every variable that you define, you cannot change its value unless you add the mute identifier here. So let mute first equal to 0, let mute second equal to 1. I have some base conditions. If num is 0, return the first element over here. If num is 1, return, 1, which we know by default, is the first answer. So these two base cases we have hard coded. If the first element is wanted, return 0, second element is wanted, return 1. And then after that, we basically run a for loop for I in 1 dot dot num minus 2. Go from 1 to num minus 2. Basically, this is the first answer, this is the second answer. And every answer after that, third, fourth, fifth, sixth, we calculate by running this for loop. And what do we do over here? We first create a temporary variable called second. I repeat, if in the first iteration, what will happen? Let's dry run this. 0 is the first element, 1 is the second element. First contains 0, second contains 1. What are we doing in the first iteration over here? We are saying temp equal to second. So we are creating a new variable called temp. We are storing 1 over here. So temp will be equal to 1. Then we say second equal to second plus first. So what will second become? Second will become this plus this, which is again 1. And what does first become? First becomes temp, which is, this thing over here, 1. So what do the first variable and second variable get replaced with? The first variable gets replaced with 1. The second variable gets replaced with 1. We have slowly moved on to the next two elements of the series. That is how we're implementing the Fibonacci algorithm here. Fairly common algorithm, you'd probably do the same way in various other languages. What will happen in the next iteration? In the next iteration, again, temp will be redefined. We will be redefining the temp variable. First will be 1, second will be 1. After the first iteration, what will the two variables be? After the first iteration, first will become 1, second will become 1, and then we set temp equal to second, so this 1 value will go to the temp variable, and then you get the idea. Second will become second plus first, which is equal to 2, and then first will become second, which is equal to 1. And then finally we return second when we're done iterating. After we iterate a few times, let's say the user wanted the 100th element, we keep updating the value of first and second. First and second pretty much, keep going up this chain. Okay, first and second are first, this value and this value. Then they become 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 this value and this value. Eventually the final value is what we return. That is how we have written the Fibonacci algorithm over here. To recap, I've defined a variable called first, which is a mutable variable. What does mutable variable mean? It can be changed. Then I define a variable called second. Then I check, is there the input element 0? Then I return the first value, or return 0 over here. Is the input 1? Then I return 1 over here. Then we run a for loop. This is one of many ways to run for loops in Rust, which is for I in the range that you want to run it through, and then do whatever you have to do finally, return the value. That is how we've written it. This is our final algorithm. Before we move to the next slide, let's quickly code it. Shouldn't take too long, probably less than 5 minutes for you to code. I know you're a coding monster. Probably will take me like, maybe 10 minutes. So let me quickly write this. What are we doing? We are writing a function called fib. What does it take as an input? It takes a number as an input, which is, an unsigned or assigned integer. This can actually be unsigned. This will always be a positive number. So, you don't have to worry about making it signed. In the main function, I'm going to write println, let's say, fib of 10. And what was the code over here? I defined two mutable variables. Mute first equal to 0, mute second equal to 1. And what did I do next? If num is 0, then I would simply return first. If num is 1, then I would return second. And lastly, as you can already see, I have some warnings over here. Okay, why do you have extra curly braces over here? So you can get rid of them. And what is the other problem I have right now? I haven't defined a return type over here. So let me give it a return type. Again, this can be an unsigned number because it will always be positive. Return second. And then lastly, what are we going to do? We're going to iterate for I in 0 dot dot num minus 2. Let temp equal to second, second equal to second plus first, first equal to temp. And then we finally return the second variable over here, and we're good to go. That is how we write the Fibonacci algorithm. We don't use I over here, so it is giving us another warning. So you can write for underscore in 0 dot dot n minus 2. Since we are not using this variable, there is no point of defining it or giving it some value. If you give it a I value, it will give you a warning. It will still compile, but this is better practice. So just replace it with underscore. Cool. This is what our final code looks like. Feel free to take a pause and try it out. Code it yourself. Let me quickly run this locally. Cargo run, and you see what's printed on the screen is 34. I would assume that is right. I have no idea. I hate the Fibonacci series since years, but let's try a number that I think I know of. The answer for fib of 4 is indeed 2, is it? Let's see. Yeah, fib of 4 is 2. I think that, well, fib of 4 is not 2. Fib of 3 is 2. This should probably be num minus 1. You get the idea. Debug the algorithm. Most probably it needs to be num minus 1 and not num minus 2. That looks much better. Yeah. Fib of 0. Let me just write it down for you. Fib of 0 is 0. Fib of 1 is 1. Fib of 2 is 1. Fib of 3 is 2. Fib of 4 is 3. So fib of 4 should be 3, which means my logic was a little incorrect. I need to iterate from 0 to num minus 1 and not num minus 2. Cool. Let's proceed. The next problem, the last problem for today. Well, the last problem for the basics is going to be write a function called getStringLength that takes a string as an input and returns its length. This one's, I would assume, fairly straightforward. If you know how to define a string, there are various ways to define a string. The one that we're going to use is the simplest one, which is, if you look at the main function over here, let my string equal to string : from hello world. This is one way to define a string by using the string type that Rust provides you. There are various ways. We will come to the more complicated ways in the second section. We define the string. We call a function called getStringLength chars. We pass the string as an input. The input comes over here. We return the final value over here. This is an implicit return, by which I mean I don't write return followed by the final thing over here and put a semicolon. I don't do that. I just write the final thing. It is implicitly returned from the function. That is one complicated thing we have done over here. I repeat, what is the complicated thing? I haven't written return over here. I haven't put a semicolon over here. If you don't do that, it's the same thing. If I don't put a semicolon here and don't write the return statement here, it is still implicitly returned from the function. s.chars is a function that returns you all the characters of the specific string, and .count returns you the total number of characters. That is, the function call that we've done over here. So we are relying on this string type over here to, get the characters and get the total count. That is one complicated thing over here. The other complicated thing is the type. If you notice, the type is not string, it is @stir. And if you remember from the beginning of the class, so we are going to learn about this very soon. What is the difference between a string and a @stir? To keep things simple, I'm going to just replace this with a string in the final code over here where I'm going to write. But I hope this is clear. If not, this will actually be coming very soon when we'll understand the difference between references, ownership, borrowing, things like these. All right, let's try to code it. I'm going to define a function called getStirLength that is going to take. I'm going to just take a string as an input. There are various things that happen differently if I write string over here, if I write @string over here, if I write @str over here. We're going to discuss all of these eventually when we reach, the borrowing and ownership section. But before that, I'm going to keep it simple. What did we write? str.chars, which returns you all the characters. .count will return you the count of this specific string or the number of characters in this specific string. And I'm going to change the return type to be whatever the return type of this is, which is usize, which is a smaller number, I think, compared to i32. Then I'm going to define a string over here, function let name equal to string from 𝗥𝗲𝗄𝗃. And then I'm going to say let length equal to get_string length for this string, and then I can just print it. The length of the string is len, and that's it. That's all that was expected. The only thing to learn was this. The other thing to learn was references, but we haven't gotten there yet, so let's not worry about that. Very simple function over here that implicitly returns this. If I want, I can write this here as well. It's the same thing. All right, let me run it. Cargo run. It says, wait for it. This is one of the reasons that Rust is ridiculed so much. The compilation times are really high. The length of the string is 8, so we're good to go. Let's proceed. Let's understand next. What are structs? Why are they used? We understand some basic primitives like strings and numbers now. Let's understand what are structs. Why do you use structs? How can they make your life a little bit easier? All right, let's understand structs next. Structs in Rust are actually very similar to structs in C++. They let you structure data together. Basically, if you have a use case like this, where you have a user who can be active on your website or not, based on let's say they've verified their email or not, and they have a username, they have an email, they have the total number of times they've been signed into the platform. Then it's a good idea for you to structure all 4 of these into a single object rather than having 4 different variables: user1 active, user1 username, user1 email, user1 sign in count. Having a single variable, something like this, let user1 equal to a struct of type user, and these are the 4 values of that user. The user is active, this is their username, this is their email, and this is the number of times they've signed in. This is how you can define a struct so that you have all of these values for a single user in a same place. They are similar to objects in JavaScript. If you've used objects in JavaScript, you've probably seen something similar. Okay, you define something like this. Okay, let user equal to an object where you write username, something, password, something. Similarly, struct in Rust lets you first define what is the type of this structure going to be. Then you can declare various variables on top of that structure with dynamic values, different values. And if you want to print the details of a user, for example, if you want to print their username, you can access it by user1.username. That is how you create a variable or create a struct. Let's quickly try to code this. I would assume this is fairly simple to code. I first define a variable here called, or a struct here called user. What are the properties? Let's say for us over here, it's going to be first underscore name, which is a string, last underscore name, which is a string, and age, which is going to be a number. And over here, I can now create an instance of this user object. Let user equal to user with the first name being string from 𝗥𝗲𝗳𝗏𝗀𝗀, last underscore name being string from sing, and then the age being, let's say, whatever, 32. Just saying hypothetically. That's how you define it. And how can you print it? Based on whatever you want to print. For example, if you want to print just the user's name, that's how you can print the user's first name. If you want to print their last name, you can write something like this. 𝗥𝗲𝗳𝗏𝗀𝗀, can I print the whole object? Something like this. You cannot, as you can see, but eventually when we will understand a few extra things, macros and traits, then we'll understand how can you implement the debug trait on user. What does implementing a debug trait mean? We'll get to that's the new things we're going to learn. But long story short, you cannot simply print it. The println macro does not know how to print this user structure. It has no idea. Okay, how should I print it? It has no default printing implementation, which is why you can still print the first name or the last name, because the println macro knows how to print a string. It does not know how to print a random struct, which is why this is going to give you an error. If I write this code, it clearly also shows me that last name and age you have defined, but you are not using them at all. Are you sure you need them? Rust will give you warnings like these from time to time. If I run this code, what do you think gets printed on the screen? A few warnings get printed to begin with. The code is still building, and then eventually 𝗥𝗲𝗳𝗏𝗀𝗀 gets printed on the screen, which is exactly what I had printed over here. Cool. That's hopefully fairly simple, nothing too complicated over here. Some standard questions you might have is, 𝗥𝗲𝗳𝗏𝗀𝗀, can I make a field optional? Can I make age is, you can either provide age or not provide age? And the answer is yes. We'll come to that very soon when we reach enums. You can make some of these fields optional. How do you do that? We'll be coming to very soon. Cool. That's structs. The other important thing around structs is that you can implement functions on structs. The closer comparison between structs and JavaScript is that structs in Rust are actually more closer to a class in JavaScript. This is the sort of on-site session I did in Bangalore as well. I'll probably post a video right after this if this felt a little overwhelming. Struct specifically, there's a much more beginner-friendly in-person workshop that I took where I explained the same thing. But long story short, if you want to compare structs to something in JS, they are closer to objects, but they're more closer to classes, because classes have methods associated with them. Classes have static methods associated with them, and both of these things you can do in Rust as well, or specifically, both of these things you can do using structs in Rust. To kick things off, let's understand what I mean when I say implementing structs. We have defined a struct. I just defined a user struct over here. We have defined a rectangle struct which has a width and a height. But this isn't enough. You might want to find the area of a rectangle. A very common use case. You might have to find the circumference, the length of the rectangle. How can you do that? You can write your own implementation, or you can attach the implementation to the struct itself. You can attach a function to the struct. You can implement something on top of the struct, so that whenever someone defines a struct that of this rectangle type, they will automatically get access to this area method. I am defining a method. I am attaching that method on this struct. I am implementing some functionality on top of the struct. This is the rectangle struct. This is me implementing a function on top of the rectangle struct. The syntax of this might feel a little complicated. Specifically, if you look at the arguments, they look very weird. Function area, name of the function is area. The argument is very weird. At self, God knows what this is. It returns a number, and if you look at it, it's an implicit return, self.width into self.height. Can you already guess what this is doing over here? This function is being implemented, but it has some extra things over here. Self. self.width, self.height. Let's see what these are very soon. But given this does implement a function on top of a struct, whatever that means, this is how you can use that function. I have now defined a rectangle struct, and I can call rect.area on this struct so that I don't have to rewrite this logic. It is already written for me over here in a single place. Let's try to understand this a little bit more. Let's understand what the self variable is over here. All right, I've written some code over here, defined the struct called rectangle or a rect, has a width and a height over here, implemented the rectangle struct, added the first function here. If I want, I can add another function called, let's say perimeter, which again will have the self as the first argument. What self is, we're coming to very soon. Will again return I32. And what is the perimeter of a rectangle? It is 2 into self.width plus self.height, right? That is how you calculate the perimeter of a specific rectangle. It's the width plus height plus width plus height. I can print that over here as well if I want. Question is, what exactly is this self argument that you see over here? And the answer is, this is similar to this in a JS class. If you have ever created a JavaScript class, let me quickly show you what the syntax of that looks like. You have a class called rectangle, which has a constructor, if you remember, which takes, a width and a height as an input. And here you do a this dot width equal to width and this dot height equal to height. And then, you can define a function called area where you do return this dot width into this dot height. For the people who are comfortable with JavaScript, this is how you create a class in JavaScript. Java classes are also fairly similar. So this variable that you see, which is, the current object, this is how you define a class. How do you create a variable of the class? You do something like this: const rect1 equal to new rectangle with the width and the height. That's how you create a new variable or a new object of the class. And then you can call rect1 dot area to, let's say, print the area on the screen. That is how you would create a class in JavaScript. The constructor actually constructs the class whenever you call new rect. And then when you call dot area, it just calls this function which returns this thing over here, which is going to be the area of the rectangle. You log it on the screen. This variable over here, which is the current object, which has the height, which has the width, the corresponding width and the corresponding height of this rectangle. That is what this variable is over here. And similarly, in this implementation, think of this implementation block, which has the area function and the perimeter function. Similar as this code block right here, where we have defined an area function, which returns this dot width into this dot height. What are we returning here? Self dot width plus into self dot height over here. Over here, 2 into self dot width plus self dot height. This self variable is the current struct. Whatever struct you are trying to call dot area on, dot perimeter on, that specific struct comes in this @self variable. If you want to pass some extra argument over here, let's say, perimeter, I don't know, 1, which, let's say this number means something. So you can have that as the second argument here. Okay, num:(I32). So you can get access to the first argument from here as the second argument over here. You will still need to reserve the very first argument for the @self variable. That is how you create or attach functions to a struct in Rust. And you might have a question, 𝗥𝗲𝗃𝗀, can I define a function without @self? And the answer is you can define a function without @self. Let's say I've created a function called debug over here. Now I have 3 functions. The first function just takes @self as an input. The second function takes @self and also takes a number as an input. The third function takes nothing as the input. So the first 2 functions can be called on the rect1 object. They can be called on an instance of the struct. Rect1.area can be called without any arguments because there is no argument after the first argument. First argument You don't have to explicitly pass over here. You don't have to do this. It automatically comes over there. Same is true for rect.perimeter, but since it expects a second argument here, you have to pass that over here as the first argument. Again, you don't have to do rect1, comma 1 over here. You just have to pass the at self comes implicitly. This argument you have to pass explicitly. And lastly, the third thing, the debug function that we wrote. Can I call it? Can I call rect1.debug? And the answer is no. The Rust compiler will begin to complain. What does it say? It says no method named debug found for the struct rect in the current scope. It does not find a function. Okay, there is a function. There is. But since it doesn't have add self as the first argument, you cannot call it on the rectangle object. You can call it directly on the struct. You can call rect : debug, something like this. This is similar to a static function in Java or JavaScript. If you remember, if you've done classes in JavaScript, you can define static functions over here. Let's say I define a static function called debug. And this static function I can call directly on the class. I can call it on the class variable, not on an object. I'm not calling rect1.debug. I'm calling capital R rect.debug, which means this is a static function. What is a static function? A function that isn't attached to the object but directly to the class. And similarly over here, if you define a variable that doesn't have at self over here, that is similar to a static function, you directly call it on the class over here. Cool. Let's see if that works as expected or not. If I run this, you will see 3 lines of code should get printed. Area is 200, perimeter is 60, debug is 1. So the third one, as you can see, I did not call rect1.perimeter. I called rect : debug because this debug function exists not sort of as a static function. It is not attached to the rect1 argument over here. Hopefully that's clear. That's all I had for structs. I added some extra things from the on-site meetup as well. So hopefully, this is straightforward. I don't have to add that video over here. Next up, to quickly recap, this is how you define a struct. This is how you implement a function on top of the struct. This is how you define the struct or declare the struct. This is how you call a associated function of that specific struct. Structs are done with that. Let's move on to enums next. All right, let's get into enums next. Enums again are a language agnostic concept. They exist in TypeScript as well. What do enums let you do? Enums let you enumerate through various types of a value. Slightly jargony statement, but it basically means if you have something that can only have certain amount of types, for example, a direction can only be one of north, east, south, or west. Or let's say you have a shape which can only be either a circle or a square. Then in this case, you use enums. They let you enumerate through various types of an object. Let's say an object can be either the north direction or the east or the south or the west direction. You can totally, describe this as a string. For example, something like this, north. But the problem is if you use a string over here to describe the direction, then you can, have another direction like YouTube. Even though it doesn't make sense for YouTube to be a direction. When you know something can only be of a few types, for example, direction, it makes sense to use an enum than using a string. Let's see this a little more practically. Over here, I have defined a function called main, where I say let my direction equal to direction : north. What do I say? Okay, here is an enum called direction, and the my direction variable is not a string called north. It is not a string called north. Its type is not string. What is its type? Its type is this enum over here, which means it can only have one of 4 values. It can either be north or east or south or west. If you are creating a game, let's say in the Rust lang or generally the backend of a game, there are only 4 directions that the player can move, let's say. Then it makes sense for you to use an enum to describe one of these 4 directions. Can you still use a string? You can. You can still, say let my direction equal to north. But why is an enum better? There are multiple reasons. One, a string will take a lot of space. Enum can take much lesser space since it only has 4 variants. But more practically, or the better reason is, okay, your code is much more type safe. Your code is much more compile time safe. Okay, this variable can only take one of 4 values. We cannot put some random value in here like YouTube, like I said a while back. That is why you might want to use an enum. You define the enum variable over here. I don't know why I did this declaration, completely ignore this line of code. And then I, let's say, call a function called move around. And what does the move around function take as an input? It takes direction as an input. What is the type of the input over here? It is this direction enum. It is not a string, which means this can have only one of 4 values. Your function implementation can be much more safer now, considering the input can only have one of 4 values. Versus if this input was a string, then someone could have sent in a random string to this function. That is why you want to use enums. If something can only have 5 types, 3 types, 2 types, 10 types, then use an enum, restrict whoever is calling a function on that specific type to one of those 4 types. That is why you might want to use an enum. Let's quickly code an enum before we proceed. I'm going to define an enum called shape, not direction, shape. And let's say, there are 2 shapes that our current platform supports. Let's say we have a canvas-like platform where you can create rectangles and circles. So I'm going to create 2 variants of shapes that we currently support. That includes a rectangle and it includes a circle. Given these 2 shapes, I first define a variable called, let's say, my_shape, which is of type, let's say, the rectangle. And then I say, I'm going to define a function called, let's say, print_area, which is going to take what as an input? It will take a shape as an input and it will eventually print its area. Right now, we don't have any values associated with the rectangle variant or the circle variant, which is why right now it won't be able to do much. Let me just print, something like hi there over here. But eventually you will see how can we add values to various variants. And once we have added values to various variants, how can we use those values here to print, let's say, the area of a specific shape. What have we done to recap? I have created a function called print_area that takes an enum as an input. This enum can have 2 variants right now, either a rectangle or a square. And we can be sure whenever this function is being called, it is being called with one of these variants, either with a rectangle or with a square. I cannot call print_area of, square over here because square does not exist as a variant over here, but rectangle and circle do, which is why I can write something like this shape : rectangle, and the program, compiles correctly. Or, if I want to use this my_shape variable, I can use that as well. If I run this, you will see a bunch of warnings because we're not using this variable right now. But I see hi there printed on the screen because this function gets called with the right arguments. The type of the argument is correct, which is a shape. The problem with this is we have not yet attached any values to a rectangle. A rectangle should ideally have, a width and a height. A circle should ideally have a radius. I have not assigned both of these things to these variants. How can I do that? Can I have an enum with associated values? And the answer is yes. Rust lets you do that. We can have enums with associated values. As you can see, I've defined an enum over here which has 3 variants. It can either be a circle or a square or a rectangle. If it is a circle, it will have one input, which is floating point 64 bits. Basically means it can be a decimal and it can be a very long decimal because it uses 64 bits. Same thing for a square. A square can have a side which is f64. Rectangle can have 2 sides. That is how I have defined my enum. Each of these variants has some values associated with it. The circle has a radius, square has a side, rectangle has a width and a height. Now if I want, I can define the variants like this. I can't write shape : circle. I have to give it one value. If I'm defining a rectangle, I have to give it two values over here. Let's code this out really quickly. Given we have an enum which has two variants, we want that the rectangle can have two sides. So it will have two values associated with it, an f64 width and an f64 height. And the circle will have a radius associated with it, which is also f64. Now, if I go to my main function, how can I define a rectangle shape? I can define the rectangle shape similar to how I was using the enum until now, but I can pass in two values now, the width and the height of the rectangle. And if I want to create a function called calculate area, that will take, let's say, the shape as an input. I can call calculate area on the specific rect shape over here. The only problem is I see an error. It says these are probably not f64s. So if I add something like this, then we're good to go. It was interpreting them as integers. 1.0 makes it a floating point number. That's how you can, define enums with some values inside. Question is, how can I access its values, 𝗥𝗲𝗳𝗀𝗀? Can I do rect.0 or can I do rect of 0? How can I get the first value of this specific shape? And the answer is, by using something called pattern matching. This is something that's going to come next, but let me just quickly introduce it. If this function is actually supposed to do what it's supposed to do, calculate the area of a rectangle, how can you do that? It is going to take a shape as an input, which means it could take a rectangle as an input. It could also take a circle as an input. We don't know inside the function what exactly is coming. It could be a circle or it could be a rectangle. Calculate area can be called on either one of these two shapes, and hence we first need to check what is the type of this thing. Is it a rectangle? And if it is a rectangle, then we can destructure its values here and find the final return value as a into b. That is going to be the area of the rectangle. If this is a circle, then we can destructure its radius and return 3.14 into r from here. And we can store the final value in a variable called area, let's say. We can return area from this function. And I'll also change the return type of this function to be f64. That is how you can define a function called calculate area, which takes an enum as an input, and based on what variant of this enum is it a rectangle or is it a circle, it will print either the area like this, a into b, width into height, or it will print the area like this, which is 3.14 into radius. That's like the area of a circle, right? I think so, pi r square. Cool. Can you do other things? You can implicitly return the value directly like this as well. This also works. This basically means, okay, I'm going to return this from this specific function, which in the end returns either a into b or 3.14 into r. What is this syntax called? It's called the pattern matching syntax. Okay, given an enum that is going to have, let's say, 4 variants or 2 variants, based on what variant this specific variable currently is the shape a rectangle? If it is a rectangle, then you call a into b. If this is a circle, then you call 3.14 into r. Cool. That is what pattern matching is. If we go back to the slides here, what did we say? Enums let you enumerate over various variants of a specific type. For example, a shape can have 3 types: circle, square, and rectangle. This is how you define the circle. It takes one value as an input. This is how you define a square. This is how you define a rectangle. And if you want, you can also eventually pattern match on these various variants, irrespective of whether they have values or not. And based on that, run certain conditions or, do certain things based on which of these branches finally gets called. If it's a rectangle, then this branch of code will get called. If it is a circle, then this branch of code will get called. The circle has an associated radius over here. The square has an associated side. The rectangle has an associated width and a height. That's how enums let you enumerate with values. Let's move on to pattern matching. I've already discussed this. So what is pattern matching? Okay, given this calculate area function that takes a shape as an input, how can you implement its body? We already saw it. We already saw it over here where I implemented the body by pattern matching on various variants of this specific enum. The same thing is being discussed over here. Okay, the calculate area function will pattern match on the shape, and if it is a circle, the answer would be you can get the pi constant from the Rust library into radius into radius. If it is a square, then it will be side length into side length. If it is a rectangle, then it will be width into height. The match statement that is used over here is to match across an enum, and then these are the 3 branches based on what kind of this enum is. Cool. Hopefully that's straightforward. Returns the result implicitly. Hopefully the syntax is clear. Okay, I did not have to add a return statement over here. Did not have to put a semicolon over here. I implicitly returned this specific match statement, which in the end returned either this or this or this based on the variant of the enum. That is what pattern matching is. Next up, let's understand 2 important enums. This will probably give you more clarity on why do you need enums. There are some enums that you can define on your own. For example, over here we defined this the shape enum, which had 2 variants. There are some enums that Rust provides you by default, specifically the option and the result enum. Let's understand what these are, why they are useful. Let me give you a TLDR. They are used for, number 1, to have null points. I wouldn't call them null pointers, but like null values is probably a better way to say it. Null values in Rust. And number 2 for error handling in Rust. Error handling and null pointers in Rust are done via enums, specifically the options enum and the results enum. Let's go through what both of these are next. Let's get into the very first enum for today, the options enum. This is something that the Rust library provides you. And what does this let you do? It lets you return none or null or nil values from a function. If there is a function that can either return, let's say there's a function called sum that can either return a number, something like return 1, or it can return something like null, then what this function should return is an option. What does an option mean? It means it can either be some value, it can either be some value like 1, or it can be none value, it can be no value. If you were writing the same code in TypeScript, you would write it something like this. Okay, there is a function called sum which returns either a number or a null. And then in the function body, you would either return a number or a null. If there is ever a function that will return either a concrete value or null, which means this function wasn't able to do what it was supposed to do. 𝗥𝗲𝗳𝗀𝗀, can you give an example? Yes. A good example of this is, let's say there is a function called find underscore first underscore a, and it takes a string as an input. I repeat, the function is called find first a, which takes a string as an input and returns the index where the first a appears. For example, if the input to this is 𝗥𝗲𝗳𝗀𝗀, then the answer would be 1, because at the first index a appears. If the input to this is Raman, then the answer from this function should be 1, because at the first index a appears. But if all Punjabi names in my head, Preet. If the input is Preet, does a appear anywhere over here? It does not. So what should this return? You might say, 𝗥𝗲𝗳𝗀𝗀, if a is not found, then you can return -1. Sure, that is one way to do it. That is one way to return null values from a function, but it's better to formalize it. Okay, if there is a function that is not returning anything, if what you were supposed to find over here, which is the first a in a string, you were not able to find that, then simply rather than returning -1, return something better. You might say, 𝗥𝗲𝗳𝗀𝗀, then let's just return null. Hopefully Rust has a null value, but the answer is Rust does not have a null value. They explicitly chose, okay, we will not have nulls. I don't know if you've heard of this, but JavaScript says the $1 billion mistake was introducing nulls or undefined into the JavaScript language. And hence, even in Java, you might have seen a very similar thing. In Rust, you have the options enum, which lets you do what? The options enum lets you return either some value or none value. ignore what this enum looks like. I know it looks a little complicated right now. This is what the enum actually looks like. It might look very similar to what we've written until now. We wrote enum rectangle and it had 2 variants. These guys have also written something similar, enum option, but there is some extra syntax over here that's hard to digest. There is, some t variable over here, which I don't know what this is. So ignore its definition for now. We will eventually understand this when we learn about generics. For now, ignore this and this. Ignore the whole definition of an enum. Let's see how you can use the options enum. Let's define our own function called find first a, which returns you the very first a given a string. Let me quickly write this for you. What do we want to do? We want to define a function called find first a, which takes a string as an input and returns the very first character, the index of the character where a appears. How can you do that? You can enumerate through the string and find the very first character. For example, let answer equal to -1. I've written a function called find underscore first underscore a. It takes a string as an input, returns an 𝗟32 number for now. 𝗟32 number meaning a number which can be negative as well as positive. It is a signed number. It is not an unsigned number. It is not an unsigned number. It's a signed number. What does the logic do? You probably don't need this anymore. It iterates over all the characters of the string. If the input is 𝗥𝗲𝗳𝗏, then it will iterate over H, A, R, K, like that. It enumerates or iterates over all the characters. If it finds the a character, it returns that specific index. If it does not find that specific character ever in this for loop, it will finally return -1. This might feel like it's decent logic. You can always do this. Okay, let index equal to find first index for the string called Preet, and you can write if index equal to -1. Then you can print a not found, else you can print the other thing, which is going to be index is index, something like this. You might think this is decent logic. This is actually not too bad, but what is the problem? The return type is a little messed up. It's not very descriptive. It is a number which has a value of -1. How can the index of something be -1? You might say, 𝗥𝗲𝗳𝗏, if it is not present, it is -1. Sure. You can always argue this, this is better, but usually it's a good idea for you to be able to return a null type. Here I want this to either return some value or return a null value. I want my function to either return one of these two. It should be very descriptive. Here nothing came back, not -1. We'll have other use cases in the future that also might not return anything. Their return type might be a string. What will you return over there? An empty string. So it's just a good idea to formalize a null value in a language, but Rust does not have a null value. What does it have? It has options. So let's understand, how can I replace the return type from being a number that is -1 if the value is not found to something better? How can I add a nullable value over here? The answer is by returning the option of type 𝗟32. I repeat, I'm not returning 𝗟32 over here. I'm returning an option of the type 𝗟32. We'll very quickly dig into, what this option type is. What does this enum actually look like? Why does it have a T over here? We'll get to that. But before we get there, what have I done? I've changed the return type to be option of 𝗟32. And now if I do find it, if I do find the value, I return the sum variant. Sum means कि कुछ value वहाँ पे, there is some value over there. The sum variant of this option enum. What is option? Option is also an enum only. Just like we defined the rectangle, option is also an enum. It looks slightly weird. It has a T over here. But this enum, has two variants, the sum variant and the none variant. So whenever you want to return null or nil from a function, the better way to do it is not return -1 or an empty string, return an option of the actual return value, so that this index over here if you look at it, has an option of 𝗟32, which means it can either be an 𝗟32 number or it can be none, or no value at all. And over here, rather than adding an if-else check, what do you think we can do? We can pattern match on this enum. Here, pattern match on the enum. If it is some value, then just print if the index is that specific value. And if it is none variant, then you can print a not found. Is that digestible? What have I done? I've said the find first function is going to return the option of an 𝗟32, which can have two variants. This is an enum which can have two variants. What does option look like? It looks something like this. Enum option. It has a sum variant, which in our case is an 𝗟32 number. It has a none variant. This is what our option, this thing looks like. Enum looks like, because our option enum is for a 𝗟32 value. In fact, I can do this. Yeah, you should probably name this something else. I'll call it custom option. It is going to return a custom option. And over here, I'm going to write custom option : sum, this thing, custom option : none. This might have confused you a little bit more, but let me still try to take you through what I've done over here. I have defined my own custom option, which can have two variants. In the end, the option enum is also the same. It is defined somewhere else. If I go to this file, you'll see pub enum option. It just has a very weird syntax we haven't discussed until now, which is called the generic syntax. We will get to that later, which is why I've just trimmed down this option enum in my own implementation to have a none variant and to have a sum variant, which is of type 𝗟32. This is what I've done. I've just changed the option enum, the official option enum, to my own implementation so that it looks something like this. Just how I had defined a rectangle which had, shape which had two variants, a circle which had a number as an input and a rectangle which had a two numbers as an input. I have defined the option enum, which also has two variants. None means by kuch return nahi hua, this function returned nothing. Sum means it returned some value to you, which in our case is a number, but in the future it could be a string, it could be two numbers. We can define what the return type of our function is. Since our function right now is find the first index, it returns us an option which returns the 𝗟32 value. But in the future it could be, a string that our function returns. What if the function was find the first word? I repeat, what if the function was, I ask you to write a function find _ first _ word. It takes a string as an input. So in this case also, you have to return an option, because what if the string is empty? If the string is empty, then there is no first word. Then, you should return a null value in that case also. So find first word will also return an option, but this will return an option of a string, and our thing returned an option of a number. And just to make it even more simpler, I sort of defined our own enum called option, but let me not do that. Let me revert everything. Let me take you back through the original implementation that I had written, which looks something like this. What have I done? To recap, defined a function, returns option of type 𝗟32. It enumerates over all the characters. What does s.chars.enumerate do? It lets you iterate over all the characters. If we ever find the a character, we return not the index. We don't return this. We say, I'm going to return the sum variant with this value. It is similar to me returning a rectangle variant, shape : rectangle, with two numbers inside. That is what this sum of value does. Sum is an enum, and I'm passing in a value inside, so that the final function returns something that whoever called it can pattern match on. I repeat, this function returns an option so that whoever called this function can easily pattern match, acha, if something was found, then I do this. If nothing was found, then I do this. This is mostly to avoid, null pointer exceptions. What happens in languages like JavaScript is, this can either be 1 or null. So, you forget to do the null check. You forget to do something like this. If index equal to null, then do the first branch of code. And hence, null pointers or nulls or undefineds in JavaScript can cause a lot of problems, which is why it's formalized like this in the case of Rust. Hopefully, that was easy to digest. Maybe not, let me know. To recap, I've defined a find first function. So I find first a function which returns what? It returns an option of type i32. It returns a number only, but in some cases it will return the actual number. In some cases it will return none. We check if the character is found. If the character is found, then we return the sum variant of the enum. If nothing is found by the end of it, you keep iterating, you find nothing, then we return the none variant, which doesn't need to have a value associated with it. It is none. It doesn't need to have any value associated with it. Finally, we pattern match on the result. If something is found, then we print it. If nothing is found, then we print the letter A is not found in the string. Cool. That is what the option enum does. Next, we look at the result enum, which is very similar, but this one is used for error handling. What was option used for? It was used for null values in Rust. What is result used for? Result is used for error handling. What does it say? The result enum lets you return either OK or error value. The result enum is how you can do error handling in case of Rust. A lot of times a function will either return a value to you or the function will error out. Here I was trying to do something, but that did not happen. I want to throw an error. In case of JavaScript, it happens by throwing a custom error like this. You throw an error in case of JavaScript. In case of Rust, and again in Java, something similar happens, is that your function returns what? It does not return just a number. It returns an enum of type result. I repeat, your function does not return a number. It returns an enum of type result. And this result enum can have two values. I repeat, the result enum can have two variants. The first variant is the OK variant, which means that some value was found, the function worked correctly. The second variant is the error variant or the error variant, which means there was some error which also has a value inside, which is the actual custom error over here. This has the final value. This has the custom error. This variant says कि कुछ value return हुई, the function returned some value correctly. This variant says there was an error that was thrown during the execution of the function. Did not understand? कोई बात नहीं. Let's go through the slides and try to look at an example. What does it say? Write a function that reads the contents of the file. This is a perfect example of a function that may return an error. If this is your Rust code over here, or your .rs file, main.rs, you might try to read the contents of another file. Let's say file.txt, but maybe this file doesn't exist. Maybe this file doesn't exist on the operating system. Maybe your main.rs file does not have access to read through this file. And hence, whenever you try to call the function, read underscore file with the path to file.txt, what should this return? What should its return value be? It should be either the text, which is the actual text content, or it should be an error. ERROR. It should either be the text or the error. Why? Because what if the file is not there? If the file is not there, what will you do? Will you crash the program right there? No, your function can just return an error. Here, some error came. I'm throwing the error to you. I am bouncing back the error to you. This is called something in Java. I'm forgetting the name, bubbling the error or something like that, which looks something like this. Let's look at it more practically. This code that you see over here lets you read the contents of a file. The code that is written over here will let you read the contents of a file. I have a main function which does what? It calls fs : read to string. What does it call? It calls this function called read to string on this fs library or this fs. Most probably this is a struct. So on this fs struct over here, which returns you something. Question is, what does it return you? Will it return you text? What is the return type of this read to string function? A function that can either return some string or can error out. If the file doesn't exist, the function should error out. So does this always return you a string? अगर ये फाइल नहीं होगी तो क्या होगा? If this file is not there, will this function panic? Will this stop the program from executing? Or will it just return the error to whoever called it? The better thing to do is just return the error to whoever called it. Okay, you wanted me to read through this file, but this file doesn't exist on the operating system, so I'm just going to give you back an error. I'm not going to give you back a string, I will give you back an error. That is what this line of code does. If you notice the return type of this, let's write this code very soon, but if you will notice the return type of this, it will be of type result. It will be of type result, where result is an enum itself. This is also an enum. It is a custom defined enum. We did not write it like we wrote our rectangle enum, but this enum, already exists in Rust, and you use it to return errors from function. If tomorrow you also want to write a function that returns an error, the result enum is what you should use. Let's try to write this out quickly. Let me delete all the existing code. All right, I've written the code over here. It's less than 10 lines of code. What have I done? Number one, I've imported the read to string function, which comes from the Rust standard library. This is just, a bunch of extra functions that you can import at the top of your file. We'll come to this in the next section where we reach package management. But basically, there are a bunch of functions that you don't have access to by default. The read to string function isn't available globally. Just like, let's say U32 is something that is available globally, or, option is something that is available globally. Read to string is not, which is why you have to import it from a separate library, specifically the file system library over here. And what does this function return? What does it do to begin with? It is a function which takes the file path as an input and reads the contents of that file. As I said, this can be a dangerous task. What if the file does not exist? In this case, what should it return? You might say that it should return an empty string. But what if there is a file that has an empty string? You won't be able to tell, does the file does not exist? Or is there a file with some empty contents inside? You might say, -1 it should return. Problem remains the same, right? What if there is a file that has -1 contents in it? How can you clearly tell the result variable there is an error, bro? Some error came while reading the file. I'm going to return you not a string, but a result. What am I returning? I'm returning you a result, and then you can pattern match on the result. Result is an enum, pattern match on that enum. If the OK variant is what I returned you, means I'm giving you some data. Feel free to log that data. The file was present, the file was read correctly. If I return you the error variant, it means there was some error. Here are the details of the error. I will shove the details of the error in a value here as well. You can print this to the screen, either the specific error, or you can print your custom error. There was errors while reading the file. So what does the read to string function return you? If I hover over result, what does it say? It says result ka type is capital RESULT. This is the result enum that the Rust library has by default. I can actually take you through its definition, which it'll be a little hard to digest again because it uses generics. But if I remove the generics from here, it looks something like this. It has one variant called OK, which in our case is going to be a string. It is going to either return a string, and it will have an error variant, which doesn't matter. Let's say in our case, that is also a string. The result is an enum, which has two variants. What was rectangle, if you remember? Shape was a enum, which had two variants, a rectangle variant, which had two numbers as its values. And then, the circle variant, which had one variant as its value, or one value that it needed. This is how we defined our shape enum. This is how the Rust library defines the result enum. They say, if you are calling a function that may result in an error, then rather than returning the string, return a result of type string, so that I can either return you an OK variant, everything was fine, or return you an error variant, something went wrong. If you remember from the slides, what did I say? I said result can have two values, either an OK value or an error value. OK means everything was fine. Error means something went wrong. That is exactly what if you look at the result enum, it looks very similar. Of course, there are some more magic over here. If I command Z and show you the original thing, it uses generics. It has this very weird syntax, which don't worry about right now. But hopefully you understand, if there is a function that you call that may return an error, then the return type of it will most probably be null, be a result. You can define your own functions as well. What if I define my, oopsie daisy. I define my own function called read from file 𝗟𝗲𝗃. It's a custom function that does the same thing. It takes a file path as an input and it returns the contents of that file path. What will I do here? I can first read the contents. I can be like, okay, this is the result. Now, if I want, okay, I want to return -1 if the file is not found, then I can do something like this. I can pattern match on the result and I can be like, if everything was fine, then I'm going to return the data. If everything was not fine, I'm going to return, an empty string that says -1. Something like this. Let me change the return type of the function. So this is an ugly implementation of the read from file function. Why is this ugly? This is ugly because it will always return you a string. Read underscore file from 𝗟𝗲𝗃 a.txt. This is ugly because it will always return you a string. Even though sometimes the real read to string function will throw an error. If it throws an error, you should not return -1. You should return an error only. You should bubble up the error to the original main function. We are not doing that. Let me run this. When I run this, cargo run, you will see it prints nothing on the screen because I don't print result. So let me print it. It prints -1 on the screen. Do I have an a.txt file? I don't have an a.txt file in my folder. Then why is it printing -1? How will you tell yahan pe ki is there a file over here? What if there is a file that had -1 over here? Then how will you tell ki does the file exist or not? Either be result will be the same. It still prints -1. If there is no file, then also it prints -1. So you are not correctly telling whoever is calling the function what actually happened. If you always want to return primitive types, if you will always return primitive types, if you will be stuck in not using the result enum, what will happen is you will eat up a lot of errors. That is exactly what is happening here. Okay, there is an error that was thrown here, but you ate that error up. You did not bubble up the error to the main function. You thought ki nahi yaar, I will want to return a string. I will default to -1 as the string, or contents not found as the string. What is the problem here? Okay, what if there is a file that has the same contents inside? You will not be able to differentiate in this result variable. Is there a file that has this content or is there no file currently? Which is why this should return a result of type string. It should return a result. Now here, what is this syntax? We'll get to as I said soon enough. This is generic syntax. It basically tells कि this result enum में what should the OK variant return, which I want it to be a string, and what should the our variant return, which also I want it to be a string. That is what this string and this string over here means. But if you don't understand it, it is fine. We'll understand when we reach the generics part. I say my function will return a result now. If I find the correct thing, then I will return the OK variant of a result with the actual data of the file. If I don't find, if the files cannot be read, then I will return the error variant so that whoever is calling me, should be file path, so that whoever is calling me, which in this case is result, whatever, let's say answer, its return type is result of something, or it gets back a result, which could be an error, it could be the final thing. It can easily differentiate by pattern matching again over here on this answer variable. Okay, was an answer returned? Was the file contents read, or was there an error while reading the file contents? Cool. That is why you might want to use the result variant on your defined functions as well, where an error can be thrown rather than actually throwing the error. You can also panic over here if you want. You can stop the thread execution. You can be like, nahi yaar, file not read. And what will happen is, in this case, the program will stop executing right here. That is what happens in most languages, right? You throw an error, and if the error is not caught, the program stops to execute. If I run this, you will see, let me delete the a.txt file. Let me run it again. You will see it says thread main panicked at source/main.rs. The thread itself panicked, the program itself stopped executing. This is another way to do error handling, or throwing errors in a Rust program. But what is the most elegant way? The most elegant way is you return a result, or you return a result from the function that you know is going to fail. And you know, whoever is calling it can then decide what they have to do with this information. Whoever is calling it can decide that while the contents were being read, the data was read or there was an error. Based on that, you know, whoever called this function can decide what to do next. They can pattern match on the result. That's a better way to do error handling, or you know, the way error handling is done in Rust. Cool. Hopefully that was clear. Let's go back to the slides and see where we are. Let me quickly recap what happens in this function. You first read the contents of a file by calling this function over here. And what does that function do? It returns you a result. Once you have that result, you pattern match on that enum. It is just an enum. It's nothing too complicated. Both option and result are just enums that the Rust standard library has written, and you use them. We pattern match on the result. If everything is fine, then we print the right thing. If there was an error, then we print there was an error while reading the file. That was it for options and enums. We have discussed pattern matching. The next thing is package management, which thankfully is much simpler than everything we have discussed until now. You can add an external crate to your project by running cargo add crate name. 𝗥𝗲𝗳𝗏𝗀𝗀, what is a crate? Let's discuss this very soon, but high level. This is similar to npm packages in case of JavaScript. It's external packages that you can bring to your code base. For example, over here, I used an internal package. This read to string function comes from the Rust standard library. You still have to import it at the top, but you know, you can import it directly from the Rust library. You don't have to bring in an external module. But if you remember, initially I said there is this cargo.toml file, which has the dependencies section where you can add a bunch of external dependencies, a bunch of code that other people have written. You can bring that code into your code base. How can you do that? We'll discuss in the next section. All right, let's understand package management next. Usually when you have a project, let's say this is your, you know, main.rs file. A lot of times you want to write a lot of code, but that code is already written by other people. For example, if you want to print the current time in case of Rust, you can write all of the code to use the Rust primitives to write it. Or you can bring in an external dependency, an external library, or more technically what's called an external crate into your project. You bring this crate into your project, and then you can just use the functions that these people have written. You don't have to write all of that logic on your own. This is what is called external packages or external crates. You can bring these external crates to your project to make your life a little bit easier to reuse a lot of the code that other people have written. If you've ever been in the JavaScript ecosystem, you might have, you might have heard of this library called Express. Express is an external library. You can look at the documentation of Express. How can you use Express on this npm.js page? If you have a Node.js project, you can actually require the code from this Express library. You can bring this Express library to your code base, and you can require code from this Express library. You don't have to write a lot of code. You can depend on that external library. Similarly, in case of Rust, you can bring a bunch of external libraries to your project. Chrono is one such library that lets you do date and time for Rust. If you want to print the current time, the current date, you can use the external library, use high-level functions that they provide you, and just print the current time rather than writing all of that logic yourself. Let's see how that happens for Chrono. If you look at Chrono, the library looks something like this. The way to add that to your code base is by running cargo add chrono. So whatever is the library that you're adding, cargo add the name of the library will bring that library to your project. Let's do that first. Let me go to my code base here. Let me empty up the thing and let me run the command cargo add chrono. What will this do? This specific command that I just ran will bring the chrono external library to my project. If you look at cargo.toml now, you will see it has one dependency that I just added, which is chrono. So what does this command do? It brings an external module to your code base. Now you can use various functions on that external library. Just like I was using the read to string function, I can use various functions from this chrono library, whichever function I might need. For example, if you go back to the slides here, the function that we are using over here, or the struct that we're using over here, is this UTC struct. What does the UTC struct do? UTC is a time zone. Everyone follows that time zone. India is in UTC plus 5:30. If you understand this, if not, that's fine. this struct will most probably let me print my current time. This struct will most probably let me print the current UTC time, which is, the central time at wherever the sun is in the center, something like that. How do I do that? I first create this now variable, which is by calling this static method on the UTC struct. Most probably this is a struct. This is a static method on the struct, which returns you some struct only is my guess. We can check very soon when we write the code. And then when you write now dot format and a specific format in which you want the date month to be printed, that can, you'll finally get the current time printed in that specific format, the current UTC time. And similarly, when you call local : now, it will print the current local time, which in my case is going to be, India time. So let's see if that actually happens. Let me import chrono UTC or local, and let me try to print the current local time. Let now equal to local now. Current time is now. Why is this cool? This is cool because, all the logic to read the clock from my machine and figure out the current time has been written by these smart folks. I don't have to write this logic. I just bring their code base, their library, their crate into my code base, and I can just use it. I think, as I said, this will probably be a struct. Yes, this is a struct. It is a unit struct, which means it doesn't have, any values associated with it, but it is a struct. It has an implementation below it, and most probably, if I go to the now function, it is just going to be a public function which does not have @self over here, which means it is a static function. You can call it directly on the local struct over here. We've done this syntax before, so hopefully this is straightforward. Here we are calling a function which is associated directly with the struct, not with an object of the struct, not with an instance of the struct. We get this variable, we print it over here. Let me see if that does what it's supposed to. If I run cargo run, you will see it prints the current time is this, which is correct in the +5:30 time zone, which is, the India time zone. If I use the UTC struct, then, it would print the current time in the UTC time zone, which probably is, 5 hours, 30 minutes behind us. So if I run cargo run now, it gives me, some weird time, 8:50 AM, because India runs 5:30 hours ahead of UTC. Hopefully that's straightforward. How can you bring an external package, cargo, add the name of the project? How can you use that project? Start to import things from the project at the top of your file, and then you can finally start to use the functions from that external module. Why would you want to do this? So that, you don't have to write all of the code. You depend on external libraries to, write most of the code. You just stitch them together. That's what most end user applications are, right? Whenever you're creating a MERN stack application, you're depending on the Express module package. Similarly, when we create a backend application over here, you will see we will depend on some external crates that, will provide us some functions that we will use to finally write our application. Cool. We're done with the very first part over here, which is the easy bits of Rust that itself took 1.5 hours. I'm super surprised, and I think this is really slow. Let's get into some hard bits from part one. This should probably, hopefully not take more than 30 minutes, but I could be wrong. Then we will get to the actual gist for today. Let's understand memory management in Rust, mutability, heaps versus stacks, ownership, borrowing, and references. Let's get into that next. Alrighty, getting into some slightly advanced concepts. I wouldn't call them advanced. It's just Rust does things a little weird, which is why, these get a little confusing. So the earlier you understand these, the better. Again, we've covered this in a 4-hour video, so you can go there. I chose some very raunchy examples over there. I'm going to keep it simple here. We're going to understand memory management, mutability, heaps versus stacks, ownership, borrowing, and references. The last 3 are what are going to boggle your head a little. The first 3 are not too difficult, and if you're coming from a C++ background, you've probably heard of them before. Without any further ado, let's understand memory management in Rust. And before that, what exactly is memory? What do I mean when I say memory? When you buy a machine, if this is my Mac machine over here, what all components does it have? It has a CPU, it has a GPU, and it has something called the random access memory. You might have in school heard that this RAM is temporary storage or, temporary memory. And the SSD is the, hard drive, that is the actual persistent memory. So what exactly is this memory supposed to do? Have you ever guessed? Why do people optimize to get this to be, 64 GB or 128 GB? Why do people pay more and more money to increase the amount of RAM that they have? And the answer is because whenever you run a program, for example, when I'm running this Rust program by running cargo run on my machine, I'm taking up some space on this memory. This memory is really small compared to your hard drive. Hard drives are 1 TB, 2 TB. This memory is small because this is really expensive. Any chip over here, the smallest single byte over here is very expensive for you to buy and run, which is why this is only used for the programs that are currently executing on your machine. For example, if on my machine I have Google Chrome running, then Google Chrome is taking some memory over here. If I have VS Code running, VS Code is taking some memory over here. If I have some Node.js program running, the Node.js program is taking some memory over here. When the program executes, the variables of that specific, process are stored here in memory. That is what memory management generally means. Your laptop or your machine is eventually going to have thousands of, these softwares that are running. For example, I'm running OBS. I might be running Zoom. I might be running Edge, Chrome browser, Terminal, Premiere Pro. All of these are softwares. All of these are programs, processes that are running. They take up some space in my memory. For example, if I open Premiere Pro over here really quickly for you, you will notice that Premiere Pro has a bunch of files. Some of these files are loaded in memory right now. Some of these aren't, it's probably a bad example, but a better example probably is, Google Chrome, I'm on this specific tab. I see the tab written over here. I see all these contents. They're stored somewhere in memory. That is why I see them over here. So memory is a very scarce resource on a machine. Whenever you're running any Rust project, it is taking up some memory in your RAM. If your RAM is 16 GB, some, let's say 2 MB, 5 MB, 10 MB are taken by your Rust program. If your Rust program has a lot of memory, let's say it, defines a vector that has a length of 10 is per 10, then of course it will take much more memory over here. If it just defines two variables, then it will take much lesser memory. Cool. How much space do you think a program actually needs? If you run a Rust program, do you upfront tell memory, I need 10 GB of space. I need 1 GB amongst this 10 GB. Do you dynamically allocate or deallocate memory in this, RAM over here? And the answer is both. You do allocate some static memory. I need this much memory. You also allocate a bunch of dynamic memory. There's this concept that you might have heard of, which is called heaps and stacks, that we will be learning about very soon. But when a program runs, it does reserve some memory. I'm going to run my program. This much memory I need over here, some static memory, and it also reserves some. It doesn't reserve some dynamic memory. It can ask for more memory. I need more space. I need more space. I need more space. It can request the operating system for more space. If the operating system obliges, then you can, get more space for your program. If let's say your program, keeps pushing elements to an array, then you will need more space. So you keep asking the operating system for more space. If you look at this program, I define one variable i32, another variable i32, a third variable which is also i32, sum of these two. I print the sum. What do you think? How much memory roughly should this program take? Well, we need one i32 number, which means I need a 32-bit number over here. That will probably be stored over here. That is what 32 over here means, right? It means it's a 32-bit number, which means I need 32 bits of space in memory for this first variable. The second variable, how much will it take? It will also take 32 bits. The third variable, how much will it take? Since that is also the sum of two variables, it's a fresh variable, the third variable, that will also take 32 bits. So how much space does this program need? Roughly 96 bits. There is some extra space that comes with, these function calls. But ignoring that, you can say, we have defined three variables. This is the amount of memory we need over here. Why are we discussing this so much? Because Rust shines when it comes to dynamic memory allocation, and more specifically, it shines when it comes to memory management, which is why we're spending time here. We wouldn't even spend this time on a language like JavaScript or Python, but on a language like Rust, the whole, premise of Rust is, it lets you do create very safe programs. We'll come to what safety means, which is why we're, spending our time over here trying to understand how much memory does a program take. Here is a better example. What did I say? There is some static memory that you store. There is some dynamic memory that you store. Whenever you create a Rust program, similar logic applies to C++ as well. There are two sort of memories that you have, the stack and the heap. The stack is where you put static data, the data that you know iska size is going to be this much. If you can predict the size of a variable at compile time, I repeat, whenever I run cargo run on my machine, my .rs file first gets converted into a binary, and then this binary is what eventually runs on my machine. Okay, there are two steps to running any Rust program, any C++ program. The first step is compilation. The second step is actually running it. So if I can predict the size of something during compilation, I repeat, if this is a main.rs file, during compilation I can predict कि यार ये तो 32-bit ही होगा. This cannot be increase or decrease in size. Neither can this increase or decrease in size. These are static when it comes to the memory that they take. They don't take more than 32 bits. They will never take more than 32 bits. But can I say the same for a string? A string can initially be 𝗥𝗲𝗳𝗀𝗀𝗋, which means it only needs, let's say, some random number, 200 bytes. But eventually I could add more things over here. I could make it 𝗥𝗲𝗳𝗀𝗃. Then I would need 200 plus 100 equal to 300 bytes. I might increase the size of a variable. I might decrease the size of a variable. You might say, 𝗥𝗲𝗳𝗀, wo to I can do for the number as well. You might say, I can do that for the number as well, 𝗥𝗲𝗳𝗀𝗃. I can increase the value of this number. If this number is initially 1, I will, take this number a equal to 1, and then I will make it a equal to 100. Does that mean I had to take more space over here now that I have a bigger number? The answer is no. When you create a 32-bit number, when you write const or let a equal to u32, you are reserving 32 bits in memory for it. You are saying that 32 bits belong to me. Assume this is 32 bits that I have mentioned over here. Now, if you want to store 100, or very small number like 1, then most of the bits here will be 0. And the very last bit here, let's say, will be 1. If you want to store a bigger number here, let's say 1000, then maybe these all bits will be used. If you want to store 10⁵, then maybe these all bits will be used. If you want to use 10⁸, then maybe all of these bits will be used. So these bits are reserved. When you create a 32-bit number, you reserve 32 bits. If it is a small number, it will not use all the 32 bits. If it is a big number, it will use all the 32 bits. So the amount of space that a number takes does not change as time goes by, as your program actually runs. But the amount of space that a string takes does change as time goes by, which is why for a number, it will look something like this. And I'm going to introduce some more operating system jargon over here, which don't worry too much about. But whenever you define a function on this stack, the name itself is stack. Little bit of DSA people understand stack. On this stack, I push the main function ka what's called stack frame. The thing that you see over here is the frame that stores the main function ke variables. The main function has variable 1, variable 2, variable 3. All three of these are stored on the main function ka stack frame. If I had more functions and more function calls, we will see how the stack changes. But for this very simple program, this is what memory would actually look like. You would have a single stack frame for the main function. You will have 3 variables that you've put over here. And when the program executes, this is the amount of memory that you're taking. That's 32 plus 32 plus 32, 96. When the program executes and ends, then this memory is eventually freed. That is how you would describe the memory of this program. But what do you think happens here? I now have a main function which defines 3 variables, but the third variable comes by calling another function called find_sum. Calls another function find_sum, which takes 2 inputs a and b, which are both numbers, defines a third number, answer, and then returns the answer from here. How do you think memory changes over here? Initially, when the main function is called, the main function is what gets put onto the stack. The very first stack frame is of the main function. And how much space does it take? It takes 96 bits of space because we want to define 3 numbers here eventually. Then the first variable gets stored, let's say over here. The second variable gets stored, let's say over here. The third variable, before it is stored, what happens? This function gets called. And what did I say? When you call more functions, they get pushed onto the stack. We push this function call onto the stack. We create a new stack frame for the find_sum function call. And how much memory does this guy need? it has a variable A it needs to store, it has a variable B it needs to store, it has a variable answer it needs to store. So memory would look something like this. After this function is actually called, you would have another stack frame which would have these 3 variables. It would do its thing over here, add those numbers, delete those numbers, multiply those numbers. And then eventually after this line of code runs and the function gets returned, the stack frame gets popped off the stack. After the function finishes to execute, this memory gets freed. You don't need the A, B and answer variable that were here anymore. This function was called, this function completed its execution, it can be popped off the stack frame. And now you're back to square one. You're back in this function. You have this memory for it. You have 96 bits of memory that your program is using right now. How much was your program using here? 96 into 2. It needed 96 bits over here, 96 bits over here. How much does it need here? Just 96 bits. You finally print the thing, you're good to go. Program exits, this gets popped off as well. Your memory is freed. That is how memory gets allocated for simple data structures. For data structures like numbers, memory management is something you don't have to worry about. Define your variables, use your variables, does not matter. Rust, whenever you're writing Rust code, you will not feel any different from JavaScript, Python or Java until you are writing things like these numbers. When you're dealing with non-dynamic variables, variables that don't change at runtime, whose size cannot change. The size of this number will never change. It will be 32 bits always during the execution of this function, versus that is not true for strings. So let's understand. Okay, until now we have only stored things on the stack. Let's try to store things on the heap next. When do we store data on the heap? And why is this so difficult, weird? When you're writing Rust code, as soon as you start to store code over here or store data over here, why do things get complicated? What is the difference between heap and stack? Let's understand that next. In the slides, this might be a little flipped. In the slides, I think I wrote stack over here, heap over here. So I've just corrected that over here. These are all the properties of the heap. These are all the properties of the stack. The heap is dynamically allocated at runtime. What does that mean? Okay, whenever you put memory over here, it comes in dynamically. You put a string here dynamically when the code is running. And then let's say you add something to the string, you dynamically add more things in memory over here in the heap. Then you delete something from the string, then this area gets removed. So you dynamically allocate data on the heap as your program executes, versus here you saw here whenever a function runs, we statically say 96 bits are stored over here. Another function ran, 96 bits are stored over here, so on and so forth. Dynamic allocated at runtime, static allocated at compile time. Basically means whenever you are compiling your code, the Rust compiler knows कि यार ये जो main function है, this main function needs 96 bits. This one needs 96 bits. Versus it cannot predict when you're writing strings what the size of string needs to be and how much data it needs to reserve over here. Heap is much larger in size. Strings are much larger. You can have a very long name, versus numbers are just 32 bits and smaller in size. This is one of the reasons that heap is dynamically allocated, because when you have a lot of data, you cannot store it on the stack. You'll run out of memory. Versus heap, you have you can ask the operating system for as much memory as you want. So large data usually stored on the heap, small data stored on the stack. Slower due to dynamic allocation and deallocation. This means, what does dynamic allocation and deallocation mean? Okay, when your program is executing, when you reach this line of code, you dynamically ask, give me more space here. Someone pushed sing to the last name variable. Initially the variable was just 𝗥𝗲𝗄𝗏, but sing got pushed to the end of the string. So you need more space over here. Hence, it takes more time for you to ask the operating system for more space, more memory, and hence storing data on the heap is slower, storing data on the stack is faster. Used for dynamic data or large data, things like vectors, hash maps, or strings. Used for small data, fixed size variables, and function call information. Usually used for things like numbers, booleans, that whose size is fixed. Used for things like strings, vectors, hash maps, whose size you cannot predict until the program actually runs. Until the program runs, you don't know how much data you will shove into a string, a vector, or a hash map. So you cannot judge how much memory you need over here at compile time. Versus anytime you're writing numbers, it will only take 32 bits. So you can predict the size of every stack frame upfront. That is the difference between heap and a stack. The things that are usually stored on the stack are numbers, booleans, fixed size arrays that are not going to change in size, structs, structs that don't, have a string as the type. If they have a string as the type, then of course the underlying string will again be stored on the heap. Let's not go there. A struct that looks like this, which has just numbers or just primitives, will also be stored on the stack. And references, which we'll come to what these are very soon. Stored on the heap: strings, vectors, hash maps, large arrays, and structs that cannot fill in the stack. So the first three are things that dynamically change as your program runs. As your program runs, your logic might change a variable, let's say where name or whatever, let name. It starts with 𝗥𝗲𝗳𝗏 and then it gets changed to 𝗥𝗲𝗳𝗏. Then it gets changed to 𝗥𝗲𝗳𝗏. Then let's say sing gets removed, 𝗥𝗲𝗳𝗏. Its value changes as time goes by. So, strings, vectors, and hash maps are data structures like this. 𝗥𝗲𝗳𝗏, what are vectors and hash maps? We'll discuss in the advanced part today. But strings, hopefully you understand their size changes, which is why they're stored on the heap. Large arrays, there are some, as I said, the amount of data that you have on the stack is limited. So if you have some data that is very big in size, even if it can be stored on the stack, it is usually stored on the heap. Cool. Let's understand how would memory management happen over here. What would the stack and the heap look like if you now use a string? I'm not using a number, I'm using a string. Let's see how this hello, all of this data is stored. Is it stored here or is it stored here? If it is stored here, is there something corresponding that is stored here as well? Let's see. When you define the string, you store this string variable, this name variable on the stack, but this doesn't hold all of this value. Ye jo hello value hai, all of the contents of the string are not put on the stack because you cannot predict how long the string would be eventually. Right now it is 5 letters, it is fine, you can predict. But as your program executes, if you have, a for loop over here, then you don't know what this for loop will do. It might send out a network request. God knows what response comes from there. You can't upfront predict the size of the string will become smaller or bigger. So you cannot store this string, the final contents of the string over here. You can try, but what will happen is if this becomes really long, eventually you'll shove out of this stack. You cannot. The size of every stack frame is fixed and defined upfront. So this actual content is stored on the heap. But what is stored on the stack? A reference to this specific pointer, an address of this specific pointer. If you have a 32-bit machine, then you can find the address of this specific H, the first H, the first letter where you have stored something. You can store this address in just 32 bits. What is actually stored over here on the stack is the address of this specific thing. And something that points to this H, and then after H, E comes, L comes, L comes, and O comes. You can find the rest of the content on the heap. What is stored on the stack? The actual variable. Why do you do this? Because you don't know if this becomes hello world in the future. If it does become hello world, you can ask for more dynamic data on the heap. What did we say when we asked about the difference between heaps and a stack? We said dynamically allocated at runtime. The heap can be allocated at runtime, which means if you change the length of this variable, hello becomes hello world, you can dynamically ask for more memory on the heap. You cannot do that on the stack. Cool. That is how you store strings, even arrays and vectors. Not arrays and vectors are also stored here. Fixed size arrays, an array that whose size you won't change during runtime, they can be stored here. But everything else, hash maps, vectors, an array of characters, which is effectively a string, is always stored on the heap. Anything that changes during runtime is what's stored on the heap, but you always have a pointer to that from the stack. So what does the stack hold? It holds this variable. What does the heap hold? It holds this actual content. The content goes here, the variable goes over here. Cool. Why are strings stored on the heap? Because they are large and their size can change at runtime, and the size of the stack frame needs to be fixed. First reason you can actually ignore. The second is the bigger reason. Okay, their size can change at runtime. You don't know if a string, becomes longer or shorter, which is why, it needs to be stored in a place where you can ask for dynamic memory. You cannot do that on the stack. You can do that on the heap, which is why it is stored on the heap. Do we understand memory management, heap versus stack? We haven't really covered memory management. We've just understood memory. What is memory? And then we've understood the difference between heap and the stack. Next up, we're going to understand mutability, which we already have, which is a very simple concept. So I'm not going to spend too much time here. Basically, whenever you define a variable, for example, let name equal to string : from hello. I've defined this string. If I try to add something to the end of the string, let's say the string was originally hello, I tried to add world to the end of it. This code will begin to complain. It will give you an error. Why? Because all variables in Rust by default are immutable. What does immutable mean? It means you cannot change their value. But if you want to make them mutable, you can add the mute keyword over here, right? When you define the variable, add the mute keyword, that will make it mutable. And now if you have hello as the original world, you can push a string to it like world. Now you have a longer string. You might ask, 𝗥𝗲𝗳𝗀𝗿𝗶𝗀, why is this stored on the heap? You can clearly at compile time check that hello is the first word, world is the second word. It would need, let's say, 200 bytes on the stack. Why are we not storing this string on the stack? Because you don't know कि इसके बाद if a for loop comes, the compiler cannot just be like, अच्छा, over here, so I can almost say that the string is constant. You can actually say that. You can say, the string will eventually hold this contents, hello, world. The compiler can sort of, let's say, infer that. So you might think, 𝗥𝗲𝗳𝗀𝗃, why don't we store this on the stack? Because you can have conditional logic in a compiler, but Rust doesn't. It says, string banai hai. We know string can be highly dynamic in nature. Just because over here you are not adding random things to it, removing random things from it, doesn't mean it won't happen eventually in a for loop, let's say. And hence the Rust compiler always stores strings on the heap. And irrespective of if this is very simple logic, the compiler isn't able to infer, the size is going to be, let's say, 200 bits and store it on the heap. It'll always store it on the stack. Cool. That covers mutability. What do we learn in mutability? If you define a variable, it needs to be mutable if you want to change its value. That is true for strings as well as numbers. Let me quickly code this out and show you if you'd like to, see this in action. If I define a variable like a simple number also, let a equal to 1, and I'm trying to change its value. As you can already see, there is a red squiggly up there on the line in which I try to change its value. What does it say? Cannot mutate immutable variable a. Every variable is immutable by default. If you want to make it mutable, if you want to allow changing its value, you make it mutable like this. Cool. Hopefully that's clear. That's it. That's all we had for mutability. Next up is when we get into some slightly more hard concepts. Ownership, borrowing, references. One more thing, I think. Ownership, moving, borrowing, and references. Our longer video, 4-hour video, covers this with some very weird examples. You can go there. I'm going to cover it here fairly simply. What are these 4 things, and why do they become important in the context of Rust? These are also only Rust specific things. Everything we saw until now is, you'll see it in other languages. You'll see package management in other languages. You will see ID setup in other languages. You will understand how to initialize a project, functions, structs exist in C++, enums exist in JavaScript, options and result exist in Java, pattern matching is again Rust specific, package management exists everywhere. These 3 things, or more specifically, these 4 things are highly Rust specific. So you need to understand them quick if you want to get into this language. So let's understand what is ownership, moving, borrowing, and references next. All right. Why are we learning these 4 concepts? Because Rust does memory management a certain way. There are high level 3 ways languages do memory management. It is number 1, by using a garbage collector. This basically means, firstly, what does memory management means? It means cleaning things up from the heap. Whenever you define a variable, whenever you define a variable like hello on the heap, you allocate this memory. Deallocating that memory, removing that from the memory whenever this name variable goes out of scope, is high level what we mean when we say memory management right now. When we say memory management, we mean when you are allocating data on the heap, where all are you putting data? When that variable goes out of scope, are you removing data from that specific spot or not? That is what it means when I say allocating and deallocating memory, or memory management right now. And as the name suggests over here in the first section, garbage collector, which means whatever things are no longer needed on the heap, removing them from there. That is the first way to do memory management. A lot of languages do this. This is why you don't have to worry about memory management in Java or JavaScript, because they have the concept of a garbage collector. They have something running in the background that keeps on checking, okay, this is the heap. What all data over here is not needed anymore. It removes that data from the heap. Usually written by smart people, usually no dangling pointers or memory issues. You can't do manual memory management, and examples are Java and JavaScript. Let's go over all of these topics really quickly, all of these points. Written by smart people, the garbage collector that we're talking about is usually written by really smart people, because any optimization you can do there will make the programming language really fast, or relatively fast. So memory or garbage collectors are written by some really smart people. They usually don't run into memory issues. What is a memory issue? You might have heard of this thing called a dangling pointer. If not, can you guess what a dangling pointer is? If I have some variable on the stack which points to some memory on the heap where no data exists, that is a pointer that is dangling. It is pointing to a random variable over here on the heap, which is why it's a dangling pointer. This is one of many memory issues that you might run into. You might have heard of oopsie daisy. You might have heard of what do you call it? Buffer overflows. You might have heard of buffer overflows. You might have heard of double free errors if you've heard of them. These are like various like memory issues that happen that don't happen in Rust, or will not happen in Rust 99.9% of the time because of concepts like these. Can they happen in this specific set of languages, 𝗟𝗶𝗸𝗀? The answer is no here also, because as I said, some really smart people have written the garbage collectors. So usually no dangling pointers or memory issues. You can't do manual memory management. 𝗟𝗶𝗸𝗀, what is manual memory management? Putting things over here, asking for some memory on the heap, asking to increase the memory on the heap, allocating memory, deallocating memory. You can't do that. These languages are one level up. That is why they say Rust is a lower level language. C is a lower level language, because you can access the memory, you can shove bytes in there. You can't really do that in JavaScript. Most applications don't require you to have extremely low level language, which is why most programs are written in JavaScript. But Rust, provides you that only. C, C++, Rust let you do manual memory management. So first is garbage collector. We're not learning that. Manual memory management. What is this? Okay, you allocate and deallocate memory yourself. The developer writes the logic to put data in here and remove data from here, read data from here. It can lead to dangling pointers and memory issues. The biggest problem with the second way to do memory management is you, as the developer, get power to allocate memory and deallocate memory on the heap. But developers are dumb, and you might write wrong code that has a pointer to a null reference, has a null pointer that tries to free some memory that you took twice, a double free error. So these are common errors, common memory issues that come with a C or a C++ program, which is why Rust solves it a third way. What is the problem with doing memory management the way C does? Manual memory management. We will see this example very soon. That is why this is marked in red over here. I'll show you an example in the next slide where you will clearly see there is not a dangling reference. We basically forget to deallocate memory. You'll see in the next slide a very common memory issue that will happen if you're ever writing C++ code as a beginner. But you can't do the same in Rust. Rust will force you to avoid those errors. I repeat, think of Rust as, the people who wrote Rust said, C is a great language, but developers are dumb. So we are going to force developers to write code a certain way so that they cannot land into a situation where they run into memory issues. I should write that down. Wow, that's quite a statement. Rust, you get the idea. I'll probably just put it on the screen. Rust was written by developers that said C is great. You do need sort of manual memory management. That is not bad. But since developers are dumb, we are going to force developers to write code a certain way so they don't run into memory issues. Let's see this with an example. Let's see how does C do it? Why is there an error? How does Rust do it? And why is it better? When it comes to memory management, why does it lead to less memory issues? This C++ code that you see on the right has a memory leak. What do I mean by a memory leak? I mean, it has a function over here called create string, and whenever this specific program will be called, first we will put main on the stack, then we will put the other function on the stack, and we will manually allocate memory. What are we doing inside this function? If you look at it, I am manually allocating memory over here. I am creating a new array with 30 bits, I would assume, I could be wrong, or probably 30 bytes. I am probably allocating 30 bytes on the stack. I am dynamically allocating memory here on the stack. I'm taking 30 bytes on the stack to store my string over there. Even in case of C++, if you want to create or put dynamic data like a string or a vector or a C++ program, it will be, you will ask the compiler will ask the OS for some extra space on the heap. You will store the data over there. You print the string, but you forget to deallocate memory. If you look at it, I have commented this line of code that should have been there. What does this line of code do? This line of code would have removed this from the heap. I did not remove this from the heap, which is why, what is this? This is a memory leak. Our program will execute, and finally we will be returned to the main function. This will get removed from the stack. The second frame will get removed from the stack, but we will still have memory over here. We will still have memory allocated, which is why this is a memory leak. And developers can write this code from time to time. You do write this code. There is this very common pattern which you can read about, RAII pattern, which is sort of what Rust ends up doing under the hood. I'm not going there, but you should read about it if you want to read something extra. But C or C++ try to solve this problem by introducing the RAII pattern, which would sort of force the developer to clean up memory. But again, this isn't something you can force in C++. You can just hope that the developers follow the RAII, resource allocation something, I forgot the name, pattern to clean up memory from correctly. That is not happening in this code. You write very basic C code over here, 25 lines of code. You leave out a very basic memory leak. Okay, when you defined a function and you allocated some memory over there, you should be deallocating that memory over here, right? You are not returning this stir to the original function. This stir will no longer be valid. It goes out of scope. So why are we storing some data on the heap over here for this stir? When we know it has gone out of scope, it cannot be used in the main function. When the scope of this function ends, when the scope of this stir variable ends, this data should be cleaned up so that there is no memory leak. Does not happen in C++ unless you manually delete the data, you manually deallocate the data. This is a very common example of a memory leak. What did we say happens in C++? Okay, can lead to a bunch of memory issues because you allocate and deallocate memory yourself. The developer does that yourself. That is exactly what I'm doing here. Since I forget to deallocate memory, I run into a memory issue. C++ code has a memory issue. When you run this main code, you call the create string function. This is what the stack and the heap looks like. I've not written the stack correctly here, but you get the idea. As soon as I create some new data and try to copy it over the heap has this, hello from heap memory leak variable stored over here. All of this string, all of this data, all of these characters are stored on the heap over here. And then finally, when I come back to the main function, the data is still alive on the heap, even though there is no references to the string. There is no variable on the stack that is pointing here. When you come back here, there is no variable called str over here. There is nothing pointing to this data, but you haven't cleaned up that data, and hence this is a memory leak. Now let's get to the Rust way of doing memory management, which will take this problem away. As I said, it will force developers to write code a certain way so that they cannot run into this issue. And whenever a variable goes out of scope, it will automatically be deallocated. You don't have to manually deallocate it. What is the third way to do memory management? First way is garbage collection. Second way is manual. Third way is the Rust way. Rust has its own ownership model for memory management. It makes it extremely safe to memory errors. Errors like these that you were able to do as a developer in C, you can't do unless you're writing unsafe Rust. You cannot do these errors. The compilation itself will fail. The compiler will tell you, okay, you are trying to do something which may lead to a memory issue, so I will not let you do it. Let's look at the Rust way. Do you think there is a memory leak in the code that you see on screen? It looks very similar to the C++ code we had written. There is a main function over here which calls a create string function. which defines a string and then prints it on screen. That's it. Do you think when this string gets allocated on the heap, does it get deallocated at this point or not? What would the memory flow look like for this application? Initially, main gets pushed onto the stack, then create string function gets called, then create string gets pushed onto the stack, where we have a 32-bit variable which points to this hello, 5 contiguous set of bytes in memory which have HELLO stored over there. What happens when this function ends? This will get popped off, but does this get cleared off the heap as well? The stack frame definitely gets popped off, but does the heap clean up itself? The answer is yes. Rust handles cleaning it up. Question is how? Does Rust have a garbage collector? How does Rust know that this is the right time for me to clean up the S variable? And the answer is by using something called ownership rules. Rust says, okay, I'm going to follow these ownership rules for memory management. It says, keep this working through the example. This comes from the Rust book, which is why I know it's taken from there. So this first statement doesn't make too much sense. But what does it say? It says each value in Rust has an owner. Specifically, anything that you're storing on the heap over here has an owner. And what is the owner? It is this variable right here. They say, okay, there is something on the stack which will own this data on the heap. And whenever this variable goes out of scope, Rust will clean up the corresponding data on the heap as well. Rust says, okay, unlike C, where we expect the users to deallocate memory, the developer needs to deallocate memory. Rust says, okay, whenever you put something on the heap, I'm going to assign it an owner. And when this owner goes out of scope, it probably makes sense for this data to get removed as well. And hence, the ownership rule says, each value in Rust has an owner. There can only be one owner at a time. You cannot have multiple owners. This is what leads to double free errors. If you have two things that are trying to clear something on the stack, that leads to, double free errors, which means you're trying to free the same address twice, which might have been taken by some other program. So every value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Whenever the owner goes out of scope, this is the owner of this data on the heap. The S is the owner of the value hello. Whenever S goes out of scope, which happens over here, what does going out of scope mean? Here, whatever braces it was inside, those braces have ended. Whenever this function ends, control reaches here, the function has ended, which means S goes out of scope. If S goes out of scope, it means you can clean up the data from the heap. So that is what ownership is in Rust. Ownership in Rust says, okay, whenever you have data you're storing on the heap, there will be one owner of that data. And whenever that owner goes out of scope, I will clean up the data on the heap as well. You can clearly see this goes away. This takes away the problem that the C++ code had. Our C++ code had a memory leak. This code will not have a memory leak. Why? Because as soon as S goes out of scope over here, the data gets cleaned from the heap. This is very similar to garbage collection only. Garbage collection and how Rust is doing the Rust way are very similar. Only when a garbage collector works in a language like JavaScript, it periodically from time to time figures out, nothing is pointing to this variable. S has gone out of scope. Let me clean this up. Versus in case of Rust, whenever S goes out of scope over here, Rust will clean up the data from the heap as well. So it's like a very mild difference. But the good thing is, since Rust doesn't need a garbage collector running in the background, constantly checking, is there some data that is leaking? Is there some data that is leaking? It is much faster than a language like JavaScript because it doesn't have a garbage collector that is interrupting, the control flow from time to time, figuring out what needs to be cleaned up and cleaning it up. In case of Rust, whenever a variable is going out of scope, we are cleaning its corresponding data from the heap. It's as simple as that. That is how Rust does memory management. Why is this cool? This is cool because the way ownership works, we will see this very soon. It's very hard for you to run into memory issues. Rust is preventing you from running into memory issues upfront. Let's see how. Let's understand the concept of moving a variable next, which is one of the reasons that, Rust is memory safe, and how does it, achieve memory safety in one more scenario. Let's look at that scenario. Let's look at the code that is written over here. We have a main function which calls a function called createString. Here, I first define the s1 variable. I define the string s1. Then I define another string s2 and I say s2 is equal to s1. What do you think happens over here? Can you guess? There are like various things that can happen when you say let s2 equal to s1. Does s1 get copied? Do you create a fresh variable? Something similar to this over here. Do you have another string created in memory? Maybe. Is this s2 pointing to the same thing? Do you sort of have a reference here, or does something else happens? Let's see. Let me tell you up front, this code doesn't even compile. If you look at it, there is a red squiggly over here. Whenever you try to assign a string to, let's say, a variable s1, and then you say let s2 equal to s1, if you try to use s1 after this, I repeat, after this line of code, if you try to use s1, it will give you an error. Let's look at what that error is, and that will probably give you a better idea of what I mean when I say moving a variable. Let's see this in action. I define a variable, a string, let a equal to and then I say let a2 equal to a1. Simply do this. Right now, if I print a2, no error appears. If I run this, everything is good. This is a normal program. But when I try to use a1, you will see a compilation error. What does it say? It says borrow of a moved value a1. It says you are trying to borrow a value. Now we'll get to what borrowing is and why does it say you're trying to borrow a value here. That's because the println macro, borrows the value. Don't worry about that. But what is the second part here? Borrow of moved value a1. What were we learning in this section? We were learning about moving. The second thing, we have understood ownership. We're understanding about moving. What does the code say? The code says, or the error says, you're trying to borrow a moved value. a1 gets moved over to a2. After you do this, let a2 equal to a1, you are not cloning the a1 string. You are not creating another variable here that looks similar. No. You can also do the same thing by doing a1.clone. If you do a1.clone, then it's a different thing. Then in memory, you have created a new variable. You have two different variables in memory, one a1, one a2. Then feel free to use a1, feel free to use a2. Nothing is wrong. In fact, when you will be writing Rust code for the first time, you will add clones everywhere. You will see an error like this. You will say let a2 equal to a1. You will try to use a1. It will give you an error. You will just clone it. You will move on. That is how a lot of times you write Rust code initially is just copy everything, over and over. But this is bad. Why do you want to store 𝗥𝗲𝗃 in two different places? You should just store it in one place in memory. If you try to do that, you see that a1 becomes invalid. Why does that happen? Can you guess? We learned about ownership before this. What did ownership say? It said only one owner at a time. It said if you have some value on the stack, which in this case is, if you have some value on the heap, it can only have one owner. Right now, a1 is the owner. When you do this, the owner gets moved. This string ka owner now becomes a2 and a1 becomes completely invalid. This string is now owned by a2. a1 is completely invalid. You cannot use a1 after this. Why? Because I kept on saying, right? Rust forces you to write code in a way that you cannot have memory issues. If Rust did not do this, it did not, have this concept that only one owner can be at a time of a specific value on the heap. Then what would happen is whenever a2 goes out of scope, you would try to remove the data from the heap. And a1 would still be pointing to that data. You would have a dangling pointer. Or if you try to free it again, whenever a1 goes out of scope, you will be freeing the same thing twice from memory. That will be a double free error. So as you can see that Rust makes it very hard to write code, which is exactly what is happening here. You would expect these two lines of code, or these 4 lines of code, to just run in any other language. If in any other language you write let string1 equal to 𝗥𝗲𝗃, let string2 equal to string1, and try to print string1 and string2. Some languages might, copy over the string, so you have two places in memory where 𝗥𝗲𝗳𝗀𝗀 is stored. Some might use a reference. Okay, both of them are pointing to the same memory. But what does Rust do? Rust invalidates the first variable. It says ये तो valid ही नहीं है. Why? Because it wants to follow a clear ownership rule. Okay, only one person will own the value. If at this line of code you think A1 needs to be moved over to A2, okay, you can move it. But A1 is no longer valid. I will not allow you to use A1 ever again, because if I allow you to use A1, then if you try to do something like this, okay, you define A2 over here. Okay, this code is valid. There's nothing invalid in this code. I just reduced the scope of the A2 variable. I said यार A2 को यहीं define करो between this scope. If Rust did not have strict ownership rules, if Rust did not say that this value can only be owned by one thing, if Rust did not make this variable invalid, what would happen? When you run this line of code, 𝗥𝗲𝗳𝗀𝗀 gets put on the heap. When you run this line of code, A2 becomes the owner of that specific value. Let's say there are multiple owners. A1 is also an owner. A2 is also an owner now. Whenever the scope ends, it will try to clear data from the heap, and over here you will be referencing a null pointer, a dangling pointer. That is why you don't want to, that is why you are forced to write code this way. That is why, the ownership rule sort of kicks you in the butt over here whenever you try to write this code, because Rust wants to be safe upfront. It says, we want memory to be extremely clean. We want to avoid all double free errors, all dangling pointers, and hence we have this ownership rule. If you want to oblige, if you do want to do this, Rust says, okay, bhai, I will give you a compilation error. If you try to run this, you'll see a compilation error. Fix it. Clone the string. Do something better. If you want to have two owners, okay, create two different places in memory where you store this data. I will not let you point two variables to the same thing. I will not let two variables point to the same variable. That is what the Rust ownership rule force. Why do they force it? For memory safety. To recap, if this is the heap and this is the stack, there is always a single variable that owns a value on the heap. If you try to assign S2 equal to S1, this variable becomes the owner and the first variable becomes invalid. It's almost like that variable isn't defined anymore. You cannot use that variable, so that whenever S2 goes out of scope now, then this memory can be cleaned, but only one owner at a time. Let's see this once more pictorically. What do you think happens when you do this? Do you think A happens or B happens? I have two options over here. When you write this code where you say let S1 equal to string.from hello, then to chalo this happens. Okay, S1 starts to point to something on the heap. This over here is the heap. This over here is the stack. Again, this over here is the stack. This over here is the heap. Do you think case 1 happens or case 2 happens? Case 1 says, here when you do let S2 equal to S1, we copy over the string. We have two separate places on the heap where we are storing the string. This one points to the first one. This one points to the second one. Does this happen? No, this does not happen. You don't by default clone the string. If you want, you can call a1.clone and then yes, this would happen. If you clone the original string, this would happen. But if you simply say let S2 equal to S1, then this though doesn't happen. Does this happen? Do both of them point to the same thing? The answer is no. Why? Because if this is the owner of this and this is the owner of this, then as soon as one of them goes out of scope, the ownership rules will clear this as well. The ownership rules say if the owner goes out of scope, value goes out of scope as well. And you will have a dangling pointer over here pointing to some data that has been deallocated. And hence, what is the right way to do this? What is the right way to visualize ownership? It is, okay, initially S1 was pointing here, that is fine. As soon as this line of code ran, then S2 is the owner of this guy. S1 is no longer valid. That is what this gray section over here means. Okay, S1 you cannot use after this. If you try to use it, the Rust compiler will begin to complain. That is what we mean when we say moving a variable. We are moving the S1 variable over to S2 over here. If you remember the error, it said borrow of a moved value. It is clearly telling you here S1 has been moved over to S2, so you cannot use it anymore. And this is one example of movement. Here is another example where exactly the same thing happens. Even though it doesn't look like it, the exact same thing happens. Let's say we had the create string function. Here I defined the string s1. And rather than doing let s2 equal to s1 over here, I've changed this line of code. I have not done let s2 equal to s1. I have called another function called print_str where I am passing s1. I am taking this s1, passing over here. This is equivalent to me doing let s2 equal to s1. Me passing s1 over to this s2 variable is the same as me moving this s1 variable to s2. I still cannot use this s1 variable anymore because it has been moved to this s2 variable. Let's see that in action. Let's try to code that. What I'm saying is, okay, let's say we have s1 equal to this in a main function and s2 equal to a1.clone, everything is fine. Or sorry, s1.clone, everything is fine. You have two different places in memory or two different hello variables, or sorry, 𝗥𝗲𝗳𝗀𝗀𝗀 variables, one in one place in memory, other in another place in memory. Now I say, let me define a function called do something that does something with a string. It takes a string as an input. Let's call that string s2 for now. And does nothing, just prints it. I've just defined a function right now. When I do this, does the Rust compiler begin to complain? It does. What does it say? It says s1 has been moved to s2. ये जो value है, this value is now owned by s2. s1 is invalid. The same thing happens if I don't do this. When I do this, do underscore something of s1. I'm not doing this. I'm not saying let s2 equal to s1. But I'm calling a function where I've defined another variable s2, which is pretty much doing the same thing. s2 is becoming equivalent to s1. So this s2 now owns that value. This variable that now exists in this function owns that value. s1 is again not valid. s1 is again invalid. If you try to use just s1 over here, s2 does not exist. If you try to use s1 over here, then it will again complain with the same error. Borrow of moved value s1. 𝗥𝗲𝗳𝗀𝗀𝗀, I did not move s1 to s2 over here. You did not in this line of code, but you did in this line of code. In this line of code, you said I take s2 as an input. You passed s1 string over there. So, it is the same as me doing something like this. Let s2 equal to s1. Passing something as an argument is the same as, taking this variable over here, s1, and putting it over here in a different variable called s2. So the same thing happens if I write this line of code, or if I take s2 as an input over here and pass s1. So it still gets moved over to another variable. And as you can guess, whenever this other variable goes out of scope, which is right here, the memory gets cleaned up. The ownership rule says whoever owns the actual data on the heap, which is यहाँ पे the owner of this data is s1. But after this line of code, the owner of this data becomes s2. At this line of code, that s2 variable goes out of scope. Over here, the data has already been cleaned, which is why it makes sense for s1 to throw an error at compilation. Here, this code is wrong. The data will get cleaned from the heap directly over here. Please don't try to use it over here. If I try to run this, you'll get a similar error. And this is sort of the, there you go. Gives you a way to fix it as well. But what does it say? It says borrow of moved value s1. It says you're trying to move s1 into this function. It will not work. And can you fix it? Yes, it's giving you one way to fix it, which is, just clone the string. It is also telling you the one unoptimal way to fix this, which is just clone it. Okay, ठीक है यार, this will have a copy of s1. It will not have the original variable. Then everything is fine. It will work. That is why I said, you will do this in Rust initially. You will see this error. You will look at the compilation help. You will just clone the string. You will do this a lot of times initially. Just keep cloning things, which is fine. But when you're writing very memory safe code, you don't want to take too much memory. Then of course you need to figure out how can you satisfy the ownership rules yet not clone the string. We'll get to how we do that very soon. But is this clear? Do we understand ownership rules? I know it's hard. It's probably the hardest thing to digest initially, which is moving variables and both into a function and into another variable. To recap, what does it say? This specific thing will fail if you try to take s1 and pass it to a function. s2 will take ownership of it, which means s1 is no longer valid. But you can do one more thing. What you can do is you can pass back ownership of that variable. So you can return s2 over here. Sorry about that, I wasn't recording. I was saying you can return s2 back over here, or sorry, a string back from this function. And over here you can be like return back s2, and you can say s1 equal to do underscore something of s1. Basically, you take this thing is stored on the heap. This 𝗥𝗲𝗳𝗀𝗃 thing is stored on the heap somewhere. Who is the initial owner of this? It is s1. On this line of code, the owner is s1. Then do underscore something gets called. Ownership gets moved to which guy? Ownership gets moved to s2. s2 is what owns this 𝗥𝗲𝗳𝗀 value over here. We return back s2 variable to s1 over here. So who becomes the owner of this value now? It becomes s1. If you return s2, the ownership gets moved back to this s1 variable. It doesn't work right now because s1 isn't mutable. But if I make s1 mutable, then I can pass ownership here, do underscore something, can borrow it for a while, and keep it. This isn't borrowing, this is moving only. I moved the ownership over here. Ownership gets moved over here. It does its thing with s2. It returns s2 back to the original implementation, and the s1 variable can store that value. You can finally print it. This is the same as doing this. If this feels complicated, then let me just remove this. What happens when I do this? Let mute s2 equal to this thing. Then s1 equal to this thing. Then let s2 equal to s1. Then s1 equal to s2. Who is the owner of the 𝗥𝗲𝗳𝗀 string over here? It is s1. Who is the owner on this line? It is s2. Who is the owner after this line? It is s1 again. So s1 is again valid after this line of code. S1 is again valid after this line of code. If I try to print s1, I have no compilation errors. But can I print s2? Is s2 valid after this line of code? The answer is no. s2 has been moved. The value of s2 has been moved to s1 again, which is why if I try to print s2, it says it is no longer valid, borrow of a moved value s2. So do we understand moving a value? There can be a single owner of a value. If you ever assign that value to a different value, then s2 has, in this case, s2 becomes the owner of the string, and then again s1 becomes the owner of the string. You keep on moving the ownership of the string. If you don't understand this, you should go to our original Rust bootcamp video where I cover this with a very weird example. Alrighty, moving on. We hopefully understand ownership. We hopefully understand moving. Next up, we need to understand borrowing and references. Let's get into them one by one. All right. Hopefully we understand ownership and borrowing. Ownership is any value that's on the heap is owned by someone. Whenever they move out of scope, the value gets removed from the heap as well. Moving is a lot of times when you define a variable equal to another variable, you move over the ownership of the underlying value to the new variable. Next up is borrowing and references. Let's see why do we need them and where they are useful. This code that you see on the right is ugly. You have to return the value back. The code that we wrote, you can look at this code, does the same thing, which is the main function calls create underscore string, which first has a variable called s1, which has the ownership of this hello value. Then it calls a print underscore str function. So the ownership gets moved to this s2 value. Then the ownership gets returned from this back to this s1 variable. That is how we have carried over the ownership of this s1 variable, or more specifically this hello value throughout. But why have we done that? Let's say we want to use s1 again. We want to call this function. After that, we want to reuse s1, which is why we had to move back the ownership. If we did not need to use s1 after this, then there is no need to return s2 here as well. s2 can exist independently on the heap. But this code is ugly, remembering to pass in a value, then returning back the value, then reassigning it to the original variable. What if there was an easier way to do it? And the answer is you can do it by using something called references and borrowing. We can pass in a reference to s1. s1 is borrowed by print underscore str. s1 is still owned by create underscore string, or more specifically the s1 variable. This is incorrect. This should say s1. What we're doing over here, what we're saying is, let me just start to code this. I think we can understand this a little bit better over here. This is how we had done the original implementation. Hopefully you understand the code that is written over here. The code says, define a mutable variable s1. s1 owns the value. What is the value? It is this 𝗥𝗲𝗳𝗀𝗃 string that exists on the heap. Who owns the value over here? When do underscore something gets called, then s2 owns the value. On this line of code, s2 owns the value. Then whenever you come back here, we reassign the value to s1. So s1 owns the value again. And then over here we print S1, everything is fine, compiler does not complain. On this line of code, S1 gets cleared. But what if you don't want to do this ugly logic of first making the string mutable, then reassigning the string? What if you want to retain ownership over here? How can you do that? How can you pass something else to a function so that you don't pass in the ownership? You just borrow or lend the variable. The variable gets lent over to the function. The function that wants it borrows the variable, does whatever it wants to do with it, and eventually the ownership remains with S1. If I change the code just a little bit where I say, okay, hey, do underscore something. I don't want to pass you S1. I don't want to pass you the ownership. S2 will not be an owner of this value. I want you to borrow S1. I'm giving you a reference to S1. You can use S1 freely, no problems over there. You don't have to return it to me either. I am still the owner of S1. Think of this S1 variable as a 𝗶 variable. I still own the value. I am allowing you to borrow it, do whatever you want to with it. And then eventually I will still be the owner. The value will only get cleared from the heap when this function ends. Isn't this syntax slightly cleaner than passing over ownership and then passing back ownership and then printing S1 over here? Looks like it. So these are what are called references, and the process, what you're passing over here is, this is what is called a string slice. We'll be getting to this in the advanced part, but think of this like, you're passing it an address or a pointer to the S1 variable, which you can use here. You can dereference. If you come from the C++ world, you can dereference S2 over here. Even if you don't understand dereferencing, it's fine. This macro automatically dereferences it. The point is, okay, I'm not passing in the S1 variable. I don't want to give away my girlfriend to you. You can borrow them for a while. This example is covered in a little more detail in the main video. It's like a bad way to put it, but you get the idea. Okay, borrow the variable, do whatever you want with it. You don't have to return it to me. I still own the thing. And I can still use it over here. Cool. Hopefully that's clear. What does borrowing mean? Whenever you pass a reference to S1, it means do underscore something has borrowed. This value hasn't moved to this function. This value isn't moved to the S2 variable. It has been borrowed by the S2 variable. You can still use it after it. The owner of S1 owner of this value remains S1 throughout. Over here, over here, over here, over here, over here. Every line of code pay, owner of this is S1. It is being borrowed by a few variables from time to time. The only difference, if you look at the code, is that you're passing in a reference to S1 over here, and then as the argument, you are not expecting a string, you are expecting a reference to the string. When you do not borrow, when you write code like this, yeah, there's another thing. I mean, we were using very complicated functions right now. You can also do this. If you remember our original example, let S2 equal to S1, what did we saw at this point? Okay, I was not able to print S1. It gave me an error. Why? Because S1 became invalid over here. But just like I was passing in a reference to a function, I can just define a variable here which is a reference to it. I can also, do a function call rather than doing this. I can do a function call and pass in S1, or I can say here let S2 equal to @S1. If I want to do something here with it, if I want to define two variables that both are sort of pointing to the same thing, but the owner remains single. There is a single owner of it, but S2 can point to it. Then I can do it directly in the main function. I can also define a separate function like we did. Then I print the value of S1 and S2. This is valid code. This is invalid code because here I move the value of 𝗥𝗲𝗄𝗏 over to S2. Here I just borrow the value. Owner still remains S1. Owner is still valid, which is why this line of code works. This much code does not work. Cool. Alrighty. Look at it. What code works over here? The code that works is when you define let S2 equal to @S1, because you are borrowing S1 in S2, owner is still valid. What code does not work? When you say let S2 equal to S1, S2 becomes the owner of this value. S1 becomes invalid, and hence you cannot print S1 over here. That's exactly the error that you see over here. Why is Rust forcing us to do so many things? Memory safety, right? If Rust can ensure there is a single owner at a time by forcing you to write code like this, कि यार मैं तो compile ही नहीं करूँगा. I will not compile the code if you try to use S1 over here. I will invalidate S1 because I don't want two owners at the same time. Yaar. If there are two owners of this hello value, then when will I know when to clear this? You might say, 𝗥𝗲𝗳𝗲𝗿𝗶, the compiler should be smart enough to know okay, if S1 has gone out of scope and S2 has gone out of scope, then it should clear the value from the heap. The answer is yes, but that is sort of what garbage collectors do. But we want to stay away from that complexity. We don't want the compiler to spend a lot of time figuring out how many references are there to something, when should I clean it up, which is why we don't want a garbage collector. We just force. Solana blockchain and Rust have a lot of parallels this way. They force you to write very difficult code so that the final thing can be very optimum. I repeat, slight detour for a minute. But whenever you write a Solana contract in the future, whenever you do a Solana RPC call, you will notice the way you have to, send data is sending a bunch of accounts upfront specifying signers. Some extra thing you have to do, which you don't have to do in Ethereum, because it makes the final process really fast. Whenever the miners are running your code, they can decide to parallelly run based on what inputs you provide. As the developer, this makes your life hell trying to figure out what inputs you have to give, but it makes Solana really fast. Similarly, as the developer, Rust makes your life hell. You can't do such a simple thing which every other language will provide you, but Rust will be like, no, I have ownership rules. You'll be for fighting the what's called ownership rules, fighting the borrow checker, trying to figure out where did I go wrong, what thing got borrowed, and why is this variable moved, why is this variable invalid. And the answer is the compiler is just saying upfront कि भाई, this is how I work. Ownership rules work a certain way. If you want this code to work, either clone the string or use references, that is fine, but don't point two owners to the same value. I will not let you. Cool. That is what borrowing is, what is happening on the right over here. Rather than doing let S2 equal to S1, I'm doing let S2 equal to at S1. Question is, how can you create a mutable reference? What if you want to borrow and mutate the value? You want to borrow the value and also change the value in there. Can you do that? The answer is yes. How can you do that? Pretty simple. Rather than passing at S1, you have to pass at mute of S1. Rather than expecting at S1, you expect at mute of S1. So if I go back to the code over here, let me revert this to the original functions that we had. If you want to change this S2 string right now, if you try to change it, S2 dot push underscore str hello, or 𝗥𝗲𝗳𝗲𝗿𝗶𝗀 sing, it will tell you okay, you're trying to cannot borrow S2 as mutable because it is behind an at reference and not behind a at mute reference. This needs to be a mutable reference. Whenever you're passing it, you need to pass in a mutable reference, which means the S1 variable needs to be mutable. If you change these three things, as you can see, compiler stops to complain. What have I changed? Number one, I made S1 mutable. Number two, whenever I was passing, I pass in a mutable reference now. Okay, you can borrow and make changes to it. It is fine. That is what is happening here. S2 dot push underscore str will be able to push to the string. If I print the string finally, it will be 𝗥𝗲𝗳𝗏 space sing that is printed over here. Let's see if that happens or not. If I run this, the thing that gets printed is 𝗥𝗲𝗳𝗏 space sing. All right, great. Over here also and over here also. That's how you take a mutable reference. And another set of ownership borrowing rules that Rust enforces on you is, at any given time, you can have either one mutable reference or any number of immutable references. I repeat, at any given time, you can have either one mutable reference or any number of immutable references. The Rust compiler says, okay, you are creating references left, right, and center. That is fine. You can do it. Let S2 equal to at S1. Let S3 equal to 𝗥𝗲𝗳𝗏𝗀 की service at S1. Both of these are immutable references to S1. And if I try to print all three of these, everything just works as expected and nothing out of the ordinary over here. No compilation errors. If I run this, I see the thing printed thrice. But if I make one of these, I repeat, if there is even one mutable reference, then I cannot have an immutable reference. If there is one thing that is changing the value on the heap, there shouldn't be another thing trying to read the value. That can also lead to memory issues. What if you're expecting some data to be there and immediately someone muted it, that data sort of changed. So to ensure memory safety, the Rust compiler says that multiple people can read from the same place in memory, that is fine. But if even one is trying to change data over there, if there is a mutable reference, then I will not allow other mutable or immutable references. I cannot have another mutable reference or another immutable reference. If there is one currently active mutable reference, what does it say? Can't borrow S1 as immutable because it is also borrowed as mutable. What is the compiler telling you? It is telling you that this does not follow this specific ownership rule. What was the rule? Okay, at any given time, you can have either one mutable reference or any number of immutable references. You can have multiple immutable references, that is fine. As soon as you introduce just one mutable reference, you cannot have other immutable references. The code will begin to complain. This is similar to if you might have seen in databases, if this is a database, there can be multiple reads at the same time. And whenever you try to write, you have a write lock, but not a read lock. Whenever you're trying to write from here, you lock the specific row in a database. Reads are still allowed on that row, but you don't allow another person to write on that row to ensure, two people aren't overwriting each other. Similarly here, if you are mutating it once, if you have one mutable reference, you cannot have another immutable reference or mutable reference. This is what the ownership rule says. Why does ownership rule do this, 𝗟𝗶𝗳𝗀𝗀? For memory safety. It will force you, I know you have to write extremely tough code. The Rust compiler says, yes, I'm forcing you to write code a certain way, but I will promise you, if you write code this way, somehow figure out how to make this work, then your final code will not have memory issues. It forces you to write code in a way. The ownership rules will give you so many compilation errors. Okay, by the end of it, the code that you have written after fixing all of these errors will not have any memory issues because it isn't allowing two mutable references. It isn't allowing two owners. It is making sure whenever the value that is owning the data gets moved out of scope, the data also gets removed from the heap. So it does all of these things to do very efficient memory management. And you as the developer don't have to worry about memory management. You do have to worry about fighting the borrow checker and making sure you're not doing anything weird and making sure the compilation succeeds. If your compilation succeeds, most probably the code that you've written will work. Cool. Alrighty. Okie dokie. That's all I had. Let me just take you through a visualization of this. I define a mutable variable over here called S1, and then I take a mutable reference in S2. Then I try to mutate it again. It'll throw an error. This line of code is enough to throw an error. What does it say? The error says second mutable borrow occurs over here. Cannot borrow S1 as mutable more than once at a time. If I try to borrow it as mutable over here as well as over here, the compiler will fail. I won't be able to compile my program. That covers all the jargon we need. Hopefully that was easy enough. We're done with part 1. Let's move on to part 2, where we're going to cover some, I would say these are simple enough. This is going to boggle your head a little. Traits are, I don't know why I marked them as red. They're probably orange. Multi-threading is also not too difficult. Macros, the thing that we're doing is probably not going to be too difficult. This we're probably going to skip, and lifetimes. This is probably the only hard bit after this. If you understand everything else, lifetimes is the only thing that are going to boggle your head. Everything else should be straightforward. With that, I will see you in part 2. All right, let's get into the advanced bit now. I wouldn't call it too advanced. Some of the things here are fairly simple. The things that are specifically mentioned in green are much simple, like very basic data structures. Only they're stored on the heap, which is why we're discussing them separately. Then we'll understand the difference between strings and slices. This is probably a good thing for you to know. Then generics, that's also not too difficult. Traits, fairly simple. I don't know why it's mentioned in the red. Multi-threading, macros, futures, async await, and lifetimes. Only this part I'm not sure of. Most probably this will be covered in a separate video. We will see by the end of it. Without any further ado, let's get into the very first section, which is on collections. What are collections? I'm sure you can already imagine /guess. Arrays, vectors, dynamically sizable vectors, HashMaps, things that dynamically increase and decrease in size, where you can store a lot of data together, is what is known as collections. A Rust standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but a collection can contain multiple values, just like an array. The data these collections point to is stored on the heap. Why? Because again, very similar to a string, this is dynamic data. It can increase and decrease in length. Hence, it should be stored on the heap and not on the stack. The very first one that we're discussing is vectors. All right, let's get into vectors next. Vectors are very similar to vectors in C++, basically a dynamic array that you can push elements to pop elements from. A vector allows you to store more than one value in a single data structure that puts all of the values next to each other in memory. Basically, whenever you are using a vector, it is similar to you creating a string. If this is the stack and this is the heap, if you have a string variable, the variable is stored on the stack over here, which points to some data on the heap. And similarly, if you have a collection, if you have a vector, you will have a variable over here which points to data on the heap, where you will have, let's say, multiple values 1, 2, 3, 4, 5, an array like this. It is just a vector or an array that can increase and decrease its size. You can add elements to it, remove elements from it, and hence it is stored where? It is stored on the heap and not on the stack. This is the syntax to create a vector and push some elements to it, print the final vector over here. The only weird thing that you might find is this syntax to print the vector. Let's really try to code it, understand how can you print various values, what is this extra thing. But other than that, I would assume the rest of it is fairly straightforward. Let vec equal to vec : new. This will initialize a new vector, and then let me push a few values to it to make it mutable. This is very similar to the code that was written in the slides. The only thing is, when I'm printing it, I'm writing double quotes just like we did until now. But unfortunately, vector, if you look at it, is a struct in itself. And if you remember, you can't really print structs automatically. You can print the value inside a struct, You can get the value at the 0th index and print that. But you can't print the vector as such unless they do something called implementing a debug trait. 𝗥𝗲𝗳𝗏𝗀𝗀, what is implementing a debug trait? We'll get to when we reach the traits section. But basically, from time to time, initially when you're going through Rust, you will try to print a statement like this. And if it doesn't work, if it gives you an error, add this : over here and hope that the thing that you're trying to print does implement the debug trait. If it doesn't, then of course this will fail as well. You'll have to figure out a different way to print the element by, let's say, iterating over the vector. But thankfully, this vector trait, whoever has written that, implements something called the debug trait. Basically, has an implementation block like this, where there is a function called debug, where it is defined how this specific vector should be printed, which probably means, printing 1 and then (2). But if you don't understand this, this is fine. This is just the way to print vectors for you for now. If you want to print the complete vector object, rather than writing print braces, you have to add a : in here. If I try to run it, you will see 1, 2 gets printed on the screen. This is a mutable vector, which is why I could push elements to it. If I make it immutable, then I won't be able to. Fairly simple stuff, nothing too out of the ordinary. The question is, how can you get values inside a vector? How can you index the first element, the second element, so on and so forth? And this is where, let's sort of solve this via assignments. The very first assignment is, can you write a function that takes a vector as an input and returns a vector with even values from it? It takes a vector as an input, returns another vector which has only the even values. So for example, over here I have a vector that has two values. It has 1, 2. And we want to create a function even underscore filter, let's say, that takes a vector as the input and returns another vector with just the even values. So how can you do it? We need to understand, number one, how to iterate through a vector, and number two, how to, create a fresh vector and push elements in there. I guess that's probably the easy bit. Approach number one that I'm taking, I'm defining a new vector over here. And I'm iterating over the original vector, whatever I got as an input in here. Notice, there's already some errors over here. It is already telling you here this syntax is incorrect. It says add missing generic argument. We will get to this when we reach generics. But for now, you have to know that you can't write vec over here. You have to write vec of 𝗏32. You basically have to tell what kind of a vector is it. Is it a vector of numbers? Is it a vector of strings? And the way to do that is by specifying a generic argument. What is a generic argument? We will be getting to very soon. Vector of 𝗏32, new vector is vector : new. For val in vec, if val mod 2 is 0, then you do a new underscore vec dot push val, then you return new underscore vec. Make sure it is mutable. Change the return type of the function to be vec 𝗏32. Hopefully that is straightforward. I've written a function which takes a vector as an input. The type of the vector can be a little overwhelming right now. Vec of 𝗏32. It's basically a vector of type number or of type 𝗏32, and it returns another vector of type 𝗏32. I define a new variable here called new underscore vector. I initialize it to an empty vector. I iterate over the original vector. This is one of many ways to iterate over a vector. We'll be coming to more ways very soon when we reach the iterators section. But one of the simplest thing you can do if you want to iterate over a vector is for val in the original vector. This will let you iterate over all the values. And over here you check, is the current value modulo 2 equal to 0? Is this an even value? If it is, you push it to the new vec array. You return this new vec array from here. And now if I call even underscore filter of new vec on the vec over here, hopefully it should just print the even values. So if I have 3 values in the original array, 1, 2, and 3, it should only print an array which has a single value called 2. And that is exactly what happened. Hopefully my function works as expected. I have written a function that iterates over all the values of this new underscore vec and this original vec and pushes just the even values to this new vec variable. This is one way to do it. And if you remember, what is a vector? It is stored on the heap. What am I doing here? I am passing the ownership to the vec even underscore filter function. If I write code that looks like this, let answer equal to this and print answer over here, I am passing the ownership of vec to this even underscore filter function, which is why if I try to use vec again, will I be able to do it? Go back to the ownership section. I cannot. What does it say? Borrow of a moved value vec. This vec variable I moved into this even underscore filter function, which is why I cannot use it anymore. How can I make it usable after this? By passing in a reference, not pass in a vector, but at vector. This vector that we have over here is a reference to the thing. It is borrowing the vector. It is not actually owning the vector. The ownership remains in this vec variable, which is why I can now print it over here. I can use it after this line of code. But if I pass in the value, if I pass in the ownership, I won't be able to. Cool. Let's run cargo run again and see if it works. It does not work because I have to dereference the value over here. This is basically a pointer to the number. So I have to do something like this. I have to dereference the number before pushing it. And now if I see, this is the original array printed after the evenly filtered array. Cool. This is the evenly filtered array. This is the original array that gets printed on the screen. And now I have passed a reference to vec 𝗏32, just like in the last few slides, if you remember, we were passing a reference to the string rather than passing the whole string. Vectors and strings are very similar. Strings are actually vectors only, right? There are a bunch of characters one after the other. Similarly, right now we have a bunch of numbers, but if I change this to be a character array, then a vector can pretty much just be very similar to, if not exactly the same as a string. A vector is nothing but, or a string is nothing but a vector where every element is, a character rather than being a number. Cool. Let's go to the slides. Let's look at both of these implementations here. Pretty much the same thing. Define the vector over here, call the even underscore values function with, firstly, this is the third approach, which is I pass the original vector inside. I pass the original vector inside mutably. I pass in a mutable reference over here. If you look at it, what is the argument over here? It is a mutable reference to vec 𝗏32. And I just remove the elements from that specific index that is an odd number. I repeat, anytime there is an odd number, while I is less than v.length. Very different syntax I've used over here. I'm not iterating like that. This is probably an easier iterator for you to understand. I initialize a variable called I. I say while I is less than v.length, while I'm iterating from I to I equal to 0 to v.length minus 1. If v of I modulo 2 is not equal to 0, if this is an odd number, then I remove it from the index or remove it from the vector. Else I do I equal to I plus 1. That is how I'm filtering out the array. This is another way to do it. And I'm doing it in place. I am not creating a fresh array. Over here, I was creating a fresh array. We have 2 arrays in memory at some point. I create a fresh new underscore vec over here. Versus in this approach, I have a mutable reference to the original vector over here, which means I'm just changing it in place. I'm not creating a fresh array. This is more space efficient compared to our approach. That's approach number 1. And approach number 2 is just, me taking the ownership of the vector, me creating a fresh vector over here, and then pretty much the same as the approach that we had written over here. So do we understand vectors? Do we understand how can you get a specific value at a specific index in a vector v of I? Do we understand how can we remove an element from a vector v dot remove? How can we push an element to a vector v dot push? Are we good to go? Hopefully that's clear. And one more thing is how, just another way to initialize a vector is by using the vec macro. Again, I'm introducing a term we haven't yet learned, which is a macro. But as the name suggests, it's something that expands to something else. It is a macro which expands to something else. This vec exclamation 1, 2, 3 will pretty much create a fresh array or a fresh vector for us and push all of these 3 elements to it. This is just a easier way to initialize a vector. Rather than me having to write this, I can simply write vec exclamation 1, 2, 3, and this will initialize a vector for me. That has these 3 values, 1, 2, 3 as the initial set of values. It's just another way to initialize an array. And now comes the slightly hard bit inside vectors, which is why I've put an orange thing over here. Defining the type of the vector as a generic. I have already done it, so hopefully this is not too hard. But whenever you are defining a variable, a vector, its type can be inferred, or you can explicitly give it a type. And if it is a vector of integers, then it looks something like this: vec I32. That is the type of this numbers array. It is an array, or it is a vector of type numbers I32. It can automatically be inferred. I repeat, whenever you're creating any variable, let me delete all of this. Whenever you're creating any variable, let's say let x equal to 1, its type is automatically inferred. The Rust compiler automatically understands that this is a number, so probably I32 is its type. What is its type? Its type is I32. Did I have to explicitly give it a type? I did not. I can give it a type if I want, but I did not have to explicitly do it. Similarly, when you're defining a vector, my underscore vec, you can define it like this, and its type will be automatically inferred. I repeat, its type will be automatically inferred to be vec of I32, which means a vector of numbers, or if you want, you can explicitly give it this value as well, something like this. Again, I understand if you don't yet get what this syntax is, we'll be reaching generics very soon. Then you'll be able to comprehend this, angle braces a little bit better. Alrighty, with that, we'll move on to HashMaps, which is the second type of, very commonly used collection in various languages. All right, let's understand HashMaps next. I'm assuming this is fairly simple if you come from the Java world, JavaScript, any language, I would say. There's this concept of HashMaps in Java as well. There's this concept of maps in C++. Similarly, in case of Rust, HashMaps exist. What do they let you do? They let you store key value pairs in Rust. Until now, we have stored collections like this. We created a vector that had values like this: 1, 2, 3, 4, 5. What is a hash map? A hash map is a key value pair, which means it has a key like 𝗏𝗏𝗃𝗏 and has a corresponding value for 𝗏𝗏𝗃𝗏, let's say 21. Let's say this is the age of 𝗏𝗏𝗃𝗏, let's say. Then there is another user called Raman, and this is the age of Raman. Then there is another user called Parthav, weirdest name I could think of. Let's say their name, age is 32, so on and so forth. This is again a collection. It has various values inside, but every value is a key value pair. Along with the value that you have on the right, there is a corresponding key over here. You can insert values in this hash map. You can get values from this hash map. You can clear the whole hash map if you want. There are various functions that the HashMap struct provides you. Let's look at them. The common ones are insert, get, remove, and clear. This would let you insert something in the hash map. This would let you get something from a hash map given a key. Remove something from a hash map, clear something from a hash map. There is some code written over here that will be a little hard to digest, so I have written it over here as well. Let's kick things off by understanding how do you define a hash map. The way to define a hash map is, number one, you have to import it from one of the standard libraries in Rust. So you have to add the import statement at the top of your file. Use std::collections::hashmap. Then this is how you declare your very first hash map. This is similar to how we had declared a vector before this, vec::new. This is how we were defining a vector. This is how I have defined my hash map. Do I need to give it a type over here? I don't. So, if what was written before feels a little weird, here is the simplest way to define a hash map. Let mute users. It needs to be mutable if you need to insert some values inside it. Hence, this is a mutable variable. HashMap::new. This is again a function associated with this HashMap struct. I can insert something here. I can insert something here. I can get something from, the hash map. So at this point, what does the hash map look like? At this point, the hash map looks something like this. It has a key 𝗥𝗲𝗃𝗀𝗃, a value 22. It has another key Raman with value as 32. This is what the hash map looks like. So when I try to fetch a value from it, when I try to do users.get 𝗥𝗲𝗃, what do you think it should return me? You might say 𝗥𝗲𝗃. It should return you 22. 22 is the value that is stored for this corresponding key. Given the key 𝗥𝗲𝗃, 22 is the corresponding value. You might think that users.get or a hashmap.get function returns you the final value, which in this case is a number. But can you guess what it should return? What if I would have written a random string over here? What should it have written in this case? 𝗥𝗲𝗃 -1. It does not exist. Or this function should return what? It should return an option enum to us. Since we know users.get may lead to a number or it may lead to nothing. There might be a key that does not exist. Hence, the folks who wrote this HashMap library are smart enough to say, this is going to return what? It is going to return you an option of type U32 or, a number or a none value based on whether or not this key already exists over here. So how would you actually print the age of 𝗥𝗲𝗃? You would have to pattern match on first username and write, if I found a value, if enum has two values, what are they called? I totally forgot. I'm remembering the other ones. Give me 1 second. None and sum. There you go. So if the variant is sum, if we found some value over here, then I'm going to just print the age. If I found no value over here, I'm going to print user not found in the DB. Hopefully that's straightforward. Nothing too out of the ordinary here. We've already done this. Insert something into the hash map. Get something from the hash map. Print it based on whether or not it exists. It may not exist. If I run this code right now, let's see what it prints out. What do you think it will print out? There are no compilation errors. So hopefully it just runs. Let me try to run it. And what does it print out? It prints out age is 22. That's what gets printed out over here. Let me try to run the same code when the 𝗥𝗲𝗃 key does not exist. When I don't insert 𝗥𝗲𝗃 into the hash map, what do you think gets printed? User not found in the database gets printed. Cool. Hopefully that's straightforward. That is all you need for this section. Let's move on to a few problems in hash maps. The best way to learn anything is by, solving a few problems in it. Write a function that takes a vector of tuples Harkirat tuples have not been introduced yet. You'll see them, fairly simple thing, nothing too complicated. Each tuple contains a key and a value and returns a hash map where the keys are unique keys from the input tuples and the values are the vectors of all corresponding values associated with each key. Wow, that's like a hard thing. The problem statement is actually incorrect based on this function signature. I initially wrote a more complicated assignment, eventually toned it down. Let me explain both the assignments, and you can pick and choose if you want to do the hard one. This is the problem statement over here is actually a harder problem to solve compared to what we are solving over here. What are we solving? We have to write a function called group values by key, which takes a vector as an input, but it is a vector of what? It is a vector of a tuple. It has two values in here, string i32. Every value of this specific vector has two parts. It has a string, it has a tuple. This could have also been a struct, but just to not complicate things, just to not have a custom struct, we defined a tuple over here. A vector of a tuple is what's present over here. What does it return? It returns a hash map, which has string as the key, which is going to be the first thing over here, and a number as the value, which is going to be the second thing over here. That is what we have to return from here. Let me write this function down over here. Let's try to code it together. All right, sorry about that. I forgot to change the screen. This is the code that I have written. The function was called group values by keys. As the name suggests, given a bunch of key value pairs in the vector format. The input is a vector of tuples where the string is the first tuple, part of the tuple, number is the second part of the tuple. What are we supposed to return? We're supposed to return a hash map, which has a string as the key and a number as the value. Basically, the input will look something like this. It is a vector where the first value is this, 𝗥𝗲𝗳𝗀𝗀 is 22 years old. The second value is this, 𝗟𝗶𝗸𝗀𝗀 is 32 years old. It is a tuple. What is a tuple? It lets you store two things together. You could totally replace this with a struct as well. A struct that looks like this. Name, string, and age, i32. You could write this as well. You can write, this is going to be an input of not a tuple, but a user. That is fine as well. The logic changes a bit and the input becomes much more cleaner for you to write. Or if you don't want to deal with structs, what have we done? We have said, input is going to be a tuple being something that has two values, a string and a number, a string and a number. Given this input vector, we send it to this function. What does this function do? It takes the vector as an input and converts it into a hash map. Pretty much, just converting one format into another. How do we do it? We initialize a hash map. We iterate over this vector. How do you iterate over vectors in Rust? There are various ways. We're coming to them in the iterator section. But one way is this. For the value in vec. For, if this was a vector of numbers, then the value over here that you would get would be a number. But since it is a vector of tuples, since the vector has two parts, you can destructure those two parts over here. That is how, or that is why, that is what we've done over here. We've destructured the key and the value. For this key comma value in the vector, hm.insert key comma value. In this hash map, insert the key and the value. What key and value we're inserting over here? The one that we got as the input. So what will this do? In the first iteration, this will become 𝗥𝗲𝗃, 22. Her key will be 𝗥𝗲𝗃, value will be 22. So what will get inserted in the hash map? At the 𝗥𝗲𝗃 key, 22 will get inserted. In the second iteration, key will be 𝗟𝗻, value would be 32. So what would get inserted in the second iteration? 𝗟𝗻, 32. This would convert our sort of vector of tuples into a hash map. And if I run this code, you would see what you would expect, which is something like this, a hash map that has 𝗥𝗲𝗃 22 as the first key, 𝗟𝗻 32 as the second key. Cool. Hopefully that's straightforward. This is, one easy practice that shows you how you can iterate through a hash map as well. And there are better ways to do this. We'll probably be coming to them when we reach the iterators section. To recap, the code looks something like this. It's the same thing that I just coded, which is let mute map equal to hashmap : new. Then you iterate over the pairs, insert it into the map, return the map from here. The only thing that will be a little boggling would be, how are we printing the hash map, which again, don't worry about for now. This is how you print a vector or a hash map. Rather than having just the curly braces, you have to add :?" here as well. That's the only new thing / slightly complicated thing over here. With that, let's move on to iterators, which are, slightly harder to digest compared to vectors and hash maps. We have already used iterators over here a little bit, when you write this code over here, under the hood, you're, not iterating over the vector, but iterating over an iterator. We'll come to what that is in the next section. Let's understand what are iterators, various types of iterators, when you should use one over the other. All right, let's understand iterators next. We've already seen a version of them before. Let's formalize them and understand various types of iterators that exist in Rust. The iterator pattern allows you to perform some task on a sequence of items, something like a vector or a hash map. In turn, basically lets you iterate, as the name suggests, over a hash map, over a vector, over any collection that you might have. An iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. If you have a vector 1, 2, 3, if you have a string HELLO, what does an iterator do? It is responsible for iterating over each one of these values and letting you know when the iteration has finished. It might seem like a very trivial thing in other languages, and it, because the complexity is sort of hidden from you. But in case of Rust, when you're defining a vector, you're actually have, a pointer to a bunch of bytes in memory. So if you want to write the logic to actually reach those bytes, it's sort of hard, which is why an iterator will take over all that complexity for you. When you use iterators, you don't have to re-implement all of this logic yourself. The iterators implement the logic to find those bytes in memory in the heap and give you back each and every value one by one. In Rust, iterators are lazy, meaning they have no effect until you call the methods that consume the iterator to use it up. This one's important. It says iterators are lazy. If I ever define an iterator, and this is the way to do it, I've done nothing. I'm not yet iterating over every element. I have just defined an iterator. Think of iterator as another type, just like vector is a type, HashMap is a type, i32 is a type. An iterator is also a struct or a type in Rust. And when you define the iterator, what have I done over here? I have declared the iterator over here. This declaration does nothing. It loads lazily. As time goes by, as you iterate over all of these elements, you actually reference the pointer, or you find the actual value in memory. Defining it over here does not have a lot of performance downsides. You're not yet iterating over the final array. In Rust, iterators are lazy, meaning they have no effect until you call the method that consume the iterator to use it up. We'll come to some of these methods and what do they mean when they say use it up over here. For example, the code. Okay, this is just a code from the Rust book which we can't see. So let me just ignore this line over here. Yeah, we'll have to ignore the last line because this is a snippet from the Rust book, which there's probably some code snippets over there that we can't see over here. If you want, we can go through it. Let's go through the Rust book. This is also a good skill for you to learn sooner than later. Figuring things out from the Rust book. Iterators. Most of the slides from this also come from the Rust book. All right, this is what we're trying to read through. In Rust, iterators are lazy, meaning they have no effect until you call the method that consumes the iterator. For example, the code listed over here. Okay, this is what they mean. Creates the iterator over the items of vector v1 by calling the iter method on the vector. Don't worry about what this is. This code by itself doesn't do anything useful. It just defines a new variable over here. And the iterator is stored in the v1 underscore iter variable. This variable now is storing not the vector, but an iterator on the vector. Once we have created an iterator, we can use it in a variety of ways. In this chapter, we iterated over an array using a for loop to execute some code on each of its items. We have also done that. We have sort of iterated over vectors and hash maps. They also, under the hood, use an iterator like this. Under the hood, this implicitly created and consumed an iterator, but we glossed over how that exactly happened. Until now, whenever we wrote code that looked like this, for val in, not this, ignore this line of code. Whenever we wrote code that looked something like this, we were sort of writing code that looks like this. It sort of under the hood got converted into an iterator. We just glossed over that specific complexity. So when we have written code like this in the past, it is the same as you know, calling an iterator on it, which iterator we'll be coming to very soon. But you know, Rust just hides this complexity from you if you're writing this very simple syntax, but you are still using an iterator over here. Cool. That is what an iterator is. There are various types of iterators. Let's go through them one by one. But you know, high level, you don't need to know these iterators, because if you're iterating over for loops, you know, you are good to go. You don't do anything extra. But in the future, when you create collections of your own, or you know, if you want to create iterators on some different type, it is a great idea for you to know, you know, what exactly does this iterator look like. You know, if I define this iterator over here, its type is this iterator type, which is, you know, a trait which has an item, and you know, it has a next function, which, you know, you implement for your own custom iterators in the future. Don't worry about this at the moment, but you know, eventually when you have your own types and you want to create an iterator on that type, you will have to create a struct that implements this trait. Ҳर्कीरत, what does a struct implementing a trait mean? Don't worry about it just yet. Cool. Let's move on, and let's, you know, move on to some simpler things now. Let's try to see a few important types of iterators. The first one is just iterating using for loops. This is the simplest thing we have already seen. Hopefully this is just straightforward as soon as you look at it. This is a variable called nums, which is a vector of arrays. For value in nums, I print each and every value over here. So fairly simple, nothing too out of the ordinary over here. I'm iterating over the nums, all the numbers. I'm printing them on the screen. We've already done this in the past. Under the hood, this does use an iterator. You just don't see it. You don't explicitly define it. But under the hood, you know, this nums, this sort of gets converted into nums.iter. You just don't see that specific complexity over here. A specific type of iterator, we'll come to what that iterator is. Second is if you explicitly first convert, or you know, create an iterator from your vector. I repeat, you call nums.iter. This will return a new variable to you, which will be of type iterator, or which will implement the iterator struct. What does that means we'll get to. And once you have this variable, you know, the logic after that remains the same. Okay, for value in iter, you can print all the values one by one. Let's quickly code this up. I already sort of coded this, so like nothing too different from what's already on screen here, which is rather than simply writing for val in v1, I'm first creating an iterator on it. If you hover over this, it returns you an iterator. It returns you a struct of type iterator, and I can use, you know, a for loop to iterate over this iterator. I repeat, I can use a for loop to iterate over this iterator. This is a new variable different from the v1 variable that we already have over here. The iter method in Rust provides a way to iterate over the elements of a collection by borrowing them. The important part over here being borrowing them. When you write code that looks like this, where you're using v1.iter, then you are borrowing all of these values. You are not consuming them. v1_iter does not become the owner of these values. v1_iter points to these values. It borrows these values, which pretty much means after this, you know, iteration is done, the original vector is still valid. I can still use the original vector because v1_vector did not consume it. It just borrowed these individual values over here. It did not consume these values. It did not become the owner of these values. It just borrowed these values, which is why even after iterating, I can still use the original v1 array. Let's try to run this code, and you will see I first print the 3 values and I still have access to the original vector. You can't mutate these variables since we have an immutable reference to the internal elements. I do borrow them. I have a reference to these, but an immutable reference. If you want to change these, then we get to the next type of iterator, which is mutable iterators. Let's come back to this specific syntax very soon. Let me first take you through iter mute, or you know, iter_mute function over here. If you want to borrow these elements mutably, you can call v1.iter_mute, and then if you want, you can actually mutate the values over here as well. Val equal to val plus 1. If the original vector is mutable, you can define a mutable iterator on it. And while you are iterating over this value, okay, this doesn't need to be mutable. There you go. And when you are iterating over it, you can actually change the values of this internal vector as well. If you are creating a mutable iterator on it, if you hover over the type over here, what is the type of this? It is iter_mute. It is not iter, it is iter_mute, which basically means it has a mutable reference to each one of these elements. Whenever you call for val in v1.iter or v1_iter, this val variable is a mutable i32 reference. It is a mutable reference to these guys, and hence you can change the value of 1, 2, 3 to, increase it by 1, for example. That is the second type of iterator we have seen, which is a mutable iterator. What was the one we saw before? An immutable iterator. The one thing that I skipped in the middle was another way to iterate. This for loop is, an easy way to iterate, but the real way, that an iterator implements / expects you to iterate over an array is by writing logic that looks like this. For loop hides some of that complexity from you, but this is what is actually happening under the hood. You define an iterator by calling, let's say, nums.iter, and then you say while let some val equal to iter.next. While there is some value, as I call the next function on this iterator, I print that value over here. Basically, iter.next returns you an option, which can either be some value or none. If it is some value, you run this for loop and you run the logic over here. If it is none, you break out of the while loop. So this is another way to iterate over an array. If it feels a little jarring, it's mostly fine. Let me just show you this in action. So it's, maybe you learn something new here. Rather than writing this for loop, even though this is one way to do it, the other way is while some or value, which let's call it, VL equal to v1_iter dot next. Then you print that value over here. This actually has two things that I'm introducing here, which is why it might feel a little overwhelming. I'll explain what those two things are. The first thing is while some, the syntax is while let some. There you go. This needs to be mutable if you want to do this. Why does it need to be mutable? You should look at the implementation of the next function, and you'll see it requires a @mute self, which is why this needs to be mutable. If you don't understand this, it's fine. Take a pause. Take a step back. Let's try to go through this code over here. What are we trying to learn? Okay, is there another way to iterate over an iterator? Is there another way to get to each and every value of an iterator? Here I have defined an iterator called v1_iter. This is one way to iterate over that iter. Here is one way to get each and every value in that iterator. Here is another way. What is this second way? While let sum of val equal to v1_iter.next. This might feel super jarring. So let's break this down. Basically, whenever you have an iterator, in this case we have, 3 numbers over here. So I can say let first_number equal to v1_iter.next. Let second_number, can you guess, is next. Third_number is v1.next. Fourth number does not exist. As you can see, we only have 3 values over here. So when you call .next on an iterator, it starts to consume each and every value over here. It'll first go through this first one, and it'll return you the value over here. It'll return you a mutable reference to this specific value here, then the next one, and then the third one. If you look at the type, what is the type of this guy? It is option @mute i32. It is a option of a mutable reference to a number. What is the type? Option, which means it could point to a number mutably. It could point to the reference of a number mutably, or it could point to nothing. Of course, if I do it the fourth time, can you guess what will be the type over here? The type over here will be none, because we only have 3 values. So this is one way, another way to iterate, right? We are iterating over the iterator. We are going through all the values over here by calling the next function rather than using a for loop. And if of course, right now I can look at the vector and guess, there are 3 values over here. So I know first number, second number, third number will be valid. Fourth number will not be valid. But what I really want is, here given I get back a value, which is an option, while that option has some value, while let some val equal to v1.next, while v1.next, this thing returns you something. It returns you something that you put in this val variable. You print it over here. This will keep on running until this returns you a none. Then this while condition will fail. Whenever v1_iter.next returns you a none, this while condition will fail because I have not written while none equal to v1_iter. I have written while some val equal to v1_iter.next, do this. And when the iterator sort of exhausts all of these values over here, it will return you a none. This while loop will break and pretty much done with the logic. So this and this both do the same thing. This is how iterators actually work under the hood. If you remember a while back, I told you, okay, every iterator sort of implements this iterator trait. Let me quickly show you, which has there you go, which has a next function. So this is how every value actually gets consumed. But if you don't understand this, it's fine. You will need to understand this if you ever have to create your own iterators, if you have to ever implement an iterator trait yourself. You don't have to do that right now. So feel free to completely ignore this as well, as long as you understand this. And us creating an iterator over here, you're decent, you're like good to go. The only thing to keep in mind is if you want to change the values, then you have to create a mutable iterator, else you have to create a normal iterator. These are the two types of iterators we have discussed until now. To recap, the first kind of an iterator you can create by calling .iter on the value, and this for loop is how you can go over all the values of this iterator. The second type of an iterator is iter_mute, which you can take a mutable reference to each one of these values. If you use iter_mute here, and now you can, iterate over all of these values and update them as well. Lastly, into_iter is the third iterator that we're going to talk about, which is slightly different from the first two. If I write let iter equal to nums.into_iter, everything else looks the same. I can still, iterate over all the values, print them on the screen. But this into_iter has some special properties, and it can give you some performance benefits if you are ready to sacrifice a few things. The into_iterator trait is used to convert a collection into an iterator that takes the ownership of the collection. Important part being here. What was true in the very first iterator? What did the first iterator say? The first iterator said, provides a way to iterate over elements of a collection by borrowing them. What is this iterator saying? It will do the same thing by not borrowing them, but taking ownership of them. It basically means whatever function you have defined over here, whatever iterator, whenever you define this iterator, you can no longer use nums. This iterator takes ownership of the numbers over here. Nums becomes invalid after that specific point, which is not true if you're creating an iterator. If you are creating an iterator using .iter, then you can't change its value, but you can still print it. But the same is not true. I can print the values over here. I still have access to the original vector. I cannot do that if I'm using an into_iter. If I use an into_iter, v1 becomes invalid. Why? It says borrow of a moved value v1. We have moved the vector v1 into this iterator. You cannot use it anymore, and hence, it becomes invalid. Why would you want to ever use this, 𝗥𝗲𝗄𝗏? I will always use iter. The answer is performance benefits, right? If you use an iter, then you have each one of these values is a reference. You have to hop to reach the address, versus if you use an into_iter, you have the actual values access over here. So the answer remains the same. 𝗥𝗲𝗄𝗏, I will make everything mutable. Why do I need to, since Rust has everything immutable by default, I will make everything mutable. You can, but then you lose the benefits that come with immutability. And similarly, You might think, 𝗟𝗲𝗃, I will always use an iterator, because what if I do need to use v1 later? That is fine, but there will be very slight performance downsides, because v1 underscore iter will have a pointer to these values. It will not own these values, and hence, it has to go through a hop to reach the final address when you dereference the value over here. Versus if you use, into underscore iter, that won't happen. Is it significant? It depends on your application. Most case, just most of the times you'll just create iters. But if you want to, you should understand what an into iter is, and hopefully you do. What is the difference between an iter, an into iter, and an iter mute? The first one you want to use if you want an immutable reference to the inner variables and don't want to transfer ownership. Second one, if you want a mutable reference to the inner variables and don't want to transfer ownership. Third one you want to use if you want to move the variables to the iterator and don't want to use it afterwards. If you are sure you don't want to use this v1 later on, then feel free to move it into this iterator. Feel free to use v1 dot into underscore iter. But if you know, you do have to use this, then you can't use into iter. You can't move this vector into this iterator, which is why you might want to use dot iter. Cool. Do you understand this? What do you think happens by default when I write this code? When I write a normal for loop without any iterators, what do you think happens? It is similar to me creating into underscore iter. It consumes the vector. If I write a simple for loop over here, if I don't write any iterators by default, if I write code that looks like this, you will notice it begins to complain. It says borrow of a moved value v1. Why did it get moved? Because this is the same as doing this into underscore iter, which consumes the vector, which is why it starts to throw an error. So if you write code like this where you're not using any iterator, you are simply using into underscore iter under the hood. It's the same thing. Code on the left and code on the right do the exact same thing, which is, it uses the into iterator and not the iterator. Cool. Hopefully that's clear. Hopefully you understand the three types of iterators that exist and how do you, iterate through that value given you have that iterator. How do you go through each and every one of these values given you have created this iterator? But iterators give you something extra. They provide you some functions by default, basically, for example, a function like .sum, which will, as the name suggests, find the sum of all of these values. So these functions are of two types, consuming adapters and iterator adapters. Let's understand that next. Is not super important, but sort of important. There are a few functions that you get that you can access on top of an iterator. Some of these functions lie in the category of consuming adapters. Some of these lie in the category of iterator adapters. Let's understand what these two types are and how do you use one over the other. All right, let's understand consuming adapters first. Whenever you create an iterator, again, you need to know this very carefully. This is a vector. The type of this is a vector. The type of this is an iterator. On top of this vector, you create another variable called an iterator. And on this specific variable, you can call various functions. For example, sum, which as the name suggests, would find the sum of all of these values. For example, 1, 2, 3, it will sum it up to 6. This function over here is a consuming adapter. Why is it a consuming adapter? Because it consumes the iterator. I repeat, it consumes the iterator. It does not consume the vector. It consumes the iterator, which basically means you can't use this iterator anymore. You can use this iterator over here once. This sum function will consume the iterator. You can't use it again. Let's look at that. While we code it, first define a variable called v1, which is a vector. Then define a v1 underscore iter equal to v1 dot iter. And then call let's sum equal to v1 underscore iter dot sum. This is how you call the sum function, and this sum function ends up consuming this iterator. Look at the other type. Now, if I print the sum, everything is fine. If I run this, you will see it says sum is 6, but I cannot use this iterator anymore. This iterator has been consumed. If I try to use this iterator over here, it will give me an error. What does it say? Use of moved value v1 underscore iter. v1 underscore iter gets moved to the sum function. If I hover over this sum function and try to look at its definition, you will notice it takes self as an input. It does not borrow. It takes the ownership of self. It takes the ownership of v1 underscore iter, which is why it has been consumed. It has been moved, not moved. It has been moved. It has been moved into this function, which is why you can't use this iterator anymore. What is this function? This function is called a consuming adapter, a function that ends up consuming the iterator. How do you know if a function is consuming the iterator? Pretty simple, right? If this function takes self as an input and not, let's say, add self. If it would have taken add self as an input, it would have been borrowing the variable. But since it takes self as an input, it ends up consuming the variable. And then, even if you try to print it, that is fine. You can't use v1 underscore iterator anymore. Its lifetime sort of ends over here. Lifetime is the wrong word. It is no longer valid because its ownership got moved to the sum function. Cool. That is a consuming adapter. Why is it called a consuming adapter? Because it ends up consuming the iterator. What is the other kind of adapter? An iterator adapter are methods defined on the iterator that don't consume the iterator. Instead, they produce a different iterator by changing some aspects of the original iterator. They produce a different iterator. They create a different iterator by changing some aspects of the original iterator. So let's say I define a vector v1 over here, which looks like this. I define an iterator on top of that v1, that specific vector. And then I call iter.map and I pass it a closure. This is something we haven't discussed, but hopefully it's straightforward to understand what this is. This is very close to a function where we have an argument first and then a return type over here. X is the argument and x plus 1 is what we are returning. This is very similar to map in JavaScript. If you've ever used map in a JS array, this thing is fairly similar, where we iterate over the original iterator, or we use the original iterator, we call map on top of it, which returns another iterator, which then we can use. So is this a consuming adapter? No. What is this? This is an iterator adapter because it is an adapter that returns another iterator. Whenever you call iter.map, it returns another iterator. This function will return another iterator, which you can use. And as you can tell, this map function over here, what would it do? It would map every individual value to something new, which means it would convert 1 over to 1 plus 1, which is 2. It would convert 2 over to 3. It would convert 3 over to 4. Let's see this in action. Let's try to take the original vector. Let's create an iterator on top of it. Let v1 underscore iter equal to v1 dot iter. Let's try to call map on it. Let v2 underscore iter or v1 underscore iter 2 maybe equal to v1 iter dot map. And what closure are we passing in? X plus 1. I think this is incorrect. This is correct. What do we say? Take x as an input and return x plus 1, return a new iterator, which has, x plus 1 as the individual values, not x. What would that mean? That means, it has 2, 3, and 4 as the next set of vectors. And now if I iterate over v1 underscore iter for I in v1 underscore iter 2, and I print it, what do you think gets printed? Can you guess? 2, 3, 4, right? Because the original vector is this. I convert this original vector over to 2, 3, 4. I map every individual value to x plus 1, which is why the final thing that runs over here, the final thing that you see in the output is 2, 3, and 4. The original vector is still intact. v1 is still intact. v1 underscore iter, this specific v1 underscore iter 2, just points to another vector which has individual values set to x plus 1. Just like there is map, can you guess another function that should probably exist over here if you're coming from the JavaScript world? It is the filter function over here, which is, what does it let you do? Filter lets you filter some values from the original vector. It lets you filter out a few, let's say, even values, odd values. I define a vector over here. I define an iterator. I call iter.filter. And what does the closure say? It says I'm going to take x as an input. And if x modulo 2 is 0, if this is an even number, then I will return true. That is what, x modulo 2 equal to 0 returns a boolean, which means either a true or a false based on whether or not x is even. If it is even, it returns true. If it is odd, it returns false. And what will iter.filter do? It pretty much filter the original array over here and just return, the even values. So 2 is the only thing that will get finally stored in this second iterator. If you iterate over the second iterator, you will notice that 2 is the only thing that gets printed on the screen. Let's try that out. I have a vector 1, 2, 3. I have the first iterator on top of it. The second iterator is x.filter x mod 2 equal to 0. Star x mod 2. This, if you hover over it, this is at I32. So, it is a reference to the reference of I32, which is why you have to dereference it ideally twice, but even once works. So ideally you should do this, but even if you do it once, it's fine. Rust is smart enough to convert it in, convert this reference, even though this is a reference, into a final number. And star x mod 2, it will understand, this points to not the pointer, but the actual value. If I run this, you will see the final array that gets printed is just 2. 1 and 3 get filtered out. That is what this filter function over here means. It means, if you have multiple values over here, 4, 5, only the even values are what will finally get printed on the screen, 2 and 4. Cool. That is what an iterator adapter is, which returns another iterator. It is a function on an original iterator, which returns another iterator. That is what a iterator adapter is. What is a consuming adapter? An adapter that consumes the original iterator, does not return anything. Cool. Assignment. Write the logic to first filter out all the all values, then double each value and create a new vector. Can you do that? It'll just show you very simple, functional language like chaining. Okay, first filter out everything that is odd. So x modulo 2 equal to 1. Then map this iterator to x into 2. And that's what gets stored over here. If I run cargo run, you will see 2, 6, 10 is what gets printed. First, we filter out the odd values 1, 3, and 5. That is what this over here does. Then on top of this iterator, we map it to x into 2. So the final cell becomes 2, 6, and 10. Cool. That was the assignment. Hopefully that's straightforward. You can define a separate function that does it, or you can just write it how I did on the screen. With that, this is another way to do it. Let's just take you through this. This isn't too bad. What is the assignment? The assignment is write the logic to first filter all the odd values, then double each value and create a new vector. So it will take a vector as the input. The only extra thing it will show you is, how to convert an iterator. How to convert an iterator back into a vector. We understand how to convert a vector into an iterator. What this specific slide is supposed to teach you is how can you convert an iterator back to a vector, and the answer is by calling .collect on the vector. Let's see this in action. The problem statement said convert a vector into a new vector, or a new iterator. Let iter equal to v1.iter dot map every individual value to x into 2. Before that, maybe filter out all the odd values, x mod 2 equal to 0, and then map it over to x into 2. So first filter out all the odd values, then map every odd value, multiplied by 2, so everything becomes even. And now if I want to convert this back into a vector, I can either define a new vector over here, let v2 equal to, vec new, and go from there, or I can simply say let v2 equal to iter.collect. What does this mean? As the name suggests, it collects all the values and converts it back into a vector, which is of type vector of I32. You have to explicitly give it a type. If you don't, it'll give you an error. Consider giving v2 an explicit type, which in our case is going to be vector of type I32. If I run this, let me print v2 on the screen. What do you think gets printed? Probably 2, 6, and 10 gets printed, right? 2, 6, and 10, because we first filter out all the odd values, that is 1, 3, and 5. Then we multiply by 2, 2, 6, and 10. Cool. That's all we had for iterators, I think. One more thing is iterators in HashMap, which pretty much the same as iterators in vectors. And as I said, in the future, you are going to create your own collections. And when you do, you will have to create iterators on top of those collections. HashMaps already have it. Similar to, in a vector, you can call vector.iter. Similarly, in a HashMap as well, here I've initialized a hash map, here I've inserted some random values in there. Then you can iterate over this iterator. Scores.iter will return you an iterator that does consume the value. If you write, does not consume the value. If you write into underscore iter, then you'll have an iterator that does consume the value, pretty much remains the same as a vector. And then you can print not just a single thing, but since this is a key value pair, it will let you print both the key and the value, and you can use it however you might want. I don't have an assignment from the top of my head right now, but yeah, basically try. The good assignment might be take a vector that is of a tuple string comma number. So 𝗥𝗲𝗳𝗀𝗀𝗃 22 and then Raman 23, so on and so forth. Convert it into a hash map, iterate over the hash map, create an iterator from it, create a vector from this iterator, and go from there. Something like that. Convert between a vector to a hash map to an iterator to a hash map to a vector, something like that. Might be a good assignment to do. With that, we're going to move to the second section for today, probably the third section, fourth maybe. Strings versus slices. A key distinction between two types of strings that exist in Rust. Rust actually has various ways for you to represent a string. We'll understand the two most popular one and why one is preferred over the other. More specifically, why do usually people only use string slices and rarely will you use strings, especially when you have functions and you're passing strings from one function to another. Let's get into that next. All right, let's understand the difference between strings and slices next. We've already used both of these a little bit, but now we'll try to understand what is this, how is it different from this, why do you even need slices, why isn't strings not enough? The string type, which is provided by the Rust standard library, is a growable, mutable, owned UTF-8 encoded string type. A lot of things there. Growable, it can increase and decrease in length. Mutable, you can change its value or add more characters to it, remove characters from it. Owned, which means the variable, the string, owns the value on the heap, and if the variable goes out of scope, the data gets cleared from the heap as well. UTF-8 encoded. This might be a little new to a few people, but there are various encodings when you write a string. For example, you might have heard of ASCII maybe, and just like ASCII, UTF-8 is covers like a lot of characters. ASCII covers slightly less number of characters. I think this covers like 127 characters only, which has everything from A to Z and small a to small z numbers and a few other characters. UTF-8 has everything, including like the Hindi language characters as well. So string is primarily UTF-8 encoded. In the end, what is a string? A string is a bunch of bytes of data, right? A bunch of bytes that eventually get interpreted as, let's say, this specific thing over here. Now the H over here is a bunch of bits, or a byte over here. A over here is a bunch of bits or a byte over here. So when we say that the string type is UTF-8 encoded, we means the final set of bytes that you have, they get converted into a string in the UTF-8 encoding. If the first byte is, let's say, 23 or 001001110, something like this, this gets converted to whatever its representation is in UTF-8, which could be, let's say H. And then let's say the second byte is 01101111011, something like this. This gets converted to A, which let's say is the UTF-8 representation of this number over here. So that is what UTF-8 encoded string type over here means. It means whenever you're using a string, you can pretty much shove anything over there. UTF-8 has, everything from the Hindi language to Spanish to English. So every character that you can think of can reside in this string type. When Rustaceans refer to the string in Rust, they might be referring to either a string or a string slice. This second thing that we're mentioning over here. Until now, we haven't formally discussed this, but when people mention strings, they could mean the string type or they could mean a string slice. Not just one of these two types. Although this section is largely about strings, well, what we are learning is about both strings and string slices. But if you go to the Rust book, this is, a snapshot from the Rust book. They have a separate section on strings, which is why, it says, although this section is about strings, both the types are used heavily in Rust, and both string and the string slices are UTF-8 included. This is what a string is. I'll code this very soon. You'll understand what it is. We've already used this. Slices let you reference a contiguous segment of elements in a collection. I repeat, slices let you reference a contiguous section of elements in a collection. String slices let you reference a contiguous section of elements in a string. So slices are a more generic concept. They apply to vectors, they apply to strings. What are string slices? String slices let you reference a contiguous segment of elements in a string. Rather than the whole collection or rather than the whole string, a slice is kind of a reference, so it does not have ownership. So there are two things that are written over here. Okay, given that you already have a string, let's say I have code that looks like this. Let name equal to string : from 𝗥𝗲𝗳𝗀𝗀𝗀𝗀𝗀. How is this stored in memory? There is the stack over here. There is the heap over here. The variable name is stored over here, which points to, let's say, HELLO on the stack. This is what a string is. And what is a string reference? It references a contiguous segment of elements in a collection. Basically, let's say HEL. If you want to reference a contiguous set of elements in a string, in a vector, how will you do it? You can do it by using slices. The name itself says slice. It is what? It is a slice of the complete string. If this is the complete string, a string slice represents a certain portion of that specific string. We've already discussed strings in the past. Let's quickly look at some code of, how do you define a string? This is how you create a string. Let name equal to string : from 𝗥𝗲𝗳𝗀𝗀𝗀𝗀, and then you can print the string over here. This is a string, this thing on the left. This is how you create a string. This is how you mutate a string. Let's say you want to push my last name towards the end. You can call name.pushStir_sing. This is how you delete from a string. You can call name.replaceRange everything from 8 to, let's say, the end of the name with an empty string, basically removing my last name from here. What does this name.replaceRange do? It replaces everything from, the 8th character over to the end with this empty string. That is why my last name gets removed from, this string over here. So if the string is 𝗥𝗲𝗳𝗀𝗀𝗀𝗀, what will name become at this point? At this point, name will become 𝗥𝗲𝗳𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀. And what is the next line of code doing? The next line of code, this line of code is replacing everything after the 8th index towards the end with an empty string. So everything from here towards the end gets replaced with an empty string, which means we revert back to the original string 𝗥𝗲𝗳𝗀. That's how you delete from a string. And this is how string looks like in memory. This is data on the stack. This is data on the heap. We have discussed it a few times. More technically, if you want to understand, the thing that is stored on the stack is the pointer to the final thing on the heap and the length of the string and the current capacity of this specific pointer. This capacity sort of becomes important because if you want to increase the size of a string, then based on this capacity, you will have to ask the operating system for more space over here. And then the operating system will decide, okay, is there some space available here? If not, it will move the complete string over to, a different space. So these are the three things that are actually stored on the stack. Until now, I only said, okay, a pointer is stored, but the thing that is actually stored on the stack is a pointer to the, first element over here, the length and the capacity. Slices let you reference a contiguous segment of elements in a collection rather than the whole collection. A slice is a kind of reference, so it does not have ownership. We discussed this a few slides ago. What is a slice? It lets you reference a contiguous segment of elements. Basically, if you want sort of a view into this string, if you want just, the first part of this string, if you want something to point here, that is what a string slice is. A string slice is sort of a view into this, let's say the first 5 characters over here. It is a view into a contiguous segment on a collection. What is a string? What is a vector? These are collections. And if you want to view a certain portion of this collection, you use a slice. Let's see this in action with a very common example that you'll find everywhere. This example comes from the Rust book. The example says, write a function that takes a string as an input and returns the first word from it. So for example, if the string is 𝗥𝗲𝗳𝗀𝗃 space sing, what will it return? It will return the first word from it. It will return 𝗥𝗲𝗳𝗃. Let's look at the code that's written over here. It's not too difficult to understand. I've defined a function main which first defines the string, let's say hello space world, and then it calls the function first underscore word, which takes the string as an input. As you can see, what is the input type? The input type is a string. And what does it return? It returns a string as well. Let mute answer equal to string : from empty string. We iterate over the original string. What does for I in str.chars do? str.chars actually returns an iterator. So for I in str.chars would iterate over all of these values. And it says if I is ever equal to an empty string, then we can break right there. Else we will push it to this answer string. By the end of it, I will return the answer string, print it over here. Do you understand what is happening here? Why this is a little inoptimal. When I'm over here, I define the first string variable, which is hello world. And when I'm over here, I'm creating a fresh variable called answer and storing something more on the stack separately. I am duplicating this hello world into a new variable that gets returned from here. Over here, I have two values. I have, the name and the answer. The name gets moved over here, so that's technically not true, but you get the idea. The final thing looks something like this. I have name, which points to a string called hello world. I have answer, which points to a separate string, a separate section that has, hello over here. I have duplicated the first word into a new variable. That might sound okay. Kya ho gaya? This is like fairly common 𝗥𝗲𝗳𝗃. It is fine. You asked for the first word, you got the first word. What was the problem statement? The problem statement was write a function that takes a string as an input, returns the first word from it. That is exactly what is happening here. What is wrong over here, 𝗥𝗲𝗳𝗃? The thing that is wrong is, number one, we take up double the memory. We could have somehow created a slice, right? Created a string slice that just points to the first 5 elements over here. So you had to use twice the amount of memory. That is actually not the best example or the best reason to not write this code that we have written over here. What is the better reason to not write this code? It is if the name string gets cleared, if I ever remove this from the stack and let's say this gets moved out of scope, answer still has the hello value in it. Answer still has hello in it. The problem is, since I am not having a view into the original string, I am not doing this. Yeah, this is the original string. I want answer to point to this. Since I am not doing this, if the original string goes away, if the original string, changes from hello world to, let's say, 𝗥𝗲𝗳𝗃 space sing, then my answer still points to hello. That is a little problematic. This is a little hard to digest example, but the one that Rust gave and hence everyone uses. The question said you should return the first word from the string. So what you're doing over here is you are returning the first word from it, but in a separate variable. So if name ever changes, I repeat, if this name variable ever changes, then this answer variable should also change through the lifetime of this program. Basically, the problem isn't given a string as an input, return the first word from it. The problem statement itself should say, given a string, return a view to the first word. Return me a view to the first word rather than creating a fresh word over here. What if you want to do this? Then you use string slices. What we want is a view into the original string and not to copy it over. I don't want to create another string. I want answer to point to this string so that if this goes out of scope ever, if the name goes out of scope, then this guy should also go out of scope, or this guy should at least complain. Here I am pointing to you, don't go out of scope. The compiler should block you from moving this out of scope if a string slice exists on it. Let's try to code this to understand it a little bit better. Let's say I have a string over here called let word equal to hello world. and I try to create a string slice from it, not create a fresh string that says hello. I don't want to do let word2 equal to hello. I don't want this. What I want is a view into the original object. How can I do that? I can do something like this. Let word2 equal to at word 0.5 or 4, one of these two. I think 5 is fine. Let's try to print it. Let's see what word2 prints. If I print word2 over here and run cargo run, what gets printed on the screen is hello, which is the first 5 characters over here. So seems like I've done something similar, but if you look at it, what is the type of word2? It is at stir. It is a string slice that points to this original string. It is very similar to me doing this, taking a reference, borrowing this word over here, taking a reference to it. But I don't want a reference to the whole thing. I want a reference just to a part of it. And why is this cool? Because now if I try to change word, let's say word is mutable. Let's say word is mutable and I try to do word dot clear. I try to clear the word. The compiler doesn't let me. It says cannot borrow word as mutable because it is also borrowed as immutable. Go back to the original ownership rules. What did it say? If you want a mutable reference to something, which when you call the clear function, notice it takes at mute self as an input. It takes a mutable reference to self. It needs to mutate itself, right? It needs to change this word variable. So it takes a mutable reference to self, and you cannot do that while someone else is pointing to you immutably. What was the ownership rule? The ownership rule said you can have multiple immutable references. If you have a mutable reference, you can't have other mutable or immutable references. This was the ownership rule that we talked about. And why is it coming handy over here? Because since word2 is sort of pointing to word, it is borrowing word over here. Word2 is actually borrowing word. It is a immutable reference to a portion of the string, not the whole thing, but a portion of the string. And hence I can't do word.clear, which makes sense because if I clear the word, then this word2 has no wajud. If I clear this, then what should this guy point to? The word itself got cleared. Even if I change the word, push underscore stir world2, then it's very hard for me to figure out. The first word might change. Word2 ka goal was you need to point to the first word over here. It is pointing to the first word, but that gives you a restriction. While this is in scope, while you have an immutable reference, you cannot create another mutable reference, which is a good thing because if you change this, ideally agar dekha jaye to your program is breaking. You change the string, then word2 is no longer pointing to the first word. It might be pointing to, it is pointing to hello world right now. But if I clear the string, then, I've removed everything from the heap. This word2 will become a dangling pointer. It will be pointing to something that doesn't exist on the heap only, which is why Rust blocks you from doing that right here. This is where, hopefully you see some memory management magic happening. Okay, Rust is preventing you from a very common memory error, which is word2 is pointing to an original word ka segment, a segment of the original word. And if you try to change it now, the Rust compiler won't let you. That is where string slices shine, or that is why you might want to use a string slice over our original implementation. What was our original implementation? Our original implementation looked like this, where we were returning a new string from the function. We were returning a new string. What are we doing now? We're returning a, at stir. If you look at the final code over here, it takes the address of a string as an input. It can also take the string as an input. No, it cannot. It needs to take the address of the string as the input. I'll share very quickly why. And it returns at stir. I do all the logic to figure out what is the first word, and then I return at stir 0 ... the space index. I return a segment from the original word, a slice that points to a segment on the original word. Let me quickly code this as well. What are we writing? We are saying this is the original word, and I'm going to define a function called find underscore first underscore word. which takes, you could write string as an input, but you'll see an error very soon, which is why I'll share why it needs to be @stir or @string. Let's say it's just a string for now, but what does it return? It is not returning a string anymore. It is not returning a string, it is returning a string slice, which means something that points to a different string on the heap. How would you write the logic? You first enumerate over the word. So for I in, first let's define an index, which let's say is 0. This index will point to where the first space is. Where did you find the first space in the word? So if the word is hello world, index should eventually point to 5. Right now it's pointing to 0. For I in word dot chars dot enumerate, if I is equal to empty space, then what do you return? You just break this specific for loop. Else you do I equal to I+1. You also have to make index mutable, and you do not I but index equal to index +1. And what do you return from here? You return a reference to the word from 0 to the first index that has a space. The only problem here is I'm comparing, oh sorry, this needs to be something like this. I is a character, this probably is the index. And what am I returning here? This thing can, yeah, so this might feel fine to you, but can you see the compiler is complaining at you? What is it saying? You cannot return a value referencing the function parameter word. You cannot reference word because the data is owned by the current function. It says, "Kya word was defined over here. Then you moved it to the find first word function. I did not pass a reference here. I literally moved the thing. This ownership was transferred to this word variable over here. You can't take a reference of a word or a variable whose ownership, the variable itself ends over here, right? This word variable is owned by the current function. You can't return a reference to it. If you return a reference to it, you're returning a reference to a variable that is about to get cleared. As soon as the scope ends, this word variable will get cleared from the heap. Why? Because this word variable, is the data on the heap is owned by this word variable, which means whenever this function ends, the data on the heap needs to be cleared. And hence, if you try to take a reference to it, of course, the Rust compiler is smart enough to tell you, okay, don't do this, or you can't do this. What does it say? It says cannot return value referencing the function parameter word. जब function parameter word hai, I can't return a value referencing it. Why? Because returns a value referencing data owned by the current function. It says you are returning a reference to data that is owned by the current function. You cannot do that because if you do, the word variable which is owned by the current function will get cleared as soon as its scope ends, and hence you can't return a reference to it, right? That will be a dangling pointer. That is exactly what a dangling pointer is. Cool. Hopefully that's clear. How can you fix it? Just make sure you're not transferring ownership, right? Just borrow the variable here rather than moving it, and you're good to go, because now word is still valid after this line of code, which means, word 2 can also still be valid because it points to some portion of word. I repeat, word 2 needs to point to a portion of word, which means if you want word and word 2 to be valid after this line of code, you need to make sure you don't move the variable, you borrow the variable in this find first word function. Cool. Now let's see if that runs. When I click on cargo run, when I run cargo run, it says hello world is the first string, which is the original string. Hello is the second string, which is the mutated string. Cool. Hopefully that is clear. Let's look at the example over here as well. The same example over here. You define a mutable string called name, and then you call the first word function. You pass @name as the input, which is a reference to this name string. What does this function do? It finds the index at which space is present, and it returns a string slice to you from 0 up to space index. Finally, you have the string slice stored in an answer, which is sort of a pointer to name. It is not a pointer, it is a slice, but you get the idea. This is an immutable reference to name, even though it's not pointing to the whole name. it is just pointing to this much over here. It is still an immutable reference, and hence, all ownership rules apply. You can't mutate the string anymore until answer is in scope. If answer is in scope, you have a mutable reference. If you have a mutable reference, you cannot have another immutable reference afterwards. Approach number 2 with slices. Let's look at what this is. Yeah, it just does not have the main function anymore. The reason was just to show you, if you were a little confused with the string reference getting returned and now answer getting, pointing to a section over here, I just moved that from the function directly to the main function so that you can see the same thing, or, visualize the same thing a little bit better. This is the name variable that we've defined, which, when this line of code runs, what happens? A variable gets stored on the stack, which points to hello on the heap. And now, after this line of code, few lines of code run, and the answer variable gets created. This answer variable also points here, but more specifically to a section of the specific original string, and then you print it over here. So all ownership rules apply after this. You can't have a mutable reference to the answer variable anymore, or sorry, the name variable anymore. Let's look at this more visually. I created a very weird visualization over here. Here is a better visualization. By the end of this program, you have the original thing which points to hello world on the stack or on the heap, and you have this answer variable which sort of points to a section of it. It points to HELLO, these 5 things over here. And how does it point to only 5 things? Number 1, it has a pointer from here to the same point as this guy, but number 2, the length variable over here is just 5 because it only points to the first 5 elements over here. It is a string slice. It is a slice of this original string that is present over here. 3 types of commonly used strings. There are actually much more, but 2 we have already discussed. Let me discuss a 3rd type. The first one is when you use the string type, which is stored partially on the heap, partially on the stack. All of this data is pushed onto the heap. You have something on the stack that points to it. What is a string slice? String slice is a view into a string object. For example, if you want a view into just the first word, if you want a immutable reference to it, you can create a slice from it, which in this case points to the whole thing. But if you want, you can point it just to the first word over here. And the last thing is a string literal. Basically, if you don't use this string type over here, if you don't have a reference to a string, if you just write hello like this is called a string literal. Its type is still @stir. Let me just show you this, in action. And this is a good thing for you to know. I wouldn't say this is an interview question. No one asked this in an interview, but a good thing to know irrespective. The 3rd type of string is something like this, where you don't use the string type. You just type it out like this, like you would in, JavaScript or C++. What do you think the type is over here? Can you guess? It's definitely not string. I haven't done string : from something over here. I haven't ever said that this is, a string struct where the value is hello world, or I haven't used, the string : from function. So the question is, what exactly is the type of this string? If I have a string literally, what does a literal mean? You don't use any class. You don't even have an @stir. You have a naked string literal over here. The type is still @stir. If I hover over this, what is the type of word? The type of word is, I don't know if you saw it, but the type of word is @stir only. It still points to something. The only thing is this actually points to your binary. What is your binary? Basically, whenever you're running a Rust program, whenever you run cargo run, you will notice a new folder gets created called target, which has, a final binary, which in my case right now is, let me just run cargo build and show you the final release binary. There you go. God damn it. Yeah, you'll see a file over here called Rust part21 for me. You might see a different name over here. This is your final binary, which basically means a bunch of zeros and ones. And whenever you have string literals like these, right? These literals are literally stored in the final binary over here. I keep saying binary, but I hope you understand what I mean when I say binary. If I go to the target/build release/release folder and I run /rust-part-2-1, it runs the program again for me. It's an empty program, which is why nothing got printed. But if you have a string literal over here, it is part of this binary. It's basically, present in these zeros and ones. In these zeros and ones, the program is present. And then this binary is also present somewhere. If you open this binary, you'll find in a certain section, this string is literally hard coded in here. And when I say let word equal to this thing, the @stir, this thing is actually pointing to this, a certain section in this binary. Whenever you open this binary, let me try to open it. It'll probably not show me anything useful. You look, see a lot of data over here. This is your final code, and somewhere in this code, this string is also hard coded. You probably can't search it. But somewhere here, this string literal is present, and this word, whenever this program runs, points to that string literal. When we say @stir over here, it is actually pointing to some part over here in this binary. In this binary, this specific literal is hard coded. That is what the third type over here means, which is when you're not using the string type and you don't have a, at reference to a string type. If you just have a string literal, it is still of type @stir, but this @stir points to not someplace in memory, but literally someplace in your binary. Cool. That is all for strings and slices. I think the only thing that's left is slices can be applied to every collection. String is also a type of collection, something that can grow and shrink. Similarly, if you have an array or a vector also, then also you can take a view into that vector or an array. You can create a array slice or a vector slice if you want to just reference a certain part of an array, which in this case is going to be, everything from 0 to 0. I think this is the starting index and this is ending index -1. Or this -1 is the ending index, which is why I think if you print array slice over here, 1 should get printed on the screen. We can quickly try it out, but it doesn't matter either way. You should let v equal to, let's say, a vec. It doesn't matter. You can create a vec, you can create an array. Let's just create an array 1, 2, 3. And if I do print ln @v 0.1, I think 1 would get printed, but I could be wrong. Yeah, 1 gets printed. So this is the starting index and this is the ending index -1. Let's just confirm if that is true. The second could also be the length. Yeah, 2 to 2. Doesn't work either. Yeah. So this is the starting index. This is the ending index. This -1 is the ending index. Cool. Let's move on. Next up, we probably can move on to generics, which thankfully, I don't have to teach. We already taught this in the 100x Devs live meetup. So I'll just post a video over here where I cover generics from there. It'll also probably be a decent-ish, warm up / breather / stretching exercise for you as you see me move around rather than sitting on a chair. I'll see you in the next section. Let's kick things off with generics. It is actually not a Rust specific concept. It exists in other languages. If you've done TypeScript, you probably know generics from there. And very similarly, generics exist on Rust. Can we read through this code really quickly? It has 2 functions, largest number or largest I32, largest char or largest character. Don't worry about this syntax. This basically means return A, this means return B, this means return A, this means return B. Just another way to return variables from a function, which is just write the name of the variable, don't put a semicolon. So don't get confused by this syntax. One variable defined which gives you the bigger between 1 and 2, another one defined that gives you bigger between A and B. Prints them on screen. We understand this code? Yes. All right. What is the problem in this code? code repetition, which is exactly what generics fix. If you look at this code, it's slightly lesser, right? It's not as big as the last slide. And the reason for that is we have written the same body over here. And we have said, I am not going to accept a number or a string. If you look at it, I say A is T, B is T, and the return type is also T. Capital T over here is what's called a generic. Ignore this thing over here. I'll get to what this thing is maybe at the end if we get the time. But what does it say? It says that A and B are not an integer, not a character, not a string. They're a generic argument. Generic means it can be a number, it can be a string, as long as it follows certain conditions, as long as this operator is valid on them. That is what this specific code over here does. If you don't understand it, feel free to, when we write this code in JavaScript, you will see we don't need this. But in case of Rust, if you want to use comparator on something, you need to make sure it has this specific trait bound, which is why we had to write this over here. But you can ignore this second part. Whenever you are using a generic variable, which means it can be anything, you have to first define it like this. Let's write some TypeScript code before this maybe to understand this a little bit better. But the goal is that this function has the same body. This thing and this thing have been converted into a single function. The type of this function is T, T, and T. It is not I32, I32, I32 or character, character, character. It has a generic type, which means you can call this function with anything, be it a number, character, or a string, as long as it has this operators set on it, as long as you can call an operator on it. This is the equivalent code in TypeScript, which might be slightly easier to digest. Similar thing, a function, this is the name of the function, but the arguments are not number, not string. It's a generic argument. This T over here, this syntax over here basically tells TypeScript कि यहाँ पे यार अब इसको generic argument use करने देना. T is a valid generic argument after this. Let my developer use this. If I write this code, I wish I could copy it. This is the code that we've written, and this is some extra syntax that I had to write because I had to tell TypeScript कि इसके बाद T use करने देना. If I want A and B can have different types, I repeat, if I want कि ये जो function call होगा ना, whoever is calling this function larger can call it with a string and a number, different types. Then I have to tell it कि यार दो generic arguments हैं. T is also a generic argument, U is also a generic argument. Let the user call it with basically anything. But if I have a single one, then the user can call it with only a single type of argument. अगर ये T बन गया, if a string becomes T, then the second one also needs to be a string. Otherwise, you will get a red squiggly over here. Argument of type 1 is unassignable to parameter of type this. This is a string. This also needs to be a string because I have said कि यार ये अगर T होगा ना तो ये भी T होगा और return type भी T होगा. This is a number, then this also needs to be a number, return type also needs to be a number. Do we understand this? How many of you don't understand this? Okay, great. Cool then. Same thing can be applied to Rust, which is, I mean, this is almost exactly the same. The only extra thing that Rust gives you is this trait bound, which as the name suggests, it bounds the variable on something. कि यार ये जो T है ना, it should follow this comparator, whatever this argument is. It cannot be something random, which does not, let you compare two values. TypeScript, as you know, is not as safe/strict as Rust, which is why this happens. Which is why I have this third, function call over here. TypeScript won't complain over here. I am giving it something fairly random. An object with name Raman, an object with name 𝗥𝗲𝗳𝗀𝗀. It is not complaining, even though there is no sense of a comparator on two objects. And if you run this code, you will see it gives you very random values. If I run this last line of code, it will print name Raman sometimes. It will print name 𝗥𝗲𝗳𝗀𝗀 sometimes, which is bad. ambiguous code, generally ambiguity is bad. It should be stopped at compilation, which is exactly what Rust lets you do. Rust lets you hear itself say कि भाई तुम इसको किसी random चीज पे नहीं बुला सकते. It needs to follow something. There needs to be some sense on this comparator. How are we doing? Can we move on to Rust? Sorry, structs. All right, let's understand traits in Rust next. If you come from the Java world, then this is very similar to abstract classes. If you come from the JavaScript world, then this is very similar to interfaces and you implementing interfaces in a class. So interfaces means a bunch of things in JavaScript, but specifically you can use interfaces to implement classes as well. If you understand these two things, then traits should be straightforward. If you don't, then it's fine as well. Let's try to understand what is a trait in the context of Rust. A trait defines the functionality of a particular type that can be shared with other types. Slightly jargony statement. When you look at it, you'll understand it in a second. We can use traits to define shared behavior in an abstract way. That's why I said it's very similar to an abstract class in Java. When you use trait bound, we can use trait bounds to specify that a generic type can be any type that has a certain behavior. Ignore this last statement for now. We're coming to it very soon. Traits are similar to feature called interfaces in other languages, although with some differences. Specifically in JavaScript, interfaces are very similar to traits in Rust. Let's look at how do you define a trait, how do you use it. The way to define a trait is something like this. I've written define a trait called summary. If it's in the same file, you probably don't need pub over here, but it's fine, we've written it. Pub basically means public, as you could have guessed. A public trait called summary, which has a function called summarize, which takes @self as an input, returns a string. Can you guess where I'm going with this? This is similar to an abstract class, a class whose function you are defining over here. And you can say, here, whatever struct implements this trait, I repeat, whatever struct implements this trait, that specific struct will need to have a summarize function. So here I've defined a trait. It's like a blueprint. I repeat, it's like a blueprint that other structs may follow. If you define a struct over here called user and you say implement summary for user, you are not simply saying implement user. This is the simple impl block we have seen until now. You are saying I'm going to implement the summary trait for user, and here you define the function called summarize, which takes @self as an input, returns a string, and the string over here is this string that you see over here, which is user, some name of the user is y years old, where the first variable here is self.name, the second dynamic variable here is self.age. Format basically is another macro. It lets you, concatenate multiple strings together. In this case, for example, we want to concatenate the name and the age. So this is how we have done it. Let's try to see this in action. Let's try to code this. But hopefully you understand, okay, for the user struct, now I have implemented the summary trait. And hence, whenever I define a user, I can call user.summarize without any issue. We can say that the user struct implements the summary trait. We can say very similar to how you might say, a class implements another abstract class in Java. I repeat, you might say one class implements another abstract class. Similarly, you can say the user struct implements the summary trait. Let's try to code this. Before that, again to recap, this is how you define a trait. Pub trait, the name of the trait, and whatever function blueprints, whatever function signatures you want, whoever is implementing this trait to have. If user is going to implement this trait, they will need to have a summary function in there. This is how we have defined a struct, nothing new here. This is where we have implemented a trait on a struct. And lastly, we have a main function where we are defining the struct and then calling the summarize function on it. Let's code this. yeah, this is the default implementation. Maybe let's discuss one more thing, then we'll try to code it. What does this say? It basically says that when you define a trait, you can actually implement a default function as well. So whoever is implementing summary, which in this case is user, if they have their own implementation, then that will be used. If they don't have their own implementation, then this default implementation will be used. So if you want, you can just have the function signature, or if you want, you can also have a default implementation. Okay, whoever is implementing this trait, by default summarize will, this is the function that will get called. But if they want, they can also override this function. Let's see this in action. Let's try to code this really quickly. Number one, I'm going to define a trait called summary. And what do I say? Okay, this is going to have a function called summarize, which takes nothing as an input and returns, or at self as an input, sorry, and returns a string. Then I'm going to define a struct called user. I'm going to say user has a name, which is a string, maybe a last name, and then, an age, which is a number. Lastly, I say implement the summary trait for the user struct, and it'll keep giving me an error because it says missing the summarize function in the implementation. So it's telling me, okay, you have to define a function called summarize, which takes at self as the input and returns a string. And over here, I can return whatever I want. The thing that we had returned, I mean, you can simply return, whatever, self.name, something like this. But if you want, a more custom string format, why is this giving an error? Self.name.clone you can call over here. Or if you want a more custom, message, you can format a string that says the name is self.name and the age is self.age. Let me remove everything else. Probably have to convert this into a string. Oh, sorry. There you go. And now the summarize function returns a slightly more formatted custom string that will say my name is X and the age is Y. Now if I want, I can define a user, let user equal to a user struct, name is 𝗟𝗶𝗲𝗏𝗀𝗀, age is 21, and then I can call user.summarize that would return the string. I want to print the string over here, so I can call something like this. Hopefully that's clear. The only issue there is this needs to be of a string type and not at stir. This is the same thing that we've been seeing in the slides, so nothing new here. Let me try to run it and just show you this in action. When I call cargo run, it prints the name is 𝗟𝗶𝗲𝗏𝗀𝗀, age is 21, which is exactly what you would expect it to print. If I go back to the slides, what did we learn over here? A default implementation. So let's try to add a default implementation rather than just having a function signature here. I'm going to return hi there. And then right now, if you look at it, I will override this implementation. So everything remains the same, even though I have created a default implementation. I have overridden this default implementation over here. If I run this, it says the name is 𝗟𝗶𝗲𝗏𝗀𝗀, age is 21, but I can also remove this default implementation now. The compiler won't complain because we have a default implementation already. And in this case, it prints hi there. Hopefully that's easy enough to digest. Here is how we have defined the default implementation. And you can see this does not error out anymore. One new thing that we've added now is, one new thing that we're discussing next is traits as parameters. What if you want to create a function called notify such that only structs that implement the summary trait can be taken as input? I repeat, you want to create a function called notify that takes something as an input, and this something needs to implement the summary trait. That is what is written over here. It's slightly hard to read, so let me quickly write it over here. We say I'm defining another function now notify, which takes something as an input, let's call it U, which implements the summary traits. What do we say? Here, whatever I take as input, let's say U, or whatever we want to call it, it is not of type user. It is anything that implements the summary trait. And why is this useful? Because I know anything that implements the summary trait will probably, or not probably, 100% have u.summarize as a function on it. Anything that implements the summary trait. Over here, user implements the summary trait, and hence it has a default summarize function. If I want, I can create my custom summarize function. If there's another struct that I create over here called, let's say, fix, a random unit struct doesn't even have any value, and I say I want to implement summary for fix as well with the default implementation. Now I can pass both this fix struct to this function. I can also pass this summary struct to this function. Already getting a little complicated, I can tell. I can see you through the camera. So let me, try to show you this in action. If I write notify user, do I see a compilation error? No, I don't. Everything compiles correctly. If I write notify one, do I see a compilation error? I do. What does it say? It says the trait bound integer summary is not satisfied. It says integer does not satisfy this specific trait bound. Summary is not implemented by an integer. Is it implemented by a string? It isn't. That is why you see an error over here. Can I implement it on a string? I probably can. Impl summary for string. I can add a default implementation to the official string type as well. And now if you look at it, this does not complain anymore. What would its default implementation be? The summarize function would still print this, default value. But since I've implemented the summary trait on it, I can now pass a string to the notify function. But if I did not do that, if I remove this specific implementation block, then I can't pass in a string. Can I pass in a user? Yes, I can. Can I pass in let f equal to fix? I can pass f as well, because fix also implements the summary trait. So what have we learned in this section? We have learned about traits as parameters. If you ever want to create a function that takes something as an input that implements a specific trait, you can write it like this. If you want a reference to it, just put an @ in front. If you don't want a reference to it, then you can simply write impl space summary. So if I want, I can also replace this with @impl summary. If I just want its reference, if I don't want a reference to it, I want the actual value, then I don't need to put @ over here. I can simply write impl summary. Cool. That's trait as parameters. But traits as parameters, or traits as arguments, under the hood sort of, do something else. Let's look at what that under the hood thing is. To recap, here I've defined a notify function. It takes an item as an input that implements summary. It will only accept things as an input that implement the summary trait. And since we know that the input implements the summary trait, we can call item.summarize over here. The impl trait, the thing that you just saw, is syntax works for straightforward cases, but it is actually syntactical sugar for a longer form known as the trait bound. I repeat, whatever we wrote over here, or whatever you wrote over here, u:\impl summary, this is actually syntactic sugar for something else. What does that mean? It means that under the hood, this gets converted to something else. What is that something else? That something else is called a trait bound. Let's understand or look at the syntax of a trait bound. It's very similar to what we saw over here. A trait bound looks something like this. It says pub function notify. I want to take a generic as an input, and these are the constraints on the generic. The t generic now should implement the summary trait. And then I can simply say item is of type t. I say item is of type t, t is a generic, but this generic should implement the summary trait. I repeat, this generic t should implement the summary trait. Only then, can it be passed. This and the thing that we saw before, which is this thing right here, which I know it's a little hard for you to see. Both of these are the same things, and one is a syntactic sugar for the other thing. This generic is bound to the trait. The T generic is bound to the summary trait. And if you want, you can bind this T generic to multiple traits by putting a plus in the middle. If you want something needs to have the summarize function, and let's say you have a different trait, not a struct, a different trait, you can actually force T to implement both of these traits. A single struct can implement multiple traits. Let's see this in action really quickly. Let me remove this. We have the trait called summary. It has a default implementation of a summarize function. I have a struct called user. The user struct implements summary. Let me create another trait called fix. Let me create another trait called fix, which has a function called fix, which pretty much returns the same thing. Hi there from fix. And I implement summary for user. I also implement fix for user. Both of these have default implementations of functions, which is why, it doesn't matter for us. I don't have to actually implement them here. If they did not, if this was just a function signature, then in this case, I would have had to implement the actual logic over here. Cool. Now, can I say user implements summary? It does. Can I say user implements fix? It does. What if I say, this function needs to take a generic as an input? I repeat, it takes a generic as an input, and this generic needs to satisfy the summary trait plus the fixed trait. Whatever it takes as an input needs to satisfy both of these traits. Is that true for the user struct over here? Yes. The user struct implements the summary trait. It also implements the fixed trait, which is why if I pass user over here, everything compiles with no errors. If I stop to implement fix, does it work? It does not. Why? Because it says the trait bound failed. The trait bound user:fix is not satisfied. It says, we expect whatever you're passing as an input over here to satisfy the summary trait as well as the fixed trait, but we are not implementing fix for user. If I do implement it, compilation error goes away. Is this easy enough to understand? Hopefully it is. That's all we had for traits. Next up, we're going to understand lifetimes. All right, coming to the most difficult topic for today, lifetimes. Lifetimes are extremely hard to digest. So very big disclaimer, there's a high probability you don't understand what is happening by the end of it, and it is fine. You'll be writing a lot of code eventually in Rust, hopefully. And when you do, the compiler thankfully helps you out whenever you are dealing with lifetimes. So we'll see that very soon. So if you are not able to digest this in the first go, it is fine. You don't use lifetimes too much. Well, you do. It's a good idea for you to try to understand these, but if you don't, it's fine. You can just use the compiler errors to fix from time to time whenever you need lifetimes, but eventually try to, digest what this is doing. It takes a lot of time to understand why they are needed. A lot of times compiler will help you out and guide you in the right direction. So feel free to, try to digest it. We'll probably be discussing this for half an hour. If you don't understand it, it's fine. Don't stop your Rust journey just because of this. You can always come back to lifetimes in the future. The goal is that by the end of this section, you can understand the following syntax. The problem with Rust is what? Rust is highly verbose. Whenever you're writing the code, this is valid Rust code. It's God knows what it does right now. But the hope is by the end of this specific section, you're able to understand what this does. It looks like a function only, function longest with an announcement, but it uses some weird types of generics. One is a T generic, and God knows what this tick is. Then there is a function which takes 3 arguments, but again, the arguments are a little weird. It's not @stir. It's not @mutestir. What is it? The argument is @tick A. God knows what that is. Another argument is @tick A. Third argument is the generic. And we have probably, constrained the generic to have some sort of a trait bound. That's probably what the statement does, but we'll get to this whole syntax eventually. Cool. Before we get there into the complicated syntax, let's try to understand what are lifetimes through an example. This example has nothing to do with lifetimes. So this is just, simple practice problem for you. You can write it yourself by now. The statement says, write a function that takes 2 strings as an input and returns the bigger string amongst them. So you will take the ownership of both of these strings. As you can see, it's not @string I'm taking as an input. I'm literally taking ownership of both the strings. and I'm returning one of these strings back, either A or B, based on whichever is longest. Fairly simple code to write. This is how you would write this code. The function longest takes two strings as an input and returns a string. If a.length is greater than b.length, then return A, else return B. Write a function that takes two inputs and returns a bigger value. This is the function. This is me calling the function. I've defined the main function over here. It defines an str1 and str2. This one is small, this one is longer. I call longest str equal to longest of str1 and str2. And then I print this. The only extra thing, the only weird thing I've done here is I have defined longest str up here, and then I'm using it / defining it later on. I've declared the variable here. I'm actually assigning it a value over here. So that's the only weird thing that is happening over here. And this does compile. There's no, nothing wrong in this code for us to declare the variable first and assign it a value later on. Let's quickly try to run through this code. What happens when this code runs? Number one, longest underscore str is defined. We define this variable over here, does not have a value yet. Then str1 is defined. Then str2 is defined. Then we move both str1 and str2 over to the longest function. What happens when I call longest with str1 and str2? They both get moved to the longest function. Over here, we check, is a.length greater than b.length? If that is true, then we return A, else we return B. Which one of these two is bigger? str2 is bigger, which means B is going to be bigger. And hence, what gets returned from here? B gets returned. What gets stored in longest underscore str? str2 gets stored because str2 is longer than str1. So str2 moves back to the longest string variable. We print that over here, it is valid. And you can print longest underscore str over here, you're good to go. Like very simple code that we've written until now. But now let's change the syntax a bit. Again, to recap, this is the code that we have written. Nothing wrong in this code. A function called longest, and then we're calling this function with two strings, small and long. And then we're finally printing the longest string. Everything is good over here until I change the syntax a bit, and it looks something like this. Still nothing too problematic is happening. What have I done? I have just scoped str2 over here, and I'm calling the function from here, assigning longest str to it. So let's dry run through this code and see, does anything change or is everything exactly the same? This is valid code. This is valid syntax. There is nothing wrong over here. First, we define the longest underscore str variable. Then str1, which owns small, is defined. Then str2 is defined, which owns longer. And finally, both str1 and str2 get moved to the longest function, same as before. What does the longest function return? It returns you B, because B is the longest string. That gets moved back to this longest underscore str variable. So this longest underscore str variable now owns this value. This is the owner of it. And since longest underscore str was valid here, it is also going to be valid here. Its scope does not end over here. The scope of str2 ends, but str2 isn't even valid anymore. str2 has been moved to longest underscore str, which is why this is still valid code. Longest underscore str contains this string and owns this string. Whenever you finally print it, longest underscore str gets printed on the screen, which is, this variable over here. What we've done until now has nothing to do with lifetimes. Let me quickly code this up also. So if you want to, code this yourself, feel free to. There's nothing wrong in it. It will compile perfectly. Let me create str1 or, long, let's say answer equal to nothing. Just define the string, the first string called answer. Then let me first define a function called longest, which takes A, which is a string, and B, which is a string. Returns a string as well. If a.length is greater than b.length, return A, else return B. Something like this. This is the longest function over here. Now I define a variable called answer. It's just defined, not using it yet. Then I define str1 equal to str2 equal to longer, and then I call let answer equal to longest of str1 comma str2, and then I finally print the answer over here. This is the same code that I had written a while back. The same code I have written over here. I define a variable, I declare string1, string2, I call the longest function, ownership of both str1 and str2 gets moved over here, one of them gets returned, you print the final thing over here. If I run this, what gets printed on the screen? Longer gets printed on the screen. The code is perfectly fine. Even if I scope these two lines of code out, even though str2 is the longer string, which means answer is eventually pointing to longer, and str2 is sort of going out of scope here, still answer remains valid, because if you understand ownership by now, this should be fairly clear. Okay, str1 owns small, str2 owns longer string, both of them move over here, so A owns small, B owns longer, eventually B gets returned. So answer now owns this value called longer. When you move over here, then you can always print answer, because answer hasn't gone out of scope, and hence this longer variable is still valid. There is nothing wrong in the syntax that we have written over here. This code is perfect and it has nothing to do with lifetimes. But if we change the syntax of this longest function a bit, is when we will start to see problems, and then we'll try to see how lifetimes come into the picture to solve the problem. Cool. Hopefully this syntax is clear by now, nothing too weird done by us, and you can code this on your side. It works perfectly. What we have done until now has nothing to do with lifetimes. Let's change the function signature a bit, not too much, but a bit. I'm going to say that longest is now going to take 2 string slices as an input. It is not going to take ownership of the strings. It is just going to take 2 string slices as an input and return one of these string slices. So the code would change very little. Rather than writing string over here and here, I've written @stir. Rather than returning string from here, I've written @stir. And I call longest with string1 and string2. These are the 2 string with which I called longest. Do you think this code is valid? You might think it is. Let's see. Let me write the code over here. Let me replace all 3 of these with @stir. Let me replace the first one with the @str1 call, the second variable with an @str2 call. Do you think this works? Mostly looks fine, but there is a red squiggly here, and the red squiggly says missing lifetime specifier. Something related to lifetimes. We were supposed to learn about lifetimes, and finally we see a compilation error that is giving us a warning, or more specifically an error. This code will not compile. Why though? I haven't changed much. I just changed kr. Rather than using strings in this function, the function longest that I've defined, rather than using strings, I am using string slices. I am passing in string slices. I'm passing in references to a string. I'm getting back a reference to a string. Why do you think this is problematic? Can you guess? Who owns the value small over here? str1 does. Who owns the value longer over here? Small is owned by str1, longer is owned by str2. When you say answer equal to longest and pass in @stir1 and @stir2, even when this function is called, who owns small? It is str1. Who owns longer? It is str2. I am borrowing str1 and str2. I am not moving them. Their ownership isn't transfer, which is why when this function returns, longer is still owned by str2. Small is still owned by str1. And if I set answer to be the longest amongst these two, which means what is the return type? @stir, which means I set answer to either point to this or point to this. If answer points to this, then can I print answer over here? Should answer even be valid over here? No. Why? Because str2 moves out of scope over here. And what do the ownership rules say? They say if a variable that owns some value goes out of scope, the value is cleared from the heap. So if I set answer to be longest amongst these two, which of course the longest amongst these two is this guy, if answer points to this guy over here, then answer will be a dangling reference. It will refer to something in memory that has been already removed from memory. str2 goes out of scope over here. It is no longer valid after this. You can't use str2. It starts over here, starts from this brace, ends until this brace. Whenever str2 moves out of scope, the ownership rules say whatever value I own, I will remove that from the heap. This gets removed from the heap. Answer still points to that value on the heap, and hence this will be a dangling pointer. But as you can see, Rust doesn't let you compile this code only. Rust understands this. Rust knows okay, what you're trying to do is dangerous. Even if the string was small, AA, even if this string was small and this string was much longer, this is a longer string now, this is a smaller string. Even though answer will point to this guy, Rust compiler will still say, I don't know how. The compiler isn't supposed to look at the string and figure out how long this is. Compiler doesn't know. Compiler says here, you are using two strings as an input and you're returning them conditionally. You are in some conditions returning a pointer to A, other conditions returning a pointer to B. I don't know what the lifetime of this str1 variable is. I don't know what the lifetime of this str2 variable is. And hence I don't know how long will answer stay alive. It basically says, if I hover over this, it says missing lifetime specifier. This function's return type contains a borrowed value, but the signature does not say whether it's borrowed from A or B. It says it returns a borrowed value, but we don't know if the borrowed value came from A or from B. The problem is, as I said, this is memory unsafe code. In some cases it will work. If this string is longer, this string is shorter, then you don't have a dangling reference. But if this is the shorter string and this is the longer string, what would happen? str2 will get cleared from the heap over here. Answer will be a dangling reference to that. Hence, the Rust compiler says, okay, whatever you are taking as inputs, right? Whatever you are taking as inputs, tell me how is the output ka lifetime associated to the input ka lifetime. I repeat, the Rust compiler says, okay, this will have some lifetime. The lifetime, can you guess what the lifetime of str1 might be? It's basically everything from here to here. str1 is valid from here until here. So you can say the lifetime of str1 is from here to here. What is the lifetime of str2? The lifetime of str2 is from here until here. The Rust compiler is saying, these inputs that you have, you are conditionally returning either A or B. Tell me how does the return type of answer, whatever you are returning over here, how does it relate to the lifetime of this guy and this guy? It says, code to likh diya hai. You have written the code. Can you please tell me if this is, let's say, if A spans for 5 lines and B spans for the 3 lines, how long will the return value span for? 3 lines, right? If A, the first thing is valid for, let's say, 1, 2, 3, 4, 5, 6, 7, 8 lines. And the second B string that you're passing is valid from here, 1, 2, 3, 4, for 4 lines. How long can you say that the return type will be valid? The return type will be valid amongst the shorter of both of these, right? Answer will be valid up until here. It cannot be valid after that because the longest function might return stir2, which ends over here. Since stir2's lifetime ends over here, you have to say that answer ka lifetime also ends over here. So the Rust compiler is telling you, specify the lifetimes. Tell me if this is 8 lines longer, this is 4 lines longer, how long will the return type be? And the answer is the return type will be the union intersection of both of these. If this is the lifetime of the first one and this is the lifespan of the second one, then the lifespan of answer will be from here until here. It will just be the intersection of the first one and the second one after this value. Answer gets declared over here. Answer's lifespan ends over here. Even if longest function returns you this, still you have to say, the life of this answer variable needs to end over here because in some cases it will point to stir2 and stir2 ends over here. So the Rust compiler is telling us please specify a relationship between the lifespan of this guy, the lifespan of this guy, and the lifespan of the return type over here. This is where lifetimes come into the picture. Let's look at this function really quickly. Let's again summarize what the problem is. This is the function code that we have written. And if we try to compile it, what does it say? It says expected named lifetime parameter. When you write this code and try to compile it, it will give you this error over here. Expected name lifetime parameter. It will expect you to put some sort of lifespans over here and relate the lifespan of the input and the lifespan of the output. Can you look at the code and tell why the compiler complaining is a good thing? I hope you understand by now. I already explained it. Why is the compiler complaining a good thing? Because first this points to nothing. Then str1 owns the first string. Then str2 owns the second string. Then str1 and str2 get borrowed. They don't get moved. Then conditions check whether or not A is bigger or B is bigger. Then let's say B gets returned over here because B is the longest string. Then longest string, this variable over here, where does it point? It points to this guy right here. It is a string reference or a string slice to this variable. The longest string points to this guy on the heap. But str2 goes out of scope over here. I repeat, longest string is a string slice pointing to str2, and str2 goes out of scope and data gets removed from the heap. So this will get removed from the heap. Str2 goes out of scope, but this is still valid and this will still try to point to the same thing. This is why it is a good thing for the Rust compiler to complain. Of course, the smart folks at Rust understand this. They understood that this is a clear case of a dangling pointer. If you take two references and randomly return one of them, in some conditions you return this, in other conditions you return this, this will very clearly lead to a dangling pointer, or there is a case where this can lead to a dangling pointer, and hence this is already been covered by the folks at Rust. They say, if you're taking multiple references as an input, right? Tell me if this is X lines of, this guy spans X lines of code, this guy spans Y lines of code. How much does this guy span? What will be the lifetime of this specific guy? So that I know, how long should longest string also exist? It starts over here, but is it really valid after this? It isn't, because it is pointing to this thing over here, which ends right here. So this is why it asks you to specify the lifetime. Now let's look at the syntax of specifying the lifetimes of a variable. So this is what the current architecture looks like. That longest stir is going to be a dangling pointer, which is why the Rust compiler is not compiling the code. It is not letting you run it. It is telling you I expect a named lifetime parameter. How do you fix the error? By fixing this thing over here. How do you do that? And the answer is this. Now I am going to boggle your head a bit. I am going to introduce something called a generic lifetime annotation. I repeat, what am I introducing? I am introducing something called generic lifetime annotation. This thing basically says, remember I wrote lines of code over here. I said this spans 3 lines of code, this spans 5 lines of code, this spans 3 lines of code. Something similar. It says, I am going to first define a generic over here, just like we have defined generics like T in the past. It defines a generic tick A. Tick is nothing but single quote. So single quote A. It says this is a generic argument, tick A. And first ka lifespan is tick A. It says the lifetime of the first variable over here is tick A. The lifetime of the second reference over here is also tick A. And the lifetime of the return value here also is tick A. Very weird thing it did over here. Why did it do this? It should have done something like this. The lifespan of U is line 4 to line, let's say 12. And it should have said here lifespan of this is line 6 to line 8. That is what this is the first guy's lifespan. this is the second guy's lifespan. It should have said something like this. And it should have said कि यार return type का lifespan will again be line 8 to line 9, something like this. You are right. This is, would have been great if we could have specified lifetimes like this. But how do you specify lifetimes? How do you specify the relationships between inputs and outputs? Because, number one, you don't know str1 will be defined just over here. You might have the longest function call someplace else with a different argument, or, with a different str1 and str2. So you can't just write lines of code over here. What you write is, number one, here I'm going to take a generic argument, a lifetime generic annotation. What am I taking? A lifetime generic annotation. This is similar to a generic like T, only it looks a little different. It is prefixed with tick. It's a lifetime and not a normal generic. And we say, if, now I'm going to confuse a little because this is also a, this is also a. I should change the name of these variables to num1 or str1, str2, there we go. Yeah. I say that str1, if str1 has a lifespan of tick a and str2 also has a lifespan of tick a, and the return type is also going to have a lifespan of tick a. Now, it compiles, even though this is very confusing what I've written over here. We'll try to understand what this is. First, let me see what this says. Yeah, okay, this is much better. Yeah, I've written this function, which is not throwing any errors at me anymore. Looks pretty similar and, doesn't look pretty, but it's trying to do something. Let's try to see what it does. It says, here I'm defining a generic lifetime argument, generic lifetime annotation called tick a. And since I've given tick a to str1, I've said str1 maybe lives as long as tick a. How long does str1 live from? It lives from here until here. And str2 also it assigned it as tick a. It basically means, does it mean they both have the same lifespan? No. str1 has lifespan from here to here. str2 has lifespan from here to here. It means the return type ka value is also tick a, which means it is the smallest amongst these two. It is the union intersection. It is the intersection of these two, which is going to be the lifespan of this thing. I know, it looks like iska lifespan A hai, iska lifespan is A, the return type lifespan is also A. But this is not what these arguments mean. These arguments mean all three of these are related. Whatever is the intersection of both of these lifespans is what is the lifespan of this guy. So what is the lifespan of the first guy? Here to here. What is here to here? What is the lifetime of the second guy? Here to here. So it says the return type is the intersection of both of these, which is going to be, here to here. And hence, we know that the answer variable ka lifespan is from here to here, or you can say from here to here. And hence the Rust compiler is now, complaining at us. It's saying str2 does not live long enough. If I try to compile this code, it says, if you are trying to print answer over here, then, str2 is not living long enough. And, this str2 variable, you said, if the lifespan of the first thing is tick a, the lifespan of the second thing is tick a, their intersection ends over here. str2 ends over here. Hence, you can't use answer after this. Answer ka lifespan, answer's lifetime ends over here. You cannot use it afterward, which makes sense, right? Forget the syntax for a moment. It does make sense. If you take two strings as an input and you could conditionally return either one of these, then of course, whichever is the shortest lifespan, if the first one is valid from here to here, but the second one is only valid from here to here, then the answer should only be valid from here to here only. It should be valid in the intersection of both of these, because in some cases this would get returned, in other cases this would get returned. So their intersection is what needs to be the lifespan of answer. That you understand that theoretically, but to be able to communicate that to the compiler, you use lifetimes. To communicate to the compiler, here I am taking two things as an input and their intersection is what the return type's lifetime is. There, the shortest of these two, or the time until both of them are valid is how long the return type is valid, is represented like this. Even though it might look like it says your lifetime and your lifetime is the same, and the same is the lifetime of the life of the return value. That is not true. This syntax does not mean that. This syntax does not mean the first string is valid for tick a lifetime and second string is valid for tick a lifetime, and then the third string is also valid for tick a lifetime. No, you can't define the lifetime over here and expect str1 to change its lifetime. str1 and str2, you are both going to have the same lifetime. You can't force that. str1 will have its own lifetime. str2 will have its own lifetime from here to here. The return type's lifetime is जहाँ पे भी ये दोनों valid है, wherever both of these are valid is my lifetime. Another way to look at this is I'm just spending a lot of time here because this is what lifetimes are, but never are people, including me, able to digest it. But here is another way to look at it. Okay, we said str1 is lifetime is a and str2's lifetime is a. We said their lifetime is the same. So we sort of forced a to be the intersection of these two. We said here str1's lifetime is going to be a, str2's lifetime is going to be a, and that is only possible if a starts from here and ends over here. I repeat, str1's lifetime can be a, str2's lifetime can be a. Their lifetime can be the same only during this much section of the code, because str1 might be valid from here to here, str2 isn't. So a sort of forces to become this line of code, this line of code, this line of code, this line of code. A sort of forces to be valid in just this much scope. And since we say the return type is also a, the return type also becomes valid in only this much scope. You specify that to the compiler. You tell the compiler कि यार जहाँ पे ये दोनों valid हैं, the space where str1 and str2 are valid is where the return type will be valid. You are forcing that to the compiler. You're telling that to the compiler, even though str1 is valid for much more. When you specify the lifetime to be the same for both the arguments, you force the compiler to think, okay, whatever is the intersection of both of them, that is what a is. So a is valid from 6 to 9. That's what both the arguments are. And the return type, since we have written TK over here, the return type also remains the same. Cool. That is how lifetimes work. Let's look at a pretty visualization if it, helps you understand it a little bit better. What we've written over here is a lifetime generic annotation, or this tick a over here. It's very similar to a generic that we've seen until now. And these three arguments that we write, at tick a stir, at tick a stir, at tick a stir, describe a relationship between the lifetimes of the input arguments and the output arguments. They define a relationship between them. They don't say this and this are equal. They say wherever these two are equal, that is going to be annotated as a, and that is what is the return type of this string variable as well. Now, if you look at it, it says that the return type will be valid as long as both the arguments are valid. As long as first and second, both of these values arguments are valid, is how long the return type of this variable is going to be valid as well. Or more technically, the shorter lifetime is what the return type will have. If there are two arguments and they have two lifetimes, the shorter of those, or the intersection of those, is what the return type of the function is going to be. Let's look at some official Rust book blocks. If that helps you digest this a little bit better. Lifetime annotations in function signatures. To use lifetime annotations in function signatures, we need to declare the generic lifetime parameters inside the angle brackets between the function name and the parameter list, just like we did for a generic type parameters. This thing right here. We want the signature to express the following constraint. The returned reference will be valid as long as both the parameters are valid. We want the relationship to say the returned reference will be valid as long as both the parameters are valid. This is the relationship between lifetimes of the parameter and the return value. This is the relationship between the lifetimes of the parameters and the lifetime of the return value. There is a relationship between these two and the final guy. We'll have the lifetime tick a and add it to each reference as shown in this figure right here. Again, to recap, this figure right here does not say that the lifetime of this and this need to be the same and same will be the lifetime of the return guy. No, they say that whatever is the intersection of these lifetimes is the return type of the specific function. Cool. Now, if you run this function, it gives you a better error. It says, okay, you are trying to print answer, but str2 doesn't live long enough. What does it say? str2 doesn't live long enough. It gets finished over here. It gets cleaned up over here. Its owner moves out of scope over here, and hence you can't use answer after this. Even though if this was a longer string and this is the shorter string, str1 is what comes over here. It won't be a dangling reference. Still, the Rust compiler won't let you do it. And if this was small and this was bigger, in that case though, great that the Rust compiler doesn't let us do it, because if it did, str2 would have gone out of scope over here and we would be pointing to str2, which points to nothing at the moment. Cool. Hopefully that's clear, but maybe not. Lifetimes take a long time. Lifetimes take a long time, man. Little bit of philosophy in the middle of a Rust class. Cool. Now if you run the code, it tells you, something similar, or tells you a better error, which is the code that you've written is wrong. It will lead to a dangling error, so I'm not letting you compile it. Alrighty. Cool. Structs with lifetime. That's it. That's it for lifetimes as a functional argument. There's one more place where you'll see lifetimes, which is if you ever define a struct which has references. We haven't done that yet. So let's do that, especially if you're writing, anchor contracts in the future, which is going to be one use case, at least for the Web3 people over here. Then you will see this, whenever you're defining a struct, you have references and hence you need to describe lifetimes. Let's see what I mean by that. I'm saying a few things here. Let's understand what that means with, very basic examples. Until now, we haven't used references inside a struct. Let's try that. We have not done this. We have said name equal to string. We have never said name points to @star. This is the first time we're doing that. Let's see, does anything change? Or, does the things that we've done until now, are they good enough? I define a function main where I say first name is string : from 𝗟𝗶𝗸𝗀. I describe user as a user struct with name @first_name. And then finally I print user.name on the screen. Do you think this compiles? The answer is no. It fails with an error. Let's try it out. Let's quickly write the code over here. Let name equal to string from 𝗟𝗶𝗸𝗀 struct user name stir let user equal to user name. And let's try to print the user's name. So print ln user.name. Notice already you have a red squiggly over here. What does it say? Missing lifetime specifier. 𝗟𝗶𝗸𝗀 lifetimes over here as well. Yes. Why? Because how will you know how long is user going to be valid? If user is a struct which has a reference inside, shouldn't there be a relationship between the lifetime of user and the lifetime of the variables that you have inside that exist on the heap? If you ever have references over here, then the reference of user is sort of tied to the reference of this, right? If name goes out of scope, then user should also go out of scope. User should also become invalid, which is why you have to describe a relationship over here between the lifetime of the struct and the lifetime of any variable that is a reference. Let's see that more practically. Structs with lifetimes. This is what we defined over here. This is the final solution, which is, whenever you're defining a struct, again add a generic lifetime annotation over here and say that name is going to be valid as long as, if the lifetime of name is going to be tick a, then the life type of user is also going to be _k. Again, what are we doing? We're describing a relationship between the lifetime of the name variable over here and the lifetime of the user struct over here, so that the Rust compiler knows whenever name goes out of scope, so does user. We have described a relationship between the lifetime of the struct and the lifetime of the name variable over here. Let's try to code that. Right now there is a compilation error. What does the error say? It says missing lifetime specifier. Consider introducing a name like a lifetime parameter _k. So as I said, the Rust compiler will, sort of help you out from time to time and, tell you where to introduce what types of lifetimes. If you don't understand them, unless you're writing a very, weird use case, you can just follow the compiler and, put the ticks in the right place, forget about what's happening. It's very hard to know what lifetimes are, trying to achieve without you thinking 100 times over it and finally realizing, that is why, lifetimes were introduced, or that is why they make sense. Specifically here, if let's do something like this, let user, and let's say I define the name over here, and over here I assign the value to the user variable. Now if I try to use user later on, it tells me, okay, name does not live long enough. That is the whole point of, specifying _a over here. Okay, the user's lifetime gets tied to the lifetime of the name, and since the lifetime of name ends over here, you can't use user after it. If you try to use it, firstly, it will be a dangling pointer, which is great. The compiler is not letting you compile code. This is bad code, and this might compile in a language like C. Let's say, you have user which sort of points to something on the heap, but that thing gets cleared over here, and you have a dangling pointer. Rust doesn't let you compile it only. Rust says, as long as you've defined the user struct correctly, as long as you've tied the lifetime of the user struct to the lifetime of the name variable, then as long as the name variable becomes invalid, which is exactly what happens over here, the name variable becomes invalid over here and does not exist on the heap anymore, the Rust compiler says you can't use user.name over here. If you comment this out, then it works, then it compiles correctly. But if you try to use user after it, even though user should be valid, it isn't, because its lifetime gets attached to the lifetime of this name variable over here, which ends right here. Cool. That is how you add lifetimes to structs, and you only need them if you're using a variable that's that exists on the heap. If you're using a reference inside a struct, is the better way to put it. All right. Why do you need structs with references to have a lifetime parameter? So we know how long the struct can live, which the answer over here was as long as the name variable is valid. Cool. Here is another example where we tie the lifetime or the lifetime of the user variable to both of these A and B, and if you try to write the same code where the first name is defined outside, last name is defined inside, try to create a user variable which points to first name and last name, where last name is defined over here, you will not be able to use user over here. If you try to use it, it'll pretty much throw a similar error at your face. Cool. This code doesn't really compile, exactly what you said, because last name does not live long enough. Last name, which is declared over here, does not live long enough to have a value over here, which is why the Rust compiler sort of does not let you compile this code, which is good. Cool. Do we now understand this code that I said initially that you'll understand? It's just a function called longest with announcement, which takes two generic arguments, one of them being a lifetime argument, one of them being a normal generic argument. It says X is going to be _a*, Y is going to be _a*, and the rest of the code here is just the same. So X and Y are two arguments attached to this lifetime. We have a very similar logic to return X or Y based on whatever is longer. The only extra thing is we take a third thing as an input, announcement, which is something that should implement the display trait. I repeat, there is this inbuilt trait in Rust called display. Whenever you called println with a dynamic argument like this, that dynamic argument should implement the display trait. That's exactly what I was showing a while back initially when I said some things when you try to print, you can print like this. comma, whatever the name of the variable is. You can put, open curly brace, closing curly brace. Sometimes you need to put open curly brace and, semicolon question mark and closing curly brace, because some structs implement the debug trait, some structs implement the display trait, and if a struct does implement the display trait, then you can just print it using this println macro, and that is what this constraint over here says. It says, announcement, whatever you're taking as an input over here, which let's is a string. String does implement the display trait, which is why you can pass the third argument as a string over here, and that string is what gets printed on the screen over here. Hopefully this syntax, even though it is very jarring, but once you understand at least the first part, the thing that we discussed initially, let me show you that. If you understand this code right here, which takes two references as an input, a string reference A and a string reference B, and uses this tick A syntax and the lifetime generic argument or annotation over here. If you understand this function, then what we're doing, if you understand this function, then what we're doing in that slide is just a third argument over here. The third argument itself is a generic, which is why we, along with the tick A, had to introduce a T generic over here. So if I go back to this guy right here, you will notice, tick A and T are the two generics that we have. Tick A is associated with the first two arguments, and then we have a third argument which is used to announce. Hence the function is called longest with an announcement over here. Cool. Alrighty, let's do a checkpoint, boys and girls. We have understood collections and vectors, iterators, hash maps, strings and string slices, generics, traits, and lifetimes. What's left is macros and multi-threading. Futures and async await have definitely been postponed. It's 4:35 a.m. So I think, and I also think generally, this deserves a video of its own. So let's quickly understand multi-threading next. Then we'll understand macros. Then we will call it. Let's get into the next section, multi-threading. All right, let's understand multi-threading next. Again, a language agnostic concept. Java has this concept of thread pools, if you might have heard of it. Golang has this concept of Go routines, which I can't really say they're the same as threads. So probably not the best comparison here. But if you have seen thread pools in Java, they're very similar to, how you can create threads in Rust. There's this section called fearless concurrency in the Rust book, which covers a bunch of things. Some of these things are important for us to know eventually, especially when we reach the async Rust section. We'll probably learn more about, shared state concurrency. What we're focusing on right now is 16.1 and 16.2, using threads to run code simultaneously, and then using message parsing to transfer data between various threads. Let's get right into it. The foundation of multi-threading is this. Okay, most machines that you run today are, multi-core machines. If I have a Mac, my Mac has a 10-core machine, which means I have 10 CPUs on my machine. And hence when I'm running some Rust code, it's a good idea for me to somehow parallelize my code so that I can use the complete power of my machine. In most operating systems, an executed program's code runs in a process, and other operating system will manage the multiple process at once. So what does it say? In most current operating systems, an executed program's code is run in a process, and the operating system will manage multiple processes at one. That makes a lot of sense. You might have Google Chrome running on your machine. You might have OBS running on your machine. You might have VS Code running on your machine. All of these are separate processes, and your operating system makes sure it is running multiple processes at once. Within a program, you can have independent parts that run simultaneously. Within the same program, you might have multiple things that are running at the same time. This feature that can run these independent parts is what's called a thread. So a single process can have, various threads, thread 1, thread 2, thread 2, 3. And why would you want to do that? So that on that single Rust process, let's say, you can use this core for running some things on thread 1, this core for running some things on thread 2, this core for running some things on thread 3. The reason threads are useful, or you might want to use threads, is because they let you run code parallelly and simultaneously. Basically, these are like two things that you need to know the difference between concurrency and parallelism. There is a very nice video, I'll probably link in the description, that will take you through the difference. Specifically, the thing that we're learning today or hoping to learn right now is parallelism, trying to run multiple things at the same time, one on core 1, one on core 2, one on core 3. This feature that lets you run these independent parts is called threads. For example, a web server could have multiple threads so that it could respond to more than one requests at the same time. It can respond to, let's say you have 100 people on your website. It's a Rust backend server that you have. You can respond to more than one request, more specifically, 10 requests on this 10 core machine at the same time. If you use threads, that will not happen if you are not using threads. Until now, all the code that we've written runs on a single core. We have not spawned more threads until now. All the Rust code we've written, even though Rust is a multi-threaded language, the code that we've written only runs on one of these cores. To make sure you can parallelize, you can run multiple code snippets together, you can use what's called the thread struct over here that the standard library returns. Let's see how that works. You first import thread from the standard library. We have also imported time just to let's see where this is used, just to make the thread sleep for a while. And what we do over here is we spawn a new thread. We say the function main is going to spawn a new thread that is going to run this code. We say here we want to print this high number X from the spawned thread. We want to print this on the screen, and then we want to make the thread sleep for just 1 millisecond. Okay, this is one thread we want to run. This is the spawned thread, and this of course is the main thread that our process has, where we again iterate from 1 to 5 and print high number this thing from the main thread. So we're printing some values on the main thread here. We have also spawned a separate thread where we're printing a few values. What do you think the final output of this code would be? Would these 5 get printed first and then these 5 get printed? Would these 5 get printed first, then these 5 get printed? Will they interleave amongst each other? Let's see. The goal is, since I'm on a 10 core machine, this thread can actually run on this core. This second main thread can run on another core. That way, they're both running parallelly, which means most probably I should see this and this statement print by interleaving amongst each other. What does interleaving mean? First a few of them get printed from here, then a few get printed from here, then a few get printed from here, so on and so forth. The main thread, let's say, runs on core number 1. The spawn thread runs on core number 2. If you look at the final output, it does look like this. It says high number 1 from main thread, then a few things from the spawn thread, then a few things from the main thread, then a few things from the spawn thread. So yes, they interleave amongst each other. And why is that happening? Because both the threads are running parallelly. Awaiting the thread to finish before running the iteration on the main thread. What if I change the code a little bit? I say, ignore this some variable. I don't think it's being used anywhere. Yeah, just feel free to ignore this. I say I'm going to spawn a thread, and whatever value this thread returns, I'm storing in this variable called handle. I'm storing this in a variable called handle. You can call it anything, but handle is popularly used. And I'm going to wait for handle to join, which means I'm going to wait for this thread to finish. Only when the thread finishes will I proceed to run this for loop over here. So what does handle.join.unwrap do? We'll come to what unwrap is, but handle.join lets you await the thread to finish before running the iteration on the main thread. This is the main thread. You are spawning a thread and running some iterations over here. And we wait for this thread to finish. We wait the spawned thread to finish before running the main thread. This is the things that happen on the main thread. We first wait for this to happen. Only when this happens, we wait for it, and then this thing, runs. The main thread actually runs. So we're pretty much waiting for this thread to run over here. Can you guess what the output would be in this case? I would first run this specific thread. All the outputs over here are from the spawned thread. And then eventually after, we're done waiting for it, this thread sort of exits, is when we move on to the final for loop and, the main thread runs over here. Let's try to code this really quickly. What does the code say? The code says, I'm going to spawn a new thread, which will take a closure as an input. Closure, as we've discussed before, is very similar to a function. And what am I doing here? For I in 0 to 5, I'm going to print I from spawned thread, I. And then I'm going to, let's say, run the same for loop over here. Hi from main thread. I over here. All right. Hopefully this works as expected. Let's see. I don't have a handle right now, so it should print them in a very random fashion. They should interleave. Sometimes this should run, sometimes this should run. It says hi from main thread 5 times. It never spawns this thread over here. Why is that? What am I missing? Thread. Semicolon. It could be, and I could be wrong on this, but let's see. Yeah, there you go. Interesting. Let me increase the number of iterations that happen. So the thing that was happening was the thread got spawned, but the program exited before that. I repeat, the thread got spawned. It was supposed to run the 5 iterations, but before it was able to run the first iteration, my program has exited. What I can do is I can increase the number of iterations in the second thread. That way, hopefully the program runs for longer. Or I just called handle.join over here, which will make sure we wait until the specific thread over here finishes to complete. So let me run this one more time. Let's see if they get interleaved. They still don't get interleaved. Same. Let's make this 500 or 5,000. Okay, there you go. If I make it really big, then it happens. Make it small, it doesn't happen. Let me run it again. There you go. I want to see some interleaving. There you go. Sort of. I don't see any clear interleaving over here. That could all. All right, let's do this. Just to confirm that we are actually straining 2 CPUs and making sure this is running on one CPU and this is running on another CPU. I'm going to print a lot of values here. I'm going to print a lot of values here. So we'll probably see some interleaving to begin with. And we'll also confirm are 2 CPUs actually running or not. So if I run cargo run now, you'll see a bunch of prints. You see a bunch of interleaving. Sometimes you see main thread, sometimes you see spawn thread. But the biggest thing I want to see is if I run htop, do I see a Rust process taking 200% of the CPU? And the answer is yes. If you look at this process right here, it takes 233% of the CPU, which makes sense. Something like, I would have expected it to be closer to 200. I don't know where the extra 30% is coming from. If I had to guess, you have no guesses. But one CPU is completely being used by one thread. Other CPU is completely being used by another thread. That is why, this is closer to 200%. That means, 2 CPUs. There you go. All right. Wow, that took a long time. So apparently the problem was with htop. Let me show you one more time. I have a thread that spawns and does something, fairly generic, doesn't do anything, has 2 for loops and inside the for loop, I just increase the value of this C variable and then decrease the value so that it doesn't become very big. It just remains at 0. The same thing I do over here. So this is the main thread. This is the spawn thread. And when I run this, if you look at my terminal, I'm running it over here. And if you look at the CPU usage, the CPU usage is 198%, very close to 200%, because while one thread is working very diligently trying to calculate the value of C, so is the other main thread. And hence, the CPU usage is 200% or 2 CPUs. If I add another spawn over here that does something similar, then can you guess what the CPU usage should be? It will spike up to 300% or 3 CPUs. At some point, of course, I have a 10 core machine, so I can't just keep spinning threads that are infinitely doing CPU intensive tasks. But at least this much I can do. The first thread is running an infinite task, a very CPU intensive task. So is the second thread, and so is the main thread. And you can confirm that we're able to almost allocate 3 CPUs to our Rust process because my machine is very free right now. If my machine was running thousands of processes, a GTA game, very expensive game, whatever, then of course even this Rust process wouldn't have been able to get 3 CPUs completely. Right now my machine is a little idle, which is why all 3 CPUs are completely dedicated over here. But notice, unless I spawn extra threads, if I write very simple code like this, then I will not use more than 1 CPU. Even though Rust is, a program or a language that is multi-threaded, unless I explicitly write multi-threaded code, my Rust program will only use 100% of the CPU, not more than that. So that is why you need to, sort of spawn extra threads for expensive processes, for handling requests, things like these. Cool. Hopefully that's clear. Let's move on. Hopefully you understand, handle.join as well. Okay. I wait for this thread to, complete, and only then does the control reach over here. Moving on, using the move closures with threads. We'll often use the move keyword with closures passed to thread.spawn because the closure will then take ownership of the values it uses from the environment, thus transferring the ownership of those values from one thread to another. Extremely long statement, went right over your head. That is totally fine. Let's try to look at an example and try to understand it. Let's say I have a main function over here where I define a variable called v, which is a vector. And then inside the thread that I'm spawning, I try to use this v variable. I try to print this v variable over here. Do you think this code runs or not? Do you think this compiles, or does it throw an error? Let's try to code and understand. Let me open Visual Studio Code over here. And let's try to write this code that I just wrote, which is I spawn a thread, and inside the thread I try to use a vector. Let v equal to vec 1, 2, 3. And here in the spawned thread, I do nothing but print the vector v over here. Can you notice it has a red squiggly over here? Why would you think that is the case? Why would there be a red squiggly over here? Why can't this thread use the v variable? Let me make this a little more, easy to comprehend. What if we had, some code that looks something like this? I define an x variable over here, and then inside a scope, I define the v variable and I spawn the thread. What would happen? As soon as the control reaches, let's say this line of code where I'm printing x, v will go out of scope, and we are not sure the thread that you are spawning might still be trying to access v. So this is a dangling pointer. The v variable that is defined over here gets cleaned up when its scope ends, and hence we don't know when the thread's spawned code will run. We don't know when this code will run. First this code might run, and then this code might run. If this code runs first, means v has become invalid, and hence whenever you are trying to use a value from here inside a thread, the compiler will tell you to force the closure to take ownership of v, use the move keyword over here. It says, please move the ownership of v to this closure by making this a move closure. What this will do is you cannot use v anymore. V gets moved over to the thread, and that is fine because this thread is the only thing that needs V right now. 𝗟𝗶𝗸𝗀, what if both of them need it? Then you do something else. We'll get to that eventually. But right now, if you are using V, then you have to move its ownership over to the thread, and this is how you do it. This is what a move closure is. Now you see no compilation errors. If I run this code, you will see it works as expected. And what did we learn from this slide? It is that whenever you're trying to use these values inside a spawned thread, you're trying to use a value from the environment, you have to add the move keyword over here to move its ownership inside the thread. This code doesn't compile because we could go out of scope before the thread ends. Whoopsie daisy, sorry about that. What does it say? It says we could go out of scope before the thread starts. It might have, in this code, it's a little hard to tell, but what if the control reaches here, then here, and this code, the method won't happen practically because you're waiting for the thread to end before the main function ends. But you get the idea. In this code that I had written, we will go out of scope, or we may go out of scope before this line of code runs, which is why you use the move keyword to move V to the spawned thread. You add move over here to move this value to the spawned thread, and now you can do whatever with it. You of course cannot use V outside anymore. Cool. That is all about multi-threading and how you can move variables inside a thread. One more important concept when it comes to multi-threading is message passing, which, as the name suggests, is how can you pass messages, pass data between two threads. You might say, 𝗟𝗶𝗸𝗀, we just pass data from here to here. Yes, but what if you want to pass data from here back to here? How can you pass data from a spawned thread over to the main thread? That is what we'll discuss next when we understand message passing. All right, let's understand about message passing next. What is message passing? It lets threads communicate with each other. It lets threads transfer data from one thread to another. A very common example of this that we'll be building very soon would be, if I ask you to find the sum of 1 to, let's say, 10⁻⁹, it might be a good idea for you to delegate this task to various threads. Okay, bhai, you find the sum from 1 to 10⁸. You find the sum from 10⁸ to 2 into 10⁸. You find the sum of 2 into 10⁸ to 3 into 10⁸, so on and so forth. You have 10 threads who perform all of this. Eventually, you join all of this data to find the net sum. That way, you delegate this very heavy task over to 10 different CPUs. That is what one use case that you can build. If you have message passing, you will need these cores to calculate the work and then eventually return this back to the main thread. How can you do that is what we're understanding here. One increasingly popular approach to ensuring safe concurrency, let me just zoom in here a little bit. One increasingly popular approach to ensuring safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here's the ideal slogan from the Golang language documentation: do not communicate by sharing memory, instead share memory by communicating. Even though in case of Rust, you do communicate by sharing memory as well. We'll be coming to that eventually. To accomplish message sending concurrency, Rust standard library provides an implementation of channels. A channel is a great programming concept by which data is sent from one thread to another. So what are we going to learn about? We're going to learn about channels that let us transfer data from one thread to another. What is the use case? One common, use case, one place I've seen message passing a lot is you have one thread that is constantly reading a stream of data from Redis, and then, it's passing it over to another thread that is actually processing the stream. A channel has two halves, a transmitter and a receiver. Basically, whenever we create this channel, we will be creating a transmitter and a receiver. The transmitter half is the upstream location where you put the rubber ducks in the river. Wow, it's like quite an example they've taken. They're basically saying you have a transmitter, you have a receiver, and you send some data from the transmitter. That data arrives in the receiver finally. And the receiver half is where the rubber duck ends up downstream. Basically means, data flows from the transmitter over to the receiver. One part of your code calls methods on the transmitter with the data that you want to send, and another part checks the receiving end for arriving messages. A channel is said to be closed if either the transmitter or the receiver go out of scope. Let's try to see this in action. Let's try to create a channel and let's try to transfer data from one thread to another. The way to initialize a channel is by using this specific struct called MPSC. It stands for multiple producers, single consumer. I repeat, what does it stand for? Okay, there is a single consumer. Most probably you consume all the messages in the main thread, but you can have multiple producers. You can have one thread producing to it. You can have another thread that, produces to the same consumer. So what does MPSC stand for? It stands for multiple producers, single consumer. We create a new transmitter and a receiver from it. The transmitter gets moved over to the first thread where I define a variable called hi, or a variable called val, which is a string. And then I transfer over that string by calling tx.send. Ignore again what .unwrap is, or I'm happy to share what this means. tx.send will send over this data from the channel. And how is this data received on the channel? The data is received in the main thread by calling rx.recv.unwrap, which again we'll understand what unwrap here and over here means. Finally, we print the received value. Let's see, can we do very basic message passing from one thread to another? Let me create a new channel. Let transmitter and receiver is equal to MPSC channel, and then let me spawn a new thread where I move the transmitter and I do a transmitter.send a new string called hello world. One thing I will have to do here is put a semicolon here and here. Notice, a warning over here, a very big yellow squiggly line. We'll come to what that is and why that line goes away if I call .unwrap over here. If I call .unwrap, the yellow squiggly goes. If I don't call unwrap, there's a yellow warning over here. We'll come to what that is. How do you receive it? The receiver dot receive, let value equal to receiver dot receive. What is the type of value? The type of value is a result. How can you destructure a result? You can either do pattern matching that we have discussed many times now. If there is a value that is returned from here, then you print the value. Or if there is no value that is returned from here, then you simply, let's say, print error while reading the data. So this works as well. Notice the code that I have written is slightly different from the code that's written over here where I unwrap the values. Can you now guess what unwrap over here means and unwrap over here means? Unwrapping basically means whenever you have a result and it will return an error. Okay, this is the only branch it will take, or you don't care. If it does not take this branch, if there was an error, I'm okay with the thread panicking. Then you can simply unwrap that value. What does unwrapping do? As the name suggests, you unwrap it, you assume / hope that this is the variant that was returned. But if an error variant is returned from this specific result, then the thread starts to panic and your execution of your program stops right there. So this is anti-pattern. You should not have unwraps in your code base. You should have pattern matches like this. If there is an error, you should do something else. If there is an error, you should catch the error, print the error, log the error. You shouldn't unwrap results ever, because this will stop the execution of your program. It will panic the thread over here if there is ever an error. For us, we don't care right now, which is why we're just unwrapping the value. And let's say, printing the value as well. But the same thing happens over here. This returns, if you look at the return value of tx.send, this might also return in an error. Let's say for some reason you're not able to send data. Then, if you look at the return value x over here, it is again a result, which is why if you want, you can unwrap the result and, hope that this always returns you the right value. If it does not, then the thread will panic. What was the warning over here? If I remove it, it says unused result that must be used. It says this is returning a result to you. You are not using it. You don't care about its return value. So that is why if you call an unwrap on it, then the warning goes away. Okay, you are assuming that it is going to return you a value. You're unwrapping the value and doing something with it, which in our case we're not doing anything with it. Anyways, it doesn't return you anything. If you look at the type of X, it's an empty tuple or an empty object over here, which is why unwrapping doesn't return anything. Specifically, whenever you do tx.send, it returns a result, but the type of the result is an empty an empty value, which is why it doesn't matter what this X is. Even if you print it, it pretty much has no value in there. Versus what will value over here be? You're passing in a string from here. So, you're going to receive a string over here. Let's see if that happens. Let's see if from this spawned thread, I was able to pass data over to the main thread. If I run cargo run, what gets printed on the screen? Hello world gets printed, which means this hello world that I'm sending from this thread is able to reach the other thread over here. I'm able to print it. So do we understand MPSCs, multiple producers, single consumers? How can you take data from one thread and pass it out to another thread? Now comes the assignment for today. The assignment is, can you write the code that finds the sum from 1 to 10⁸. You might write a for loop, but no, we have to do something extra. What is the extra thing we have to do? We have to delegate this calculation over to various cores. We have to write multi-threaded code so that there are, let's say, 6 threads or 10 threads that are running that are partially solving this problem. And then eventually you're joining the results from all of them. You're not calculating this result on a single thread. Cool. Use threads to make sure that you use all the cores of your machine. Do not run this very expensive or mildly expensive task on a single core. Cool. Remember, the name says multiple producers, single consumers. If you have multiple threads, from every thread you can produce some value. So here is some test code where if you want, if you see over here, let's see which line of code is this. Thread.spawn. There you go. You can actually clone a producer, and before you pass it to a thread. That is how you can have multiple producers and a single consumer. This is probably like too long of a code for you to look at. So let me show you the final result over here. The way we have written the logic to find the sum from 1 to 10⁸ is by spawning, let's say, 10 threads, because I'm on a 10 core machine. I spawned 10 threads and I delegated this task to all 10 of them. I said, number 1, I'm creating a channel. This is the producer, this is the consumer. And 10 times, I repeat, for I equal to 1 to 10 or 0 to 10, I'm first going to create a fresh producer. I say let producer equal to tx.clone. This will create a new producer. It's multiple producers, single consumer. I'm creating one of many such producers over here. I create a new producer. I move this producer over to the thread that I'm spawning. I'm spawning 10 threads. For every iteration over here, I create a fresh producer. I move the producer over to the thread. What is happening inside the thread? Inside the thread, I initialize answer to be 0. Then I iterate from j in 0 to 10⁷. And I say answer equal to answer plus I into 10⁷ plus j. Can you understand this math over here? Maybe not. The math over here will basically, when I is 0, it will find the sum from 0 to 10⁷. When I is 1, then it will find the sum from 10⁷ to 10⁷ into 2. When I is 2, it will find the sum from 10⁷ into 2 to 10⁷ into 3, so on and so forth. That is what, all of these threads over here are doing. They are slowly calculating the sum, from we have just broken down the problem into 10 smaller problems, and each one of these threads is solving the smaller problem over here. Once it solves the problem, once it has the answer for it, it will send the answer via the producer. And all 10 of these threads are going to do the same thing, which is find the specific problem that they are solving. Once they're done solving this problem, they're sending the result over from the producer over where to this consumer. What have we written over here? Here we say let mute final answer, answer equal to 0. And then for val in rx, this is another way to iterate over every value that you're receiving from a transmitter. For val in rx, while you're receiving values from various transmitters, answer equal to answer plus val. Whatever value gets pushed from here, I'm going to add it to this final answer. The first one will return me the sum from 0 to 10⁷. The second one will return me the sum from 10⁷ to 2 into 10⁷. I keep adding all of them up to eventually get the final answer, which is going to be the sum from 0 to 10⁸. Is that easy to understand? Does this code, is it comprehensible? Can you write this code? Let me quickly write it on our side as well. What is the code that we're writing? We have a producer and a consumer, and we're going to spawn 10 threads. So for I in 0.10. Sorry about that. The recording ended for a bit. What I was doing was I was spawning a thread 10 times. I'm first creating a producer. To repeat, we have multiple producers, single consumer. To create a new producer, you clone it, and then you just move it over to the specific thread that you're spawning. Over here, we're going to do a producer.send. But what is the value that we want to send? We want to send the sum from some number to some number. What are those initial number and final numbers? Let sum equal to 0. It will be a mutable variable. And then you're going to write for I, or whatever, j in I into 10⁻⁷ plus 2, I plus 1 into 10⁻⁷ minus 1, something like this. You have to find the sum from sum plus j. There you go. Something like this. You find the sum from I into 10⁻⁷ to I plus 1 into 10⁻⁷ minus 1. So the sum from I into 10⁻⁷, for I equal to 0, this value will be 0. For I equal to 0, this value will be 10⁻⁷ minus 1. For I equal to 1, this value will be 10⁻⁷. This value will be 2 into 10⁻⁷ minus 1. For I equal to 2, this value will be 2 into 10⁻⁷. This will be 2 into 10⁻⁷ minus 1, so on and so forth. That's how you iterate and find the sum in every respective thread. And finally, you send over this value over the channel. The only problem is it's called sum. And then what happens on the receiver's end? On the receiver's end, you don't receive once. You say for val in rx.receive. You keep adding it to the, let's say, final underscore sum. And then you finally print the final underscore sum over here. For val in rx, that's the right syntax to keep receiving values, as various producers are sending it. And if you want, you can unwrap over here as well. Cool, let's try that out. Let's see if this works or not. Again, to recap, the code that I've written is, I've created a producer and a consumer. I've iterated 10 times to clone the producer, spawn a new thread, move the producer over here. And what value am I sending via the producer? The value that finds the respective sum for this thread. The first thread will find the sum from 0 to 10⁻⁷. Second one will find the sum from 10⁻⁷ to 2 into 10⁻⁷, so on and so forth. By the end of it, we have a final sum variable over here that we're printing, which is getting all the values that are being produced by this producer. If I run this, go run, the final sum, the logic would be wrong if I'm being honest. I've written this. Oh, the thread itself panicked over here. So let's see what happens. What happened here? Sum equals sum plus j. Am I finding two bigger values over here? Attempt to add with overflow. Yeah. Let's make the sum variable over here u64 rather than u32. The same thing for the final sum variable. Maybe the sum becomes too big to be stored in a 64-bit number. I don't know. Sum from 1 to 10⁻⁷, maybe. I don't know. u64 should be good enough, so I'm not worried too much about that. And notice it remains hung. I repeat, the process doesn't exit for some reason. It shouldn't take this long. On 10 threads, you spawn 10 threads. On these 10 threads, you're finding the sum from 1 to 10⁻⁷, 2 to 10⁻⁷. It shouldn't take this long. What's happening? There is one small thing that we've missed. The code that I've written over here says here, until all the producers go out of scope, I will keep waiting for values. The problem is, if you put a log over here, you will see you are receiving values. Received value from thread. you are receiving values. If I run this, you'll see you receive values from all the 10 threads, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the problem is the receiver doesn't know that all the producers have finished. It knows all of these cloned producers have finished, but this TX is still valid. This TX was never moved to a different thread. So what you have to do is explicitly drop this TX variable because you're not using it. The first transmitter over here was never moved to a thread, which means it is still active over here, which means the receiver will keep waiting on it. Maybe it wants to send me something, which is why this for loop never ends. So to make sure this for loop eventually ends, all the transmitters go out of scope. You explicitly drop the first transmitter. You can also find a way to, pass the first transmitter to the first thread and clone the rest of them. That sort of also works. Or, in the last thread or the last iteration, just send the transmitter or just explicitly drop it over here like we've done. Now if I run cargo run, you will see find the final sum from 0 to 10^9, which 10^8, which hopefully is this. This looks wrong. I'm sure there's something wrong that I've done in the logic. I would assume the sum from 1 to 10^7 is not this, but I could be wrong. Maybe it is. Cool. Alrighty, that's how you write multi-threaded code that can share data with let's say the parent thread in this case. So that you can delegate a task like finding a very complicated sum from 1 to 10^8 or 10^9 or 10^10 across various threads on your machine. You don't have a single thread that's doing all of this calculation. Of course, if you do it on a single thread, it will be like 10 times slower than delegating it to so many threads. Alrighty, what went wrong over here in the original code? The thing that went wrong was that the original TX variable was never dropped, and so the for loop kept on waiting on it. What was the solution over there? It was to explicitly drop this TX over here, which I've done here. Explicitly drop the DX variable or the TX variable, sorry, which is this transmitter, so that the receiver is not waiting for this transmitter to also send some data. All of these producers have sent data, but since this transmitter is still active, it's still waiting for that transmitter to send the data unless you explicitly drop it, which we did. That's all we had for multi-threading. Oh boy, a long session. The one thing that's left is macros. Let me quickly take you through them. I don't think we're going to discuss them too much, but let me give you a one-on-one. I think they exist in the C++ also, pretty sure. I don't know what they're called. But macros, let you are code that write other code. I repeat, macros are code that write other code. Whenever you write print ln and it is followed by an exclamation, then this code eventually expands to some really long code that has been written inside this println macro. So what is println? It is a macro, and if you look at this syntax, somewhere somehow it calls create :io underscore print and tries to call another function. So this single line of code gets expanded to a lot of lines of code. The same thing happens when you write let v equal to vec exclamation 1, 2, 3. This is also a macro. If I hover over this and go over here, it says macro underscore rules exclamation vec. So we've been using a lot of macros. We haven't created them, and we probably won't for a really long time, because this is what's called meta programming. Your code writing other code, which is not very easy to do unless you've done computational theory in school or computer science. Is that the right? Probably that's the right subject. I could be wrong, but you need to understand abstract syntax trees. You need to understand compiler design. How is a language written? And how do you parse the syntax of a language? Because whenever you're creating these macros, you're expecting some input from a user, which could be numbers, could be strings, but could be other code as well. I repeat, you could be expecting the user to write something like this code that does something. So you need to parse all of this code and convert it into a different format, which requires some knowledge of how languages are written. Happy to go through it, but probably deserves one thing. I will have to revise this myself, or understand this myself, because I have never created macro in the real world. Probably something good to try out if you're super geeky about it. You do use them from time to time, like I am over here. Do you write them? Probably not. I remember suddenly a video a few years ago where someone wrote a macro like this that would let you pretty much what was it? I'm forgetting. You had to write, maybe not. I don't remember actually. Basically something related to SQL. You'll probably find a video if you're on like Google macros. You'll find like a 5-year old video where something related to SQL was done. I'm totally forgetting now. Okay, it would convert an SQL, it would convert some code into an SQL statement, something like that. When you write something like this, okay, let me not say something that I don't remember very well, but it would eventually spit out SQL queries for you. It was sort of an ORM, if I remember correctly. But yeah, that's one of many use cases of a macro. What is a macro? Code that writes other code that gets expanded to more Rust code eventually, and we have used it from time to time. The topmost level / nirvana over here is you understand how you can write a macro of your own, which we're not doing today. With that, let's go through the topics one more time. What all topics were we supposed to go through today, and what all topics were we able to? We discussed a bunch of beginner things in the first section of this video. In the second section of this video, we were supposed to go through these 3 easy things. We did. I would assume this was very easy to digest. Strings versus string slices. Hopefully you understand this now. String is a type that Rust provides you. String slices are you trying to reference some contiguous segment of that type, and the same applies to arrays and other collections as well. Generics from the live video. Traits very similar to interfaces in JavaScript or TypeScript, and abstract classes in Rust. Multi-threading, how can you run code on various threads together. Lifetimes, probably the most hard thing to digest today. Macros, hopefully you understand what a macro is. Next time you're seeing one, you know what it is. We have not discussed how you can create your own macro. What is left is futures, async await, and Tokyo, which frankly deserves a video of its own anyways. That'll probably be the next video in this series, where we'll write some asynchronous code, because if you're able to write asynchronous code, if you understand the Tokyo runtime, which is one of many asynchronous runtimes that exist in Rust. The reason let me not digress. Long story short, it needs to be a video of its own. And with that video, I think, you can start to write backend servers, basic, HTTP servers, because most HTTP servers will require some sort of async runtime. Tokyo is the most popular one. That's probably the one that we'll discuss in the next video. With that, I think it's super late for me and for you guys as well. Let me know if the video was insightful and what would you like to see next. With that, let's end it. I will see you guys in the next one. Bye bye.